Chapter 14 Quantum Mechanical Postulates Section 14.1 Quantum Mechanical Postulate 1 Quantum mechanics is built on 6 quantum mechanical postulates. Postulate 1 states that all particles are probability waves. The probability distribution of a particle in space can be described by the squared modulus of the wave function of the particle, and this wave function is denoted by uppercase Greek letter psi of r and t, where r specifies the position of the particle, t denotes time, and this r is a vector with 3 components, x, y, and z in the 3 dimensions. At time t, the probability of finding a particle within a box with an infinitesimal volume of dx times dy times dz is psi squared dx dy dz. To be more accurate, this is the squared modulus of psi. At any given time t, the integral of the squared modulus of psi times dx dy dz over the entire space is 100%. So we have this equation. This is a triple integral. X, y, and z are from negative infinity to positive infinity. That means we need to integrate over the entire space. And over here, this expression is the probability of finding the particle within a infinitesimal volume of dx times dy times dz at position x, y, and z. The physical meaning of this equation is that the total probability of finding this particle in the entire space is exactly 100% at any given time. The squared modulus of a function is the sum of its real part squared and its imaginary part squared. For example, if the wave function psi can be written as f plus I times g, where I is the square root of -1, then the squared modulus of psi is simply f squared plus g squared. Both f and g are real. But over here, when you look at this entire expression, it's f plus I times g. So f is the real part, I times g is the imaginary part. The modulus of psi is the square root of f squared plus g squared. F and g are also functions of the position of the particle and time. Again, this r is a vector that's used to specify the position of the particle in a 3-dimensional space. The squared modulus can also be obtained by multiplying the complex conjugate of psi and psi. Psi star denotes the complex conjugate of psi. So how do we get the complex conjugate of a function? It's very easy. You just need to find every occurrence of I in that function and replace all this occurrence of I with negative I, and then you will get the complex conjugate. The complex conjugate of a real function is itself, because there's no replacement. For example, when psi is equal to f plus I times g, then we have the complex conjugate equal f minus I times g. All I did was to replace this I with negative I. Again, the squared modulus of a wave function is equal to its complex conjugate multiplied by that function. So if you have a function f plus I times g, its complex conjugate is f minus I times g. We just need to do this multiplication. We have two terms multiplied by two terms, and of course we're going to get four terms. F times f, that's f squared. Negative ig times ig, that's g squared. It's because negative I times I is 1. We also have negative ifg and positive ifg. They cancel. So in the end, the squared modulus of any complex function that can be expressed as f plus ig is simply f squared plus g squared. Again, the two imaginary parts, negative ifg and positive ifg, cancel in the last step of the derivation. Now let's look at one example problem, 14.1.1. Find the complex conjugate and the squared modulus of a complex function cosine x plus I sine x. Cosine x and sine x are real functions, but this sine x is multiplied by I. Therefore, this I sine x is the imaginary part of the complex function. The complex conjugate of this function is cosine x minus I sine x. I only replaced this I with negative I. The squared modulus would be the function times its complex conjugate. And then we have cosine squared, sine x squared, and then we have two more cross terms, I times sine x cosine x, and also negative I sine x cosine x. So in the end, the squared modulus is 1. Another example problem, 14.1.2. Find the complex conjugate of the following complex functions. ln, the logarithm of I times x times y, e to the power of z, 5 minus ix. You may assume x, y, and z are real. And over here, I just replace this I with negative I. E to the power of negative z does not contain I. It's a real function. Therefore, the complex conjugate of this function is itself 5 minus ix. I just need to replace I with negative I. The complex conjugate is simply 5 plus ix. The squared modulus of psi times d tau is the probability of finding the particle in the volume element d tau. D tau is dx, dy, dz located at position r at time t. And this position r is simply a vector with components x, y, and z in the 3 dimensions. The squared modulus of psi is the probability density. That's probability per unit volume within d tau at time t. At any given time, the total probability of finding the particle in the entire space is 100%. Therefore, this triple integral of the squared modulus of psi dx, dy, dz is 1. Here's an example. When a particle is completely confined in a space with a volume of 100 cubic meters, well, we can calculate its average probability density, because we can just divide this 100% by the total volume of the space. The result is 0.01 per cubic meter, or 1% per cubic meter, and that's the average probability density. Again, the average is only 1% per cubic meter, and then we have 100 cubic meters. Therefore, the total is 100%. If the probability density of the particle is evenly distributed in this 100 cubic meter space at all times, then its wave function is simply the square root of probability density. So we'll just take the square root of this, and the wave function can be expressed as 0.1 times meter to the power of negative 1/2. The unit looks weird, but again, the unit of probability density should be 1 over the unit of volume. The SI unit is 1 over cubic meter. Now the wave function is the square root of the probability density, and therefore its unit should be meter to the power of negative 1/2. In the three-dimensional world, the SI unit of the quantum mechanical wave functions is always meter to the power of negative 1/2. When the distribution of the probability density is inhomogeneous, well, we cannot say the probability density is the same in the entire space. Therefore, we have to resort to integral calculus to calculate the probability within a certain interval in space. For example, let's look at a one-dimensional world. If the wave function of a one-dimensional particle is this function, then we have the integral of this function squared dx is 1 over the entire space. That means x is from negative infinity to positive infinity. C is the normalization constant. The value of C should be chosen so that this integral is exactly 100%. And over here we have an exponential here. The exponential term must be unitless. Now, when the wave function of a particle in the one-dimensional world is the normalization factor times exponential function of negative x over 2 meters, and then we have this integral equal to 1. C is the normalization factor. And over here, this m denotes meter, not mass. It's meter here. Now let's do some mathematics. We can evaluate this integral, and then this way, and this equation is an even function because we have the absolute value of x here, and then we can rewrite this integral as 2 times this integral with a different lower limit. It's from 0 to infinity. Again, it's just because if you look at this integral, x is from negative infinity to positive infinity, and the integral from negative infinity to 0 is equal to the integral from 0 to positive infinity. That's why I have a 2 here and a simpler integral here. We can integrate this. I think we'll get just 1 meter here. So 2 times c squared times 1 meter is just 1. And therefore c squared is 1 over 2 meters, and this normalization factor is 1 over the square root of 2 meters. Now we have this wave function normalized. It's equal to 1 over the square root of 2 meters times e to the power of negative x over 2m. And this x is the absolute value of x. If we use this wave function to plug it in here, if we integrate this, the squared modulus of this with respect to x from negative infinity to positive infinity, we'll be able to get 1. Now, a numerical example 14.1.3. Assuming the wave function of a particle in a one-dimensional world is this, then what's the probability of finding the particle between 1 meter, negative 1 meter, and 1 meter? And what's the probability of finding the particle between negative infinity and negative 1 meter? So we can simply just integrate the probability dx times dx. We just need to use this lower limit and upper limit for the integral. We can evaluate this integral, and this is just mathematical trivia, really easy to do. We get 1 minus e to the power of negative 1 here. The probability is 63%. So if we have this wave function, the probability of finding the particle between negative 1 meter to positive 1 meter is 63%. So there is still 37% chance outside this range. How do we compute the probability of finding the particle between negative infinity and negative 1? Well, again, outside the range from negative 1 meter to positive 1 meter, we have a probability of 1 minus 0.632. And because the probability is an even function of x, so you can see this is an even function of x, we just need to divide this by 2, and then we get 18.4% of finding the particle between negative infinity to negative 1 meter. Also, the probability of finding the particle between positive 1 meter and positive infinity is also 18.4%. So we have 3 ranges. Below 1 meter, the probability is 18.4%. Between negative 1 meter and 1 meter, it's 0.632 or 63%. Between 1 meter and infinity, again 18.4% due to the symmetry. Postulate 1 states that the squared modulus of the quantum mechanical wave function is the probability density of the particle. It also states that the wave function must be single valued, continuous, and finite everywhere in space. So let's look at 3 examples. This is a wave function, but not a QM wave function. This is not a QM wave function either. The third one, again, not a legitimate quantum mechanical wave function. And they are not quantum mechanical wave functions for different reasons. This one, psi is not single valued. So if I have x here, I got 2 different values for psi, and that's a violation to postulate 1. This wave function, well, this is single valued, but it's not continuous right here. This one is single valued and it's continuous, but it's not finite. As x approaches negative infinity, psi approaches infinity. As x approaches infinity, psi also approaches infinity. Make sure this psi is always finite everywhere, even if x approaches infinity or negative infinity. The essence of postulate 1 is that particles are waves and waves are particles. For each particle, we can use a wave function to describe it. The wave-particle duality is supported by 2 experiments. The first experiment is the double-slit diffraction of electrons that proves electrons are waves. The second experiment is the photoelectric effect experiment that proves photons are particles. Now let's look at the double-slit diffraction pattern of electrons. If we have an electron gun that shoots electrons, allow the electrons to pass through slits, and then we'll observe the interference pattern of waves, the same as water waves. So it can be, well, you may imagine this is water waves, you may imagine this is light waves, but anyway, the interference between electrons create this kind of pattern with the brightest stripe in the middle, and then, well, the lightest, and then brightest, and then the lightest. So we get this kind of patterns because electrons are waves, and waves can interfere with each other. We have two wavefronts from the two slits, and we can have constructive interference and destructive interference. When we have constructive interference between the two electron waves, we see a really bright spot in the middle. But when they cancel, because they are out of phase, you see the lightest stripes. The photoelectric effect experiment proves light consists of individual particles, and those particles are called photons, and each photon is a particle of light. When light is shed on the surface of a metal, an electron on the metal surface may absorb a photon and be ejected. If the energy of the photon is greater than the work function of the metal, the work function is the minimum energy required to eject an electron from a piece of solid. The work function is similar to the ionization energy. The difference is small. Ionization energy is the minimum amount of energy required to eject an electron from an atom. The work function is the minimum amount of energy required to eject an electron from a piece of solid that consists of many atoms. The kinetic energy of the ejected electron is the energy of the photon minus the work function. So the electron needs at least this much energy to escape. And if it can escape, the kinetic energy of the electron that escapes from the metal is equal to the total energy it gets from the photon, which is h nu, minus the minimum amount of energy required for the electron to be ejected. Therefore, the work function can be calculated using this equation, h nu minus the kinetic energy of the photon. The work function of the metal in this diagram can be calculated. Let's do some calculation. So we have this kinetic energy. Well, this is speed, but using half mv squared, we can get the kinetic energy of this ejected electron. And also we have the wavelengths here, so we can compute the energy of the photon. It's given here, it's 3.1 electron volt. You can double check this number. So we have 3.1 electron volt minus the kinetic energy of this electron. We'll get the work function. We can use this data as well. So we have the energy of the photon, 2.25 electron volts. We can calculate the kinetic energy of the electron, which is 1/2 times the mass of the electron times its speed. And then we take the difference between h nu, the energy of the photon, in this case 2.25 electron volts, and then minus 1/2 times the mass of the electron times the speed squared. We'll get the wave function for this metal. Now let's look at one example problem, 14.1.4. We can also plot the kinetic energy of the ejected electrons versus the frequency of the photon in an Excel spreadsheet and determine the Planck constant. Here's how. Let's say we have two data points. We have the wavelengths of the photon, and then we calculate the frequencies of the photon. We have the speed of the ejected electron, and then we can compute the kinetic energy of the ejected electron. Now what do? Kinetic energy is a linear function of frequency. The slope is h. The intercept is negative w. If we plot kinetic energy versus frequency, so it's pretty simple. Make a graph of kinetic energy of the ejected electron versus the frequency of the photon. The slope is going to be the Planck constant, and negative w is going to be the intercept. Now again, let's look at this example problem. We have kinetic energy here, we have frequency here. We make a graph, we do linear regression, we determine the slope. Slope is 6.67 times 10 to the power of negative 34. What's the unit? Joule over Hertz. And this is simply the Planck constant. And over here we have the intercept, a negative intercept. This is actually negative work function. So immediately we know the work function is 3.24 times 10 to the power of negative 19 joule. So we have learned that particles are waves, waves are particles. Two examples: electrons, we know they are particles, but they are also waves. Light, we know light is a wave, but light consists of particles as well. Each particle is a photon. In 1924, de Broglie proposed an equation that quantified the wave-particle duality. The equation is simple. Lambda is h over p. Lambda is the wavelength of a particle. P is the momentum of the particle. H is the Planck constant. But over here, make sure that this P is the unsigned magnitude of P, or the absolute value of P. This is to avoid getting a negative lambda. Although particles are also waves, it's impossible to observe the wave-like properties of a macroscopic object. Why is that? Very simple. A macroscopic object is also a wave, but its wavelength is extremely small. It's impossible to measure. On the other hand, the wavelength of a very light particle, such as an electron, can be much more easily measured. Now let's look at one numerical example problem, 14.1.5. Calculate the wavelength of a football that flies at 20 meters per second. A typical football weighs 0.4 kilograms. So lambda is h over p, p is mv. We plug in the numbers. Well, the wavelength of this football is 7.9 times 10 to the power of negative 35 meters. We won't be able to observe such a small wavelength. The smallest length we can ever measure is 10 to the power of negative 18, and this wavelength is much smaller than this threshold. We simply cannot measure or detect the wavelength of the football. It's too heavy. Now let's look at another numerical example problem. This time we'll calculate the wavelength of an electron that moves at 2 millimeters per second. The mass of the electron is 9 times 10 to the power of negative 31 kilogram. We plug in the numbers h, m, and v. We get 3.6 angstroms, or 0.36 nanometers. And it's fairly easy for scientists to measure a wavelength like this. Now we just showed that all particles are waves. It's just very difficult to measure the wavelength of a macroscopic object such as football. but it's easy to measure the wavelengths of an electron. Like electrons, photons are also waves and particles. So we can compute the mass of a photon as well. We know the rest mass of photon is 0, but photons move. They move at the speed of light. And when a photon moves at the speed of light, it has a non-zero mass. Its moving mass can be predicted using the Balois equation. Again, the information we have is lambda, 500 nanometers. Now we're going to use this equation. Lambda is h over p, and the momentum is mass times the speed. So the mass is equal to h over lambda v from this equation. We plug in h, the Planck constant, lambda, the wavelength, the speed of light. We get 4.4 times 10 to the power of negative 36 kilogram. So a moving photon with a wavelength of 500 nanometers has a moving mass, which is 4.4 times 10 to the power of negative 36 kilograms. Planck introduced the term quantum in quantum mechanics by showing that the energies of the photons emitted by a heated object are quantized. A heated enclosed cavity emits electromagnetic waves, and it's so-called black body radiation because the design of the apparatus makes sure light can hardly escape from the cavity. Electromagnetic theory predicts that the spectral density of the photons inside this cavity can be calculated this way. Rho is 8 pi nu squared over c cubed multiplied by the average oscillation energy of the atoms inside this cavity. Now what is rho? Rho is the intensity of the emitted waves divided by the range of the frequency. Alright, for example, if you have intensity of a photon between 10 to the power of 14 Hertz and 10 to the power of 15 Hertz, you just need to use the intensity divided by 10 to the power of 15 minus 10 to the power of 14. Now let's look at some classical mechanics predictions. Classical mechanics predicts that the oscillation energy of the atoms inside the cavity is kBt on average. This is based on an assumption that energy is continuous. That means the energy spacings between any two adjacent oscillation energy levels should be infinitesimal. And therefore we have this equation. We plug in this oscillation energy equals kBt over here. We get this expression. It shows this spectral density rho is proportional to nu squared or frequency squared. That means as the frequency increases, rho increases. However, that's not the case when we do the experiments. There are mismatches. Now let's look at some experiments that were conducted to plot this spectral density rho versus nu squared. When the frequencies are low, we have this 8. Well, we have this equation, and how low should this frequency be when we have this proportionality? Well, the criterion is this: nu should be low enough that h nu is much smaller than kBt. And then we have the spectral density proportional to the frequency squared. However, experimentally also, we found that when the frequencies are really high, so maybe this h nu can be much greater than kBt, well, we found rho is equal to a pi nu squared over c squared times the average oscillation energy, and that approaches zero. So there's some disagreement. Classical mechanics predicts that the spectral density is always proportional to nu squared. In quantum mechanics, rho is proportional to nu squared only when the frequencies of the oscillation of the atoms are very low. What if you have high frequencies? Well, in that case, the spectral density approaches zero. Now let's look at a graph over here. The graph is intensity versus wavelength. So when you have a larger wavelength, you have a small frequency. When you have a small wavelength, you have a large frequency. So in this region, you can tell that the intensity decreases as the wavelength increases. But in this region, you can see intensity increases as the wavelength increases. So now let's think about this. When the wavelength approaches zero, its frequency approaches infinity. So that's a really high frequency scenario. And this rho is supposed to be approaching zero. So over here, these three curves are approaching zero when the wavelength is small. Now when the wavelength is large, we'll have a smaller frequency. And then we should use this equation to make predictions. Since we have low frequency, h nu is smaller than kBt, the spectral density rho is equal to nu squared over c squared times kBt. Alright? And this rho is just proportional to nu squared. So now let's look at this example again. There's a mismatch between the experiments and the prediction from classical mechanics, and it's called ultraviolet catastrophe because the mismatch is serious in the UV range. The mismatch is less serious in the visible range. The mismatch can be almost neglected in the infrared range. So what causes this ultraviolet catastrophe? So what happens to the relationship between the spectral density and the wavelengths? Well, the thing is, in classical mechanics, the oscillation energy levels are assumed to be continuous. Based on this assumption, we can derive the oscillation energy to be kBt. That's doable. But Planck proposed that energy is quantized in this black body container or cavity. The only allowed energy values are in 1 times h nu, 2 times h nu, 3 times h nu, etc. And based on this assumption, Planck derived this equation. He said if the frequency is high in the UV range, the oscillation energy is equal to h nu time divided by e to the power h nu over kBt minus 1. Well, apparently this oscillation energy is not just kBt. So over here, classical mechanics, it's kBt. Over here, well, definitely it's not kBt. So Planck proposed a different expression for the oscillation energy. And the spectral density is equal to a pi nu squared over c squared times the oscillation energy. So we have this expression. What if nu approaches 0? Well, in that case, the exponential function minus 1 is approaching h nu over kBt. So you just need to know the Maclaurin expansion for the exponential function. The Maclaurin expansion of e to the power of delta is simply 1 plus delta squared over 2 factorial plus delta cubed over 3 factorial, etc. When delta is small, we can keep only the first two terms, 1 plus delta. And therefore, this equation, e to the power of h nu over kBt minus 1, is simply h nu over kBt, as long as nu is small enough. And now we can further simplify the expression of rho. You can see rho is now proportional to kBt when the frequency is low. So at a low frequency, the classical mechanics holds. The oscillation energy is proportional to kBt. But what if we have a high frequency? When we have a high frequency, now let's look at this expression again. When we have a high frequency where h nu is much greater than kBt, what will happen here? Well, this part is going to be infinity. Alright, so e to the power of h nu over kBt will be approaching infinity. And on top, I think we have nu to the power of 3. It also approaches infinity. However, the exponential function approaches infinity faster than the polynomial functions. So that means when h nu is much greater than kBt, well, we're gonna just have this rho approaches 0, because although the top and the bottom both approach infinity, the bottom exponential function approaches infinity much faster than this nu cubed. We can also use this expression to make a prediction about when this rho reaches maximum. Well, it's pretty simple. We just need to take the first derivative of this with respect to the frequency nu, and then we can set d rho, this is d rho, the exact differential of this with respect to frequency is 0, and we can do variable substitution to make the calculation a little easier. If we assume h nu over kBt is denoted by x, well, then first derivative of this rho with respect to nu is gonna be computed given this expression, and setting this first derivative to 0, we'll get e to the power of negative x equals 1 minus x over 2. Again, x denotes h nu over kBt. Solving this equation, we get x is 1.6. So you can see the maximum here, here, and here. You'll see at the maximum h nu is 1.6 kBt. So when you have a higher temperature, well, you'll have a larger frequency. Alright, higher temperature from 3000 to 4000 to 5000. You can see lambda decreases, and that means this nu increases. Alright, for the maximum point here, here, and here. At this 3 points, h nu should be 1.6 times kBt. Chapter 14, Quantum Mechanical Postulates. Section 14.2, Quantum Mechanical Postulate 2. Quantum mechanical postulate 2 states that for every physical observable, such as position, momentum, or energy, there is a corresponding operator in quantum mechanics. The quantum mechanical operators can be applied to the wave functions of a system, and the quantum mechanical operations can transform those wave functions. Now let's look at several examples. The position of a particle isn't observable. In classical physics, we use x, y, and z to specify the position of a particle in the 3 dimensions. In quantum mechanics, we have corresponding operators, x, y, and z with a caret on top. When you see a caret, it's an operator. We apply those operators to wave functions, and the corresponding operation is multiplied by x, y, or z. For example, if you apply this x operator to sine x, the result is the product of x and sine x. Momentum is another physical observable. In classical mechanics, we have P equals mv, or P sub x equals mv sub x in the x direction. We have similar equations for the momentum in the y direction and z direction. Correspondingly, we have quantum mechanical operators. We put a caret on top of P. Now we have a momentum operator. This P sub x is the operator in the x direction. The corresponding operation is to apply negative I h bar delta over delta x to the wave function. For example, if the wave function is sine x, we just need to apply this to sine x. We will get negative I h bar cosine x. Similarly, we have corresponding momentum operators in the y direction and z direction. H bar is the reduced Planck constant. H bar is simply the Planck constant over 2 pi. We plug in the numbers. H bar is roughly 10 to the power of negative 34 joules second. And this I is the square root of negative 1. I is an imaginary number. Postulate 2 states that for every physical observable in classical mechanics, there's a corresponding quantum mechanical operator. In general, operators transform functions and numbers. Again, there are some more general examples over here. If we apply x operator to psi, it's simply x times psi. We apply y operator to psi, it's just y times psi. Now, what if we apply this momentum operator to psi, and we get negative I h bar delta over delta x of psi? So we do need to take the first derivative of this wave function with respect to x, and then the result multiplied by negative I h bar. That's the result of applying the momentum operator to psi. And we have x, y, and z directions. We have similar equations. Now for a particle in a one-dimensional world, let's say x direction, we have this simple equation. We apply the momentum operator to psi. We get negative I h bar times the first derivative of psi with respect to x. If the wave function does not change with time, then we lose this variable t. There's only one variable in this equation, that's the position. So when we apply this momentum operator to psi, we get negative I h bar times d psi over dx. So we switch the notation from delta to d because in this case we have only one variable. It's single variable calculus here. There are many more observables in physics, like kinetic energy, potential energy, and total energy. In classical mechanics, the kinetic energy of a particle is half mv squared. In quantum mechanics, we have a notation here. We put a caret on top of this E sub kinetic. What's the corresponding operation? Well, it gets more complicated. It's negative h bar squared over 2m. And then we have the sum of 3 second derivative operators. We need to apply all this to a wave function. And really, just you take the second derivative of the wave function with respect to x, with respect to y, with respect to z, sum everything up, and then multiply the sum by negative h bar squared over 2m. That's how the operation works. Potential energy. In classical mechanics, we use this notation, E sub potential, or sometimes just PE as potential energy. And the difference between kinetic energy and potential energy is this. Kinetic energy depends on the motion of the particles. Potential energy depends on the position of the particles. In quantum mechanics, we use this notation. We put a caret on top of E sub potential, or simply use V with a caret on top. And the operation is just multiplied by the function of V. V is a function of the position of the particle. What about the total energy? In classical mechanics, it's denoted by E. In quantum mechanics, it's denoted by H with a caret on top. The name is Hamiltonian. The Hamiltonian operator is equal to the kinetic energy operator plus the potential energy operator. So now we have the kinetic energy operator here, we have the potential energy operator here. The sum would be the Hamiltonian. Now, for example, if we apply the Hamiltonian operator to psi, it's equivalent to the sum of applying the kinetic energy operator to psi and then apply the potential energy operator to psi for a 3D particle. For a 3D particle, we have x, y, and z. In this kinetic energy operator, we have x, y, and z in the potential energy operator. Equivalently, we can write this. H psi is equal to negative h bar squared over 2m. Now, inside this parenthesis, we just apply those second derivative operators to psi individually and sum them up. And finally, when we apply the potential energy operator to psi, it's just multiplication. The potential energy operator, V with a caret, being applied to psi is equivalent to a multiplication between the function of the potential energy and psi. Finally, we'll look at angular momentum as a physical observable. It's a three-dimensional vector in the three-dimensional world. There are three components. In classical mechanics, we use L sub x, L sub y, L sub z as the components of the angular momentum in the x, y, and z direction. In quantum mechanics, the notation is similar. We just put a caret on top of Lx, Ly, Lz. But what are the operations? Well, it's negative I h bar times y, delta over delta z minus z, and then delta over delta y. It looks a little strange over here. Why so complicated? Well, just remember, in classical mechanics, we know the angular momentum is this r, the radius vector. The radius vector cross product the momentum vector. So if you know how to deal with the cross product of two vectors, that would be great. But if not, well, the cross product of two vectors can be expressed as a 3×3 determinant. I, j, k are the unit vectors in the x, y, and z direction. X, y, z are the three components of the radius vector. Px, py, pz are the three components of momentum in the x, y, and z direction. And there's a way to decompose a 3x3 determinant into three 2x2 determinants like this. So you have this I multiplied by this 2x2 determinant here, and then J multiplied by this determinant xz px pz. But you also need to remember to put a negative sign here. Now let's look at this k unit vector. It's also multiplied by a 2x2 determinant. Over here, xy on top, px py on the bottom right here. Now the sign is positive. So we need to have this positive, negative alternatively. If you're doing some, larger determinants. And now we can easily evaluate 2x2 determinants. Over here it's just y times pz minus z times py over here. And now remember, pz has a corresponding quantum mechanical operator. The quantum mechanical operator of pz is negative ih bar delta over delta z. So really you are looking at y times pz here. Now over here, py, what is py in quantum mechanics? It's negative ih bar times delta over delta y. So that's why you see this form as the x component of the angular momentum operator in quantum mechanics. And similarly for L sub y, the corresponding operator can be expressed by using this and then put a caret on top of px and pz. If you put a caret on top of px, it becomes an operator. It's negative ih bar times delta over delta x. And the pz operator is negative ih bar times delta over delta z. Alright, this is just a animation for looking at the angular momentum in classical physics. This L is R cross product P. The expression of angular momentum in classical physics can be expressed as the x component plus the y component plus the z component. I, j, k are the unit factors in the x, y, and z direction. The corresponding angular momentum operator in quantum mechanics can be written similarly. You just don't forget to put a caret on top of the momentum, and we have this expression. The x, y, z components of the angular momentum operators are the three equations. Again, L sub x corresponds to negative ih bar times y delta over delta z minus z delta over delta y operation. So again, this is gonna be our operation, and when we apply the L sub x operator to a function, essentially we are applying this whole thing to that wave function. And L, the three-dimensional vector of angular momentum, is the sum of the three components, in this case the three operators in the x direction, y direction, and z direction. So if you apply this angular momentum vector to a wave function, well, you will end up with a three-dimensional vector. Here we review how to deal with determinants, especially 3x3 determinants. This is a very simple example. If you have a 3x3 determinants, how do we evaluate the value of this? Well, what you want to do is pretty simple. You first write out this determinants. Alright, the first column, the second column, the third column, and then you copy the first column here, and then you copy the fourth column here. Alright, so now what you need to do is you need to draw 6 arrows. 3 arrows this direction, 3 arrows the other direction. The 3 blue arrows will be positive. So you're going to do negative 7 times negative 9 times 2. You get positive 126. And you just multiply these three numbers, negative 140. Multiply these three numbers, 12. And now you need to subtract the 3 red arrows. Over here you need to subtract the product of 7, -9, and 4. You need to subtract the sum of this. You need to subtract the sum of this. And you can see the blue ones, alright, you do pluses. The red ones, you do minuses. But in this case, the blue ones are negative, so you do minus negative numbers. The result is 324. Here's a numerical example problem, 14.2.1. Let's evaluate those determinants. Those are all 3 by 3 determinants. So first one, 1, 2, 3, 4, 5, 6, 7, 8, 9. All you need to do is these 3 numbers, 1, 5, 9, right? And then 2, 6. Imagine a 7 here, so 2, 6, 7. And then 3, 4, 8, because you need to just copy this column and this column here and here, and then you get this. And then you do backward. You do 3, 5, 7. So backward 3, 5, 7. So it's just slash versus backslash. All right, slash versus backslash. So you have -3, 5, 7. All right, and then 8, 6. Okay, over here it should be 1. So it's 8, 6, 1. So right here, and then finally 2, 4, 9. And then the result is 0. And this one is actually equivalent to this one, because if you pay attention to all those numbers, I simply rotated those numbers by 90 degrees. When that happens, we're not gonna change the values over here, because you still have 1 times 5 times 9, and you still have 4 times 8 times 3, so like this. You still have 2 times 6, 2 times 7, so like this. Alright, so the same values. Okay, these two same values. Finally, we have some variables in this, but the same principle. If you do not like to copy the first column and second column here and here, there's another way to do it. You just do 1 times 5 times z, so this direction. Remember, we're gonna do this direction from top left to bottom right. Alright, and then 2 times 6. Alright, 2 times 6. And then you need to find another element that's not in the same row or column with this element 2 or this element 6. That's x, so 2 times 6 times x. Alright, and then 4 times y, and then times 3, because this 3 is not in the same row or column with 4 or y, so 3 times 4 times y. Alright, and then we change the direction. 3 times 5 times x, it's gotta be negative. And then 6 times y times 1, it's negative. 2 times 4 times z, it's negative. So we got this expression. Anyway, it's pretty simple to do. Chapter 14, Quantum Mechanical Postulates, Section 14.3, Quantum Mechanical Postulate 3. Quantum Mechanical Postulate 3 states that in any measurement of the physical observable, denoted by uppercase O of a system, the only values that will ever be observed are the eigenvalues associated with the eigenfunction of the O operator. Again, this O with a caret on top denotes the quantum mechanical operator O. We have this equation, O psi equals O psi. On the left, we have a operator, O with a caret on top. On the right hand side, we have a constant, lowercase o multiplied by psi. So if this equation holds true, then psi is an eigenfunction of the quantum mechanical operator O. The lowercase o is the corresponding eigenvalue. This lowercase o must be a constant to be the eigenvalue. When a function psi satisfies this equation, we say psi is an eigenfunction of the O operator. The condition is simply O psi over psi is a constant, and that constant is denoted by a lowercase o. So over here, if you apply the O operator to psi and then divide by psi, if the result is a constant, we say the function psi is an eigenfunction of the O operator with the corresponding eigenvalue, which is that constant denoted by lowercase o. Here's an example. Sine kx and cosine 5kx are both eigenfunctions of the second derivative operator, assuming k is constant. And now let's just evaluate this. Let's apply the operator to the function and then divide it by the function. Let's try sine kx. I'm applying the second derivative operator to sine kx. I got negative k squared sine kx, and then divided by sine kx, the result is negative k squared. Since k is assumed to be a constant, so indeed when we apply the operator to the function and then divide it by the function, we get a constant. That means sine kx is an eigenfunction of the second derivative operator. The corresponding eigenvalue is negative k squared. What about cosine 5kx? Again, we take the second derivative of cosine 5kx. The result is negative 25k squared cosine 5kx. Now divided by the original function, we get negative 25k squared, which is a constant. That means cosine 5kx is an eigenfunction of the second derivative operator, and it has a corresponding eigenvalue of negative 25k squared. If the wave function psi of a system is an eigenfunction of O operator with eigenvalue lowercase o, then any measurement of this quantity uppercase O of this system will yield a value of the lowercase o, the eigenvalue. For example, if the wave function of a system is e to the power of negative ikx, where k is a constant, I is the square root of negative 1, then it's an eigenfunction of the momentum operator. Let's try this. Let's apply the momentum operator to the function. We have negative ih bar d over dx, the e to the power of negative ikx. We take the first derivative, we get negative ik here, and then we have this exponential function. The result is negative kh bar multiplied by the wave function e to the power of negative ikx, and therefore this negative e to the power of negative ikx is indeed an eigenfunction of the momentum operator, and also the corresponding eigenvalue is negative kh bar. That means if we measure the momentum of such a system, the measured value is always negative kh bar, the eigenvalue here. This system has a exact momentum, negative kh bar in the x direction. A function may be an eigenfunction of one operator but not an eigenfunction of a different operator. For example, sine kx and cosine 5kx are both eigenfunctions of the second derivative operator, but they are not the eigenfunctions of the momentum operator. We can double check. We can apply the momentum operator to sine kx and divide by sine kx. Well, the result is definitely not a constant. Sine kx is not an eigenfunction of the momentum operator. Same here, if we apply the momentum operator to cosine 5kx and divide by cosine 5kx, we're not getting a constant here, and therefore cosine 5kx is not an eigenfunction of the momentum operator. Although a measurement of the physical property O of a system must always yield one of the eigenvalues, the initial state of the system does not always have to be an eigenstate of the operator O, which means, well, O psi over psi may not be a constant. So what will happen if you try to measure the physical property O? In this case, the measurement is probabilistic, like the outcome of buying a lottery ticket. When you buy a lottery ticket, what will the outcome be? We don't know. You might get nothing. You might get $1 billion. You might get some other amount in between. We do not know. It's all about probability. So if we have an arbitrary wave function psi, well, it can always be expressed as a linear combination of the eigenfunctions of any given quantum mechanical operator. So we have this equation. this psi is an arbitrary function. It can be expressed as the sum of Ci psi I. Ci is a coefficient. Psi sub I is an eigenfunction of the O operator. So really, even if this psi by itself is not an eigenfunction of the O operator, it can be expressed as the sum of many eigenfunctions of this O operator, and very likely we have a infinite number of terms here, so this I is from 1 to infinity. And again, C sub I is just the coefficient of psi sub I. C sub I squared has a physical meaning. That's the probability of having this system appearing in this eigenstate. Here's an example. If the eigenfunction of a system is sine kx, where k is a constant, we know that sine kx is not an eigenfunction of the momentum operator. We double check this. We apply the momentum operator to sine kx and then divide by sine kx. We did not get a constant. But however, we have this wave function expressed as a linear combination of the eigenfunctions of the momentum operator. And this is the momentum operator, and right now I'm expressing the sine kx as a linear combination of two eigenfunctions of the momentum operator. We can verify that e to the power of ikx is an eigenfunction of the px momentum operator with an eigenvalue of k times h bar. We can also verify this e to the power of negative ikx is also an eigenfunction of the momentum operator with an eigenvalue of negative kh bar. I'd like to verify these two are both eigenfunctions of the momentum operators with eigenvalues of kh bar and negative kh bar respectively. So again, if we have a function here, sine kx, that is not an eigenfunction of the momentum operator, well, it can be expressed as a linear combination of the eigenfunctions of the momentum operator. So we will get around the problem here. So if we try to measure the momentum of this system with a wave function of sine kx, well, sometimes we will get a measurement value of kh bar, sometimes negative kh bar. Again, we can verify that both e to the power of ikx and e to the power of negative ikx are the eigenfunctions of the momentum operator. Simply by applying the momentum operator to this function, we get kh bar multiplied by this function. We can apply the momentum operator to the other wave function e to the power of negative ikx, and we get negative kh bar times e to the power of negative ikx. We have another eigenvalue here, negative kh bar. So we know if we apply the momentum operator to this sine kx, and this sine kx by itself is not an eigenfunction, it's a combination of the eigenfunctions, then, well, what are we gonna see when we measure the momentum of the system? The result is probabilistic. The result can be kh bar or negative kh bar with 50-50 chance. Alright, so if you try to measure the momentum of this system, sine kx, well, it's possible you get kh bar, it's possible you get negative kh bar, each with 50% chance. And again, initially this system does not really have an exact momentum because it can be negative or positive kh bar. However, after the first measurement, the initial wave function of the system, sine kx, will collapse into one of these two eigenfunctions. Alright, either this or this, 50% chance for each. Alright, and also it's going to yield a result of kh bar or negative kh bar. So if you want to measure the momentum again, if the first measurement is kh bar, that means the system now has a wave function of e to the power of ikx. And then if you measure the momentum again, you get kh bar again. You measure it a third time, kh bar. You keep measuring the momentum of this system. Well, only the first measurement is probabilistic. It can be plus or minus kh bar. But the second, third, fourth, fifth, sixth measurements all agree with the first measurement only because right after the first measurement, the wave function of the system is no longer sine kx. It collapses into either e to the power of ikx or e to the power of negative ikx. And then if you keep measuring the momentum of the system, you will get the same eigenvalue repeatedly. Now let's look at one example problem, 14.3.1. Let's say the wave function of a particle in the one-dimensional world is this. Psi is 0.6 times e to the power of ikx minus 0.8 times e to the power of negative ikx. Don't worry about this. This is just a normalization factor. I introduced this in just to ensure that the integral of the squared modulus of psi over the entire space is 1. Now let's measure the momentum of the system. Psi is a linear combination of the two eigenfunctions of the momentum operator e to the power of ikx and e to the power of negative ikx. Again, we can easily verify these two are the eigenfunctions of the momentum operator. They have eigenvalues of kh bar and negative kh bar. So if you try to measure the momentum of the system with a wave function of sine kx, well, the measured value is probabilistic. If you want to measure the momentum of this system, okay, this is not sine kx. Alright, this is not sine kx. It's just a different wave function. If you try to measure the momentum of this one, well, with 36% probability, you'll get kh bar. 64% probability, you'll get negative kh bar. Why 36%? Well, the probability is proportional to this coefficient squared, and this probability is proportional to this coefficient squared. So if we square both, we get 0.36, and this is 0.64, and now we have 36% versus 64% chances of getting kh bar associated with this eigenfunction or negative kh bar associated with this eigenfunction. Again, this is just the first measurement. After the first measurement, the wave function of the system collapses into either e to the power of ikx or e to the power of negative ikx. And then the second, third, fourth, fifth measurements all agree with the first measurement. So if you try to measure the momentum of this wave function repeatedly with 36% chance, you'll get kh bar, kh bar, kh bar, kh bar, kh bar. With 64% chance, you'll get negative kh bar repeatedly. Chapter 14, Quantum Mechanical Postulates, Section 14.4, Quantum Mechanical Postulate 4. Postulate 4 states that if a quantum mechanical system has a wave function psi, then the expectation value of the observable O corresponding to quantum mechanical operator O is given by this equation. Over here we have the expectation value of the observable O. The notation is this lowercase o enclosed in a pair of brackets. On the right hand side we have a fraction. We have this integral on top, the integral of psi star times O psi d tau, and O psi is this O operator being applied to psi. On the bottom we have the integral of psi star psi d tau. Psi star is the complex conjugate of psi. If psi is real, then psi star is equal to psi. If psi is already normalized, then the integral of psi star times psi is just 1. Then the expectation value of the observable O is equal to the integral of psi star times O psi d tau. When you evaluate this kind of integrals, you need to apply the operator O to psi first, and then do a multiplication between psi star and O psi, and then finally integrate the product over the entire space. Here's an example. If the wave function of a system is sine kx from negative a to positive a and 0 everywhere else, then the expectation value of the momentum of the system is this. Over here, this px enclosed in a pair of brackets is the expectation value of the momentum of this particle. And again, we have two integrals. On the bottom, it's the integral of psi star psi d tau. On top, that's the integral of psi star multiplied by, over here, this is the momentum operator being applied to the wave function psi. Now, if this psi is already normalized, then the bottom is simply 1. But I don't think this sine kx is normalized, so we need to integrate the top and then the bottom and then do a division. Now let's look at the integral on the top. The integral of psi star multiplied by px psi is this. I replaced psi star with sine kx. Psi is also sine kx. This is because we have a real function here. And then we need to apply this px to psi. Px is the momentum operator. This operator is negative I h bar d over dx. We apply this momentum operator to sine kx. And the result is negative I h bar times k times cosine kx. And then we integrate a constant times sine kx and cosine kx. But I also want to show you a trick of doing this kind of integrals. Well, if you look at this expression, we have dx here and dx on the bottom, so really they can cancel. And then all we have is negative I h bar times the differential of sine kx. We can take negative I h bar out of integral like this, and then we have to integrate sine kx d sine kx. Well, we can just mentally do a variable substitution. We'll set z to be sine kx. You're integrating z dz. That's 1/2 z squared. That's why you see this 1/2 sine kx squared over here. And x is from negative a to positive a. So if you plug in positive a and negative a, well, you'll just get the same result. They cancel. So this integral is just 0. The expectation value of the momentum of this system is simply 0. But wait, we didn't even compute the integral on the bottom. Well, we don't have to, because on top we have a 0, so on the bottom, whatever value you get, 0 over that value is going to be 0. So we're going to say the expectation value of the momentum of the system with a wave function of sine x is simply 0. And we do expect this kind of result. It is 0 because we learned sine kx can be written as a linear combination of e to the power of ikx and e to the power of negative ikx. The former has a momentum of kh bar. The latter has a momentum of negative kh bar. And it's 50-50 chance. So the expectation value is kh bar times 50% plus negative kh bar times 50%. It should be 0. An arbitrary state can be expressed as a linear combination of multiple eigenfunctions of the operator O. So usually if we have an arbitrary function psi, we can express this as the sum of ci psi I. Ci is just a coefficient. Psi I is one of the eigenfunctions of the quantum mechanical operator. The physical meaning of this Ci squared is the probability of finding a system in the ith eigenstate. That means with this psi sub I eigenfunction. If psi and psi sub I are already normalized, then the average value of property O is simple. There's no calculus. It's just the sum of the probability times the corresponding value. So it's just we have a certain probability of finding a eigenvalue, which is O sub I, and the probability is C sub I squared. Now here's an example. The wave function of the electron in hydrogen may be a linear combination of several eigenfunctions. Here's just one example. It's possible for the for the electron in the hydrogen atom to have this kind of wave function: 0.8 times the 1s orbital minus 0.6 times 3p orbital. What's the physical meaning of this? Well, if you have a wave function like this electron is in the 1s orbital and 3p orbital at the same time. If you really want to see, whether this electron is in the L1s orbital or 3p orbital, you have to make a measurement. When you make a measurement, 64% chance the electron is in the 1s orbital, 36% chance this electron is in the 3p orbital. It's just because when we square the coefficient over here, we get 64%, this one 36%. What if you're about to measure the energy of this electron? Well, again, it's going to give you the energy of the 1s orbital with 64% chance. It might give you the 3p orbital energy with 36% chance. The 1s orbital has an energy of -1/2 atomic unit of energy. The energy of 3p orbital is -1/18th atomic unit. 1 atomic unit is about 2625.5 kilojoule per mole. So if you really want to convert it to kilojoule per mole, you can, but we don't have to. We can just use atomic unit right here to compute the expectation value of the energy of this electron with 64% chance in the 1s orbital and 36% chance in the 3p orbital. All we need to do is we have the probability of having -1/2 atomic unit, 36 probability of having -1/18 atomic unit. We sum it up, we get -0.34 atomic unit energy. Alright, this is the expectation value of the energy of the electron. However, if you really want to measure the energy of the electron, well, you're not going to get -0.34. You can only get the eigenvalues. That means you can either get -1/2 or -1/18. It's never going to be -0.34. Again, it has to be -1/2 or -1/18. The electron will have to collapse into a 1s electron or 3p electron when you try to measure its energy. Again, it's probabilistic. There are two possible outcomes: -1/2 with this much chance, or -1/18 with this much chance. But I do want to emphasize the expectation value is -0.34. So when do we have this? Well, experimentally, if you have this kind of system with a hydrogen in both the 1s orbital and 3p orbital with 64/36 probability, and then you can somehow prepare 1,000,000 such identical systems and measure their energy. About 64 of this 1,000,000 hydrogen atoms will give you -1/2. 36% of the 1,000,000 measurements of the 1,000,000 identical systems will give you -1/18. And then you take the average. That's going to be -0.34. Now let's look at example problem 14.3.1. The wave function of a particle in the one-dimensional world is this: 0.6 times e to the power of ikx minus 0.8 times e to the power of negative ikx. N is just the normalization factor. We have this n here to ensure the integral of the squared modulus of psi is 1. Now let's look at the expectation value of the momentum of this system. The general equation for the expectation value is this: the expectation value of O is the integral of psi star times O psi divided by the integral of psi star times psi. Now let's evaluate the expectation value of the momentum of this system. We plug in the expression of psi here, and over here this is actually after we apply the px operator to psi. So remember, px is negative IH bar delta over delta x. Alright, when you apply this px to this, because there's a negative sign here, this sign becomes positive, because negative times another negative, it becomes positive. So on top we have this expression. There is a kh bar constant. I took it out of the integral. On the bottom we have this expression, and then we have 2 terms times 2 terms on top, 2 terms times 2 terms on the bottom. So we just do some algebra of complex functions. We have this, and well, somehow if you know that e to the power of I theta is cosine theta plus I times sine theta, we can do a conversion from this, a linear combination of ikx and negative ikx to here, and from here to here. So really the combination of these two exponential functions can be expressed as a sine function. The linear combination of these two can be expressed as a cosine function. Now we have this. And now if we look at these two integrals, on top we have minus 0.28, and then over this sine function. Look, this integral is from negative infinity to positive infinity. So the integral of this term is much greater than the integral of this sine x. Similarly, the integral of 1 is much greater than the integral of cosine x. Therefore, we can just obtain this kind of equation. On top and on the bottom, we have similar integrals of a constant, while the division results in negative 0.28, and then we have this number. Alright, and then the expectation value of the momentum of this system is negative 0.28 kh bar. There's an easy way to do this. Over here, we have a momentum of kh bar. Over here, negative kh bar, right? So we have 36% of kh bar and 64% of negative kh bar. So we have 0.36 minus 0.64. We get this anyway in the end. Another thing I want to emphasize: how do we integrate this from negative infinity to positive infinity? Actually, we do not do that directly. We replace each infinity with, for example, L as the limit from negative L to positive L, and then on top you have negative 0.28 times 2L. On the bottom you have 1 times 2L, and then 2L and 2L cancel because it appears on the top and the bottom, and then we have this. So this is simply a mathematical trick to evaluate this kind of integrals. Chapter 14, Quantum Mechanical Postulates. Section 14.5, Quantum Mechanical Postulate 5. Postulate 5 states that the wave function of a system evolves over time as dictated by the time-dependent Schrodinger equation. H psi equals IH bar delta psi over delta t. H is the Hamiltonian operator. It's the sum of the kinetic energy operator and potential energy operator. Therefore, the physical meaning of H is the total energy of the system. Psi is the wave function. I is the square root of -1. H bar is the reduced Planck constant. H bar equals h over 2 pi. Delta psi over delta t is the first derivative of the wave function psi with respect to time. H bar is roughly 10 to the power of -34 joule second. For a one-dimensional particle, we can write psi as a function of x and t. X is the position, t denotes time. And then the Hamiltonian is simply the kinetic energy in the x direction plus the potential energy as a function of position and time. Again, negative h bar squared over 2m times the second derivative energy operator. Second derivative operator is the kinetic energy operator. And V is the potential energy operator. And H is the total energy operator. So we're going to write out this time-dependent Schrödinger equation right here. H psi is IH bar delta psi over delta t. And H is the kinetic energy operator plus the potential energy operator. We can apply the kinetic energy operator to psi, we get this. We'll apply the potential energy operator to psi, we get this. And then we have a time-dependent Schrödinger equation for a one-dimensional particle. There are two variables, position x, time t. Again, for a one-dimensional particle, its wave function is a function of two variables, the position of the particle x and time t. Now we write out the time-dependent Schrödinger equation. We'll apply the kinetic energy operator to psi. We apply the potential energy operator to psi. This is simply the product of the potential energy function and the wave function. Well, on the left-hand side, we have h psi, the Hamiltonian operator being applied to psi. On the right-hand side, we have IH bar times delta psi over delta t. This psi is a function of x and t. Now let's simplify this. This is for time-dependent Schrödinger equation. But what if this term, this potential energy, does not change with time? It's possible for a system to have a potential energy that never changes with time. In that case, V of x and t is simply V of x if this V does not change with time. And then we can separate the spatial coordinate x from the temporal coordinate x as follows. We will make a guess of the form of the wave function psi. We're going to take a guess. We say, well, this psi of x and t might be written as the product of a function of x and a function of t. So we have the lowercase psi of x and f of t, where f of t is a exponential function, e to the power of negative I et over h bar. E is the energy of the system, t is time, h bar is the reduced constant. Now let's verify this. If our guess makes sense, we need to apply this IH bar delta over delta t to psi. So it's this side. Now we express the uppercase psi as the product of the lowercase psi of variable x and then a function of t. So we're going to do this, and then we're trying to take the first derivative of psi of x and f of t. So over here, and just because psi of x is independent of time, we can take this out of this derivative operation. So we have IH bar psi of x and then delta over delta t operator being applied to this f of t. F of t is e to the power of negative I et over h bar. It's easy to take the derivative of an exponential function. We just copy the exponential coefficients here, and that's it. and over here we have this exponential function. And now let's simplify this expression. We have I multiplied by negative I, that's just 1. We have h bar cancels h bar, and then in the end we have e. So from here, e times this lowercase psi times f. This f of t is this exponential function. Alright, so this equation, the time dependent Schrodinger equation, now becomes this. On the left hand side we have the kinetic energy being applied to the uppercase psi, this potential energy multiplied by uppercase psi. On the right hand side we have this. We have IH bar delta uppercase psi over delta t, which is the energy of the system, times the lowercase psi of x only and a function of t. So right here, left equals right. And if we look at this carefully, we notice that we have f of t, f of t, f of t. We're gonna just cancel all those. We get this equation. In this equation, there's no longer time. There's only one variable x, the spatial coordinate of this wave function. We have the kinetic energy operator being applied to the lowercase psi, potential energy operator being applied to psi, and the sum is equal to E multiplied by psi. And over here, this also makes sense. Really, it's just the Hamiltonian being applied to psi is equal to E psi. And the physical meaning of the Hamiltonian is the total energy. And this equation does not contain the temporal coordinate t, the temporal variable t. There's no time in this equation, and therefore we call this equation the time independent equation. It's a time independent Schrodinger equation. For a one-dimensional particle, when the potential energy operator is independent of time, somehow we can separate the time variable from the spatial variable. We get this time independent Schrodinger equation. This can be simplified as h psi equals E psi. On the right hand side, this is just E psi. Psi is a function of x. On the left hand side, we have the kinetic energy operator applied to psi and potential energy operator applied to psi. The sum of kinetic energy and potential energy operators is simply the Hamiltonian h. And over here, this h does not contain time either. So h here is a time independent Hamiltonian. H is the sum of kinetic energy and potential energy. Kinetic energy operator here, potential energy operator here. And this lowercase psi is an eigenfunction of the Hamiltonian. E is the corresponding eigenvalue. The physical meaning of H again is the total energy of the one-dimensional system. Because in this H we do not see the temporal variable t. That means this H does not depend on t. That means H is independent of time, and therefore the total energy of the system is also independent of time. The energy remains constant. For a two-dimensional system, the kinetic energy operator is a little bit more complicated. There are two terms, one for the x dimension, one for the y dimension. And the second derivative is simply the first derivative and then the first derivative, just twice. You apply the first derivative twice, and when you do that, you need to hold y constant. When you take the second derivative of psi with respect to y, you need to make sure x is held constant when you do the derivation. And again, the second derivative is simply the first derivative of the first derivative. For a two-dimensional system, the time-independent potential energy operator is denoted by V of x and y. Sometimes we put a caret on top to indicate it's an operator, but usually for potential energy, the operation is simply multiplication. So occasionally we just do not put the caret on top just for simplicity. For a three-dimensional particle, we have x, y, and z, and then time. But then the time-dependent Schrodinger equation can be really complex, because if you look at the kinetic energy operator, we have three different derivatives with respect to x, y, and z. And over here we have a potential energy that depends on x, y, z, and time. And over here, this is simpler. It's still IH bar delta psi over delta t. Again, this psi is a function of x, y, z, and time. But again, if the potential energy V does not change over time, things get simpler. This V now becomes a function of only the spatial coordinates x, y, and z. It does not depend on time. Now we separate the spatial coordinates from time. So we can write out this uppercase psi as the product of two functions. One is the function of x, y, and z. The other is a function of time. The function of time has to be e to the power of negative I e t over h bar for convenience. Now let's evaluate delta psi over delta t. We'll evaluate this because the lowercase psi is independent of time. We can take it out. And now, how do we take the first derivative of exponential function? It's easy. It's negative IE over h bar multiplied by this exponential function. We clean up everything, we get this. It's negative IE over h bar multiplied by the uppercase psi. And therefore, the time-dependent Schrodinger equation becomes this. On the left-hand side, we have the kinetic energy operator being applied to this psi times f. This psi is a function of x, y, and z. F is a function of t. Similarly, we have the potential energy, which does not depend on time, multiplied by psi of x, y, z, multiplied by a function of t. On the right-hand side, we have just the total energy multiplied by the wave function of the system. Now, both sides divided by the function of t. ft, 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 they all cancel. Now we have this. We have the kinetic energy operator being applied to the lowercase psi plus v times the lowercase psi equals e times the lowercase psi. Simply put, we have h psi equals e psi. This is the so-called time-independent Schrodinger equation, and this h is time-independent Hamiltonian operator. This h is the sum of the kinetic energy operator plus the potential energy operator. If we have multiple particles, the wave function psi now becomes a function of the positions of all particles and also time. So we have 3m plus 1 variables. H is, well, the kinetic energy operator plus the potential energy operator. The kinetic energy operator is the sum of all kinetic energy operators of all particles. And now we have this time-dependent Schrodinger equation. H psi equals IH bar delta psi over delta t. Again, if the potential energy does not change over time, this V is dependent on the positions of the particles only, then we can get the time-independent Schrodinger equation. H psi equals E psi. Over here, we use the lowercase psi as a function of the positions only. And this H becomes a time-independent Hamiltonian. This H can be expressed as the sum of the kinetic energy operator and the potential energy operator. We do not see any operator that contains time t. Therefore, H is independent of t. And because of that, when we see H psi equals E psi and H does not depend on t, then E does not depend on t. Now, this lowercase psi is a function of the positions of all particles. It's a time-independent wave function. If the potential energy V does change over time, we can express psi as the sum of Ci psi I. It gets a little complicated. Ci is a coefficient of psi I, but this coefficient may change with time. That means the probability associated with psi sub I may change with time. That corresponds to the change of the, for example, electronic structure in an atom or in a molecule. If we're using this to describe the electrons in a atom or molecule, again, psi sub I is the eigenfunction, the ith eigenfunction of a complete basis set. So what does this mean, a complete basis set? Well, that's just simply the eigenfunctions of this H over here. So if we can solve this time-independent Schrodinger equation, we can get a bunch of eigenfunctions, usually an infinite number of eigenfunctions. And the infinite number of eigenfunctions can form a complete basis set. That means any smooth function can be expressed as a linear combination of the eigenfunctions from this complete basis set. And then we can actually solve this time-dependent Schrodinger equation, h psi equals I h bar delta psi over delta t. And solving this is equivalent to finding how the coefficients C sub I changes with time. So over here we have C sub I here. We're going to just see how the probability of a system in the ith eigenstate changes with time. Chapter 14, Quantum Mechanical Postulates. Section 14.6, Quantum Mechanical Postulate 6. Postulate 6 states that the wave function of a multi-electron system must change sign under the exchange of two electrons. The wave functions of electrons must be antisymmetric with respect to the exchange of the coordinates of any two electrons. Over here, we just label them 1 and 2. And the mathematical expression is this: psi of R1, R2 and time equals negative psi R2, R1 and time. Note I just exchanged electrons 1 and electron 2 here. Antisymmetric means changing the sign, and over here the coordinates include the spatial coordinates and also the spin coordinates of the electron. For a time-independent system that consists of two electrons, 1 and 2, we have a simpler mathematical expression. We do not have the time variable t, so the lowercase psi of R1 and R2 equals negative psi of R2, R1. The Pauli exclusion principle is the direct result of postulate 6. No two electrons may occupy the same spatial orbital and have the same spin, because if they did, since electrons are indistinguishable, we would have psi of R1, R2 equals psi of R2, R1. But from postulate 6, we have psi of R1, R2 equals negative psi of R2, R1. So if you compare these two equations, the left side equals this left side, the right side here equals this right side, and therefore psi of R2, R1 equals negative psi R2, R1. Well, if you look at this, psi is negative psi. What does that mean? The only possible solution of this equation is this: psi of R2, R1 is 0, and also psi of R1, R2 is also 0. We just essentially have 0 equals 0, 0 equals negative 0. And then we have the probability density equal to 0. This is because if psi is 0, the squared modulus of psi is 0. And the squared modulus of psi is the probability density. So that means the probability is 0 for finding two electrons with the same spin occupying the same orbital. and that's called the Pauli exclusion principle. No two electrons may have the same set of quantum numbers, or in general, no two electrons have the same quantum state. Chapter 15, Quantum Translation, Section 15.1, the free particle. The time-dependent Schrödinger equation is each psi equals IH bar delta psi over delta t. The wave function of a one-dimensional particle is a function of two variables, the position x and time t. The time-dependent Schrödinger equation of a one particle is therefore each psi of x and t equals IH bar delta psi over delta t. Again, this psi is a function of the position x and time t. But if the potential energy V of the 1D particle never changes over time, we have Vx as the potential energy. Since the Hamiltonian operator is the sum of the kinetic energy operator and the potential energy operator, we have this equation as the time-dependent Schrödinger equation. On the right-hand side, we have IH bar delta psi over delta t. On the left-hand side, we have simply the kinetic energy operator applied to psi plus potential energy operator applied to psi. The wave function of the particle depends on its position and time, but we can separate the two variables by setting psi to be a lowercase psi of x only and a function of time, and this will simplify the time-dependent Schrödinger equation. So mostly we replace this uppercase psi with the product of the lowercase psi and a function of time here and here and finally here. Because the function of time does not depend on x and the function of x does not depend on time, we can simplify this equation. So over here we can take this function of time out of the second derivative, and over here we can take this function of x out of the first derivative with respect to time. So this lowercase psi of x is considered a constant with respect to time. It does not depend on time. Now the separation of the variables leads to this time-dependent Schrödinger equation. The separation is done this way. We assume the uppercase psi, the wave function of x and t, can be expressed as the product of the lowercase psi of x only times the function the lowercase psi of x only multiplied by a function of time. So now we have this time-dependent Schrödinger equation. We can now divide both sides by psi of x and f of t. Now we have this equation. So on the left hand side we have negative h bar squared over 2m psi delta squared psi over delta x squared plus vx. On the right hand side we have IH bar and then 1 over f times delta f over delta t. And why do we do this? When we do this, we can see on the left hand side of the equation we have a function of x and x only. This part does not depend on time. And on the right side, we see a function of time which does not depend on x. If the left part does not depend on t, the right side does not depend on x, and we have equal sign between. That means both the left side and the right side are independent of x and t. Alright, that means we can say the left equals the right equals a constant. So now we're going to use a symbol E, a letter E, to denote that constant, because later you will see that constant has a physical meaning, which is the energy of the system, and therefore we use this letter E to denote that constant. Again, the left side does not depend on t, the right side does not depend on x, and they are equal. Therefore, both sides are independent of t and x. Alright, now we're going to just say, well, the left side equals the right side equals E, and E has a physical meaning. It's the total energy of the system. And now we have actually two differential equations. This function of x is equal to E, and this function of t is equal to E. So we write out these two equations here and here. Given this equation, we can move around the variables so that df over f is equal to negative IE over h bar. So you just move this IH bar to the right hand side, you move the delta t to the right hand side, and then we have this equation. Again, df over f is negative IE over h bar times dt. This is a simple differential equation. To solve this equation, we just need to integrate both sides. We get the logarithm of f is equal to negative IE over h bar times t, and therefore this f function is e to the power of negative IET over h bar. It's an exponential function of time. In this case, the probability distribution of the particle is independent of time, because the probability density is this psi times f squared, and we can separate this two. It's psi squared and f squared. Now let's look at this f squared. It's really the squared modulus of f, which is the complex conjugate of f times f. Over here we have f, and then what is its complex conjugate? We just need to replace I with negative I. Now we have the complex conjugate here. We do the multiplication, we get 1. That means the squared modulus of f is always 1. This part is always 1. The probability density of the particle never depends on time. It never changes with time. So now we have this time independent equation for the 1D particle over here. And both sides multiplied by the psi of x. This time independent Schrödinger equation becomes over here the kinetic energy operator negative h bar squared over 2m d2 d squared over dx squared applied to psi plus the potential energy applied to psi is equal to E psi. The simplified form of the time independent Schrödinger equation for the 1D particle is simply h psi equals E psi. Psi is a function of x. H is the kinetic energy operator plus the potential energy operator. E is the total energy of the system. Psi of x is the time independent wave function of the particle. The squared modulus of psi is the probability density of the particle at position x. The potential energy of a free particle is always 0. So in this case, for a free particle, V is always 0. Therefore, we have the kinetic energy operator applied to psi equals E psi. And then we can move around those parameters. Then the second derivative of psi is equal to a constant times psi. That constant is negative 2me over h bar squared. We can simplify this expression by defining k to be the square root of 2me over h bar squared, or the square root of 2me over h bar. This k is a constant because E, the energy of the system, is a constant for the time independent Schrödinger equation. The mass is of course a constant. And then this is also the magnitude of the momentum, because in this case for a free particle its total energy is the kinetic energy. So the square root of 2me is the square root of 2m times the kinetic energy, which is half mv squared. We do some evaluation here, we get mv, which is just the magnitude of the momentum. Therefore kh bar is the magnitude of this momentum. So you can see over here, this is K is the magnitude of the momentum over h bar, and the momentum is K times h bar. Now we have this equation, which is simpler. The second derivative of psi is equal to psi multiplied by negative K squared. There are two possible solutions for this kind of differential equation. Again, the second derivative of psi is psi multiplied by a constant, negative K squared. And we have two solutions, e to the power of plus ikx and e to the power of negative ikx. We can easily verify that these two solutions satisfy this differential equation. We can take the second derivative of e to the power of plus ikx. We will get plus ik times this exponential function. And of course, plus ik times plus ik is negative k squared. We can also take the second derivative of e to the power of negative ikx. We'll get negative ik times this e to the power of negative ikx. And of course, negative ik times negative ik is also negative k squared. So we just verified that the psi plus and psi minus are both legitimate solutions to this differential equation. However, there are actually an infinite number of solutions. The general solution for a free particle is a linear combination of psi plus and psi minus. It can be expressed as a coefficient times e to the power of plus ikx plus a coefficient times e to the power of negative ikx. We use a sub plus and a sub minus to denote those coefficients. They can be any constant. They can be complex numbers. In general, if two functions f and g are both eigenfunctions of the same operator O with the same eigenvalue, then the linear combination of these two functions, that means a coefficient times f plus a coefficient times g, is also an eigenfunction of that operator, and a and b can be any constant. So over here we provide a linear combination of two eigenfunctions for the same operator, and they have the same eigenvalue. Then af plus bg is also an eigenfunction of this operator, also with the same eigenvalue. So specifically, since this is an eigenfunction of the Hamiltonian, this is also an eigenfunction of the same Hamiltonian, and these two have the same eigenvalues, negative k squared, and therefore the linear combination of these two exponential functions is also an eigenfunction of the same Hamiltonian with the same eigenvalue, negative k squared. The general solution for a free particle is the linear combination of psi plus and psi minus. Psi plus is e to the power of plus ikx, psi minus is e to the power of negative ikx. In front of the exponential functions, we have coefficients. These two coefficients can take any values. They are just arbitrarily constant. Now let's verify it. We'll take the second derivative of this general solution. So over here, the second derivative of this part plus the second derivative of this part. Over here, we just copy this function over here, and then since we're taking the derivatives of an exponential function over here, we need to copy this exponential coefficient twice, plus ik here and plus ik again. Over here, same, negative ik and negative ik, so 2 times. Positive ik squared is negative k squared. Negative ik squared is also negative k squared. So overall, we have just negative k squared times psi. Psi is the linear combination of these two. And now we just proved that h being applied to psi is equal to, well, negative h bar squared over 2m times the second derivative of psi, which is negative k squared psi. Now this is simple multiplication. We have k squared h bar squared over 2m times psi on the right side of the equation. Again, h psi equals e psi, and over here k squared h bar squared over 2m is the energy of the system. So we have just verified the linear combination of e to the power of plus ikx and e to the power of negative ikx is also an eigenfunction of the Hamiltonian operator for the one-dimensional free particle, regardless of the values of a sub plus and a sub minus. And the eigenvalue over here, k squared h bar squared over 2m, is both the total energy of the system and also the kinetic energy of the system. Because the system is a free particle has a zero potential energy. We can also determine the momentum for e to the power of ikx and e to the power of negative ikx. We just need to apply the momentum operator to these eigenfunctions, and over here, when we apply the momentum operator to e to the power of ikx, we get this wave function multiplied by kh bar. Therefore, the momentum for this eigenfunction is kh bar. We apply the momentum operator to e to the power of negative ikx, we get negative kh bar times this exponential function. The eigenvalue is negative kh bar. That indicates the system with this wave function has a momentum of negative kh bar. But now if we have a general solution over here as a linear combination of e to the power of positive ikx and e to the power of negative ikx, that means this particle has a momentum of kh bar and negative kh bar at the same time. This free particle can be moving forward and backward at the same time. Chapter 15, Quantum Translation. Section 15.2, the particle in the one-dimensional box. The potential energy of the particle is zero inside the one-dimensional box, between 0 and A. The potential energy is infinity outside the box. We have two equations. V is 0 inside the box. V is infinity outside the box when x is less than 0 or greater than A. The Schrödinger equation for the particle inside the box is the same as the equation for a free particle because V is 0 inside the box. Therefore, the Schrödinger equation is negative h bar squared over 2m d squared psi over dx squared is equal to E psi. On the left hand side, we have the kinetic energy operator applied to psi. On the right hand side, we have E psi. The potential energy is 0 inside the box between 0 and A. In section 1, we have learned the general solution of a free particle is this: a linear combination of e to the power of plus ikx and e to the power of negative ikx. A sub plus and a sub minus are just arbitrary constants. Again, we have this solution if x is between 0 and A. That means when the particle is inside the box. This solution is the legitimate solution for a free particle inside the box. The particle can never escape out of the box because of the infinite energy barrier at x equals 0 and x equals A. Therefore, this particle is completely confined. And just because the wave function has to be continuous, well, we know the wave function has to be 0 when x is less than 0. The wave function has to be 0 when x is greater than A. And now we know even at the two boundaries, when x is 0, the wave function must also be 0, just to make sure this wave function is continuous at this point. And the wave function is also 0 when x equals A, because when x is greater than A, well, the wave function must be 0. Therefore, to ensure the wave function is continuous, its value must be 0 when x is 0 or A. Inside the box, the free particle has a wave function like this: a linear combination of e to the power of plus ikx and e to the power of negative ikx. A sub plus and a sub minus are simply arbitrary constants. Outside the box, the wave function equals 0 when x is less than 0 or when x is greater than A. And now, to ensure the wave function is single valued and continuous, we have to have these two conditions. Psi of 0 must be 0. Psi of A must also be 0. That means at the two boundaries of the box, the wave function must be equal to 0. These two equations describe the values of the wave function at the two boundaries, and therefore they are called the boundary conditions. We have two boundary conditions, one at 0, the other at A. We will prove the energy of the particle must be quantized to satisfy these two boundary conditions. Now let's look at these boundary conditions. The first one is this: when x is 0, the wave function must be 0. So we just plug in the value of x into the general solution of the wave function. We have this: e to the power of plus ikx, e to the power of negative ikx now become e to the power of plus ik0 and e to the power of negative ik0. So the sum of these two terms should be 0, and because this is simply 1, this is also simply 1, we learn that to satisfy the first boundary condition, a sub plus plus a sub minus should be 0. These two are opposite to each other. Therefore, we can rewrite the wave function here. It's a plus times e to the power of positive ikx minus a plus times e to the power of negative ikx. Now we can see there's a common factor, a plus, so we have this a plus here, and then we have e to the power of ikx minus e to the power of negative ikx. The reason we put 2i here and divided the difference by 2i here is because all this in this pair of parentheses is sine kx. Again, it's just because e to the power of I theta is cosine theta plus I times sine theta. E to the power of negative I theta is cosine theta minus I times sine theta. So sine theta can be expressed as e to the power of I theta minus e to the power of negative I theta over 2i. So I'm just replacing theta with kx. So we have this equation. Again, a plus is simply an arbitrary constant. So we can simply set a to be 2 times I 2 times a plus. To simplify this expression, we have psi of x, the wave function of the particle in the box, to be a times sine kx. It just looks simpler, and a is also an arbitrary constant. Now let's look at the second boundary condition. Psi of a is 0. That means, well, a times sine ka should be 0. So now we have a product here. A times the sine function is 0. So can a be 0? Well, a cannot be 0, because if a is 0, the wave function must be 0. And if the wave function must be 0 inside the box, there's no particle in the first place. So a cannot be 0. Alright, then sine ka has to be 0. Now let's examine this. Sine ka is 0. What kind of values can this ka have? We need to review sine functions. We know sine 0 is 0, sine pi is 0, sine 2 pi is 0, sine 3 pi is 0, sine negative 5 pi is also 0. So there are an infinite number of solutions to this equation. As long as ka is equal to n pi, we satisfy this equation, and n has to be an integer. Again, sine n pi is always 0 as long as n is an integer. So we have ka equals n pi. It seems k has to be quantized. K has to be a integer multiple of pi over a. Now to satisfy the two boundary conditions, we have psi equals a times sine kx inside the box. And also, k times a should be n pi, and n must be an integer in this equation. Therefore, the wave function of the particle in the box should be a times n pi x over a. Well, n pi over a is k. So over here, you see ka is n pi. So k is n pi over a. Sine kx is sine n pi x over a. There are a couple caveats with the value of n. So first, n can never be 0, because if n is 0, we're looking at sine 0 inside the box. and psi is then 0. That means the particle disappears. There's a 0 probability of finding the particle inside the box. So number 2, n can be positive or negative because they are identical in describing the probability distribution of the particle, because in the end we need to take the squared modulus of psi to get the probability density. So whether it's plus or minus, when we take the squared modulus of psi, it's going to be the same. For convenience, we'll just assume n is a positive integer. Alright, therefore n has to be 1, 2, 3, 4, 5, etc. Again, the wave function of the particle in the box is a times sine n pi x over a. N has to be a positive integer, 1, 2, 3, 4, inside the box. And outside the box, the wave function is 0 due to the infinite energy barrier. Now, the first 4 wave functions are showing in this figure. The mathematical expressions are here. Let's look at the math functions. When a equals 1, the wave function is a times sine pi x over a. When a is 2, it's sine 2 pi x over a. When a is 3, we have sine 3 pi x over a, and then we have 4 pi x over a. Now let's examine sine pi x over a. So we have this x from 0 to a, and therefore we plug in the lower limit and upper limit for x, and pi x over a is going to be between 0 and pi. Really, we're just plotting sine theta from sine 0 to sine pi. Alright, so this is sine 0, this is sine pi. In the middle, we have sine pi over 2. Of course, there's a normalization factor, but this is trivial. We don't worry too much about this. Let's just look at the sine functions. Now let's look at this sine function, sine 2 pi x over a. Again, x is from 0 to a. Plug in the value. When x is 0, this whole thing is 0. When x is a, this whole thing is 2 pi. So we have one entire period from 0 to 2 pi. So over here, this is the entire wave. This is sine 0, and this is sine pi, and this is sine 2 pi. And in between, we have sine pi over 2. Over here, we have sine 3 pi over 2, which is negative 1. So we have this kind of shape. Now we have sine 3 pi x over a. X is from 0 to a. So really, we're looking at a sine function from 0 to 3 pi. Alright, so sine 0, sine pi, sine 2 pi, sine 3 pi. And then in the middle, we have sine 0.5 pi, sine 1.5 pi, sine 2.5 pi over there. And now we have sine 4 pi x over a with this kind of shape. Over here, x is between 0 and a. So 4 pi x over a is between 0 and 4 pi. So really, we're talking about sine 0, sine pi, sine 2 pi, sine 3 pi, sine 4 pi. And then in the middle, we have pi over 2, we have 3 pi over 2, 5 pi over 2, and 7 pi over 2. So that's why we got this kind of shapes. Again, over here, we have only 1/2 of the wavelengths. Over here, when a equals 2, we have an entire wave. And over here, we have 1.5 of the wavelengths. And over here, when a equals 2, we have 2 wavelengths. The wave function of the particle in the box can be written as a times sine n pi x over a. N is a positive integer, 1, 2, 3, 4. Because remember, n cannot be 0. When n is 0, you simply have sine 0 inside the box. That means psi is always 0 inside the box. There's no particle. Outside the box, of course, psi is 0 due to the infinite energy barrier. Now the 4 wave functions are shown in this figure. When n is 1, 2, 3, 4, let's look at the number of nodes inside the box. Over here, we do not see any nodes, but over here, we have over here there's a node. This corresponds to sine pi. We have a node. And now over here, we have 2 nodes. This is sine pi, this is sine 2 pi. And now 3 nodes, sine pi, sine 2 pi, sine 3 pi, 3 nodes. So you can see as the value of n increases, the number of nodes increases. And actually, the number of nodes is simply n minus 1. Actually, we have a similar example in general chemistry. When we look at atomic orbitals, well, the number of nodes is also n minus 1. But in general chemistry, we use n as the principal quantum number for the atomic orbitals. Over here, n is the quantum number for the particle in the box. but still the number of nodes is just n minus 1. As the number of nodes increases, the energy increases. The same statement is true for atomic orbitals. Now let's look at all those expressions. Those are the first 4 eigenfunctions for the particle in the box. The first one does not have any node inside the box, and this one has a node when x is a over 2. When x is a over 2, 2 pi x over a is pi, so sine pi is 0. Now this wave function has 2 nodes, because if you plug in a over 3 or 2a over 3 here, you get sine pi and sine 2 pi. This function has 3 nodes, because when you plug in a over 4, 2a over 4, and 3a over 4 into this function, we get sine pi, sine 2 pi, and sine 3 pi. So we have 3 nodes when a equals 4. And also, we can look at the graph. No nodes, 1 node, 2 nodes, 1, 2, 3. 3 nodes inside the box. Do not count the boundaries as nodes, okay? We're counting the number of nodes inside the box. Now we can normalize the wave function psi. So that means we can determine the value of a, although it's not very important. We can determine the value of a so that this psi is normalized. That means the total probability of finding such particle between 0 and a should be 100%. Again, the particle cannot escape out of the box. Therefore, the probability of finding this particle between 0 and a is always 100%. That means we have this equation. The integral of the squared modulus of psi times dx is just 1. The squared modulus of psi is the probability density. We are integrating the probability density here. It should be 1 between 0 and a. And this psi is sine n pi x over a, so I'm using the sine function over here. You need to be familiar with trigonometric functions. Sine theta is 1 minus cosine 2 theta and then divided by 2. That's what I'm doing here. You can prove this yourself. And then we can separate this 2. We got 1/2 in this integral. Over here we have 1/2 of this cosine function. And look, there's 2 here. Again, it's because sine theta squared. Alright, if you square a sine theta, it's equal to 1 minus cosine 2 theta divided by 2. Alright. It's just trigonometry. Over here, we can easily integrate this. This is just 1/2 of a. This one a little tricky, but still we can do variable substitution. We can multiply this x by 2n pi over a, and over here we have this divided by 2n pi over a. And we can set phi to be 2n pi x over a. This is just standard variable substitution in integral calculus. And then we have this integral of cosine phi. That's really easy to integrate. We also need to take care of the lower limit and upper limit. So x has a lower limit of 0, upper limit of a, and phi is 2n pi x over a. So we need to plug in the lower limit and upper limit of x in here, so that we see the lower limit of phi is also 0, but the upper limit of phi is 2n pi, because when you put x equals a in here, a and a cancel, the upper limit of phi is 2n pi. So we need to integrate cosine phi from 0 to 2n pi. The integral of this is sine phi. Well, sine 2n pi is 0, sine 0 is 0, so this term is going to be just 0. We have a squared times the length of the box over 2. That should be 1. And therefore, the normalization factor a is the square root of 2 over the box length. The normalization function is this: the square root of 2 over the box length times sine n pi x over a. And x is between 0 and a. Again, the normalized wave function of the particle in the box is the square root of 2 over a times sine n pi x over a. This lowercase a is the side length of the box, or the dimension of the box. N is 1, 2, 3, 4, etc. We can apply the kinetic energy operator to this wave function. Let's do it. Okay, the kinetic energy operator is negative h bar squared over 2m d squared over dx squared. We apply this to this wave function over here. It's slightly complicated because you're taking the second derivative. But if you know the first derivative of sine theta is cosine theta, and the first derivative of cosine theta is negative sine theta, you mostly can solve this problem easily. There's also a chain rule, because when you take the derivatives, you need to copy this n pi over a in front of the derivatives twice, because we're doing the second derivative. That's why you have this n pi over a 2 times or squared in front of this negative sign n pi x over a. We can clean up everything. We see this is simply the wave function of the particle, and over here we have h bar squared n squared pi squared 2ma squared. Sounds complicated, but h bar is simply h over 2 pi. So somehow h bar times pi is just h over 2. Over here, h bar squared times pi squared is simply h squared over 4. And therefore, we can clean it up. We get this as the kinetic energy, n squared h squared over 8ma squared. So I'm just using the boson to emphasize this. We apply the kinetic energy to the wave function. We get the wave function multiplied by a constant, n squared h squared over 8ma squared. And this is the eigenvalue of psi. When we apply the kinetic energy operator to it, therefore the physical meaning of n squared h squared over 8ma squared is the kinetic energy of the particle. Well, it's also the total energy of this free particle, because the potential energy of a free particle is just 0. Therefore, the energy of a particle inside a one-dimensional box is quantized. The expression is n squared h squared over 8ma squared, and has to be a positive integer, 1, 2, 3, 4, etc. The smallest possible energy of the particle is h squared over 8ma squared when n is 1. Because this is the lowest possible energy, we call that 0 point translational energy. It's just the naming. The lowest possible energy is the 0 point energy. Alright, the second and third lowest energies are 4h squared over 8ma squared and 9h squared over 8ma squared. You simply have n equals 2 in this case, n equals 3 in this case. Now, given the kinetic energy of the particle, we can easily compute its momentum, because the magnitude of the momentum is just mv, and mv is the square root of m squared v squared, which is the square root of 2m times the kinetic energy. So you can see this is equal to this. 2m times the kinetic energy is over here. We know the kinetic energy is n squared h squared over 8ma squared. We plug in everything. We clean up this m and m cancel. 2 over 8 is a quarter, and we take the square root. Now we have the magnitude of the momentum of the particle. It happens to be nh over 2a, very simple expression. And the momentum has to be quantized as well. It has to be a integer multiple of h over 2a. The magnitude of the momentum of the particle can also be determined using the famous de Broglie equation. The momentum is h over lambda. And now we have the lambda. We can see over here, this is 1/2 of lambda, this is 1 lambda. Over here, this way, we see 1.5 lambda, and over here we see 2 lambda. From here to the middle, we have 1 lambda, and from the middle point to the right side, we have another lambda. So it's pretty simple. If you know the wavelength of the wave, the wavelength of this function, the square root of 2 over a sine n pi x over a, is actually 2a over n. So over here, n is 1, so the wavelength is 2a. Well, that makes sense, because we're seeing only 1/2 of the wave, which has a length of a. If the 1/2 of the wave is a, then the entire wave is 2a. Over here, this is just the wavelength. When equals to 2a over 2 is a, so this is just the wavelength. The box length is the wavelength. Over here, we're seeing this box length is equal to 1.5 wavelengths. Therefore, the wavelength is 2/3 of a. Over here, we're looking at 2 wavelengths. 2 wavelengths equals a, and therefore, well, the wavelength is 2a over 4, which is A over 2. So this is one wavelength, A over 2. This is another wavelength, A over 2. So once we have the expression for the wavelengths, we use this de Broglie equation or de Broglie relation to compute the momentum. H over lambda is simply H over 2A over N, and then it's just NH over 2A. So look, when we use de Broglie relation, we have NH over 2A as the momentum. Or we can use this equation, we get NH over 2A. So at least the results are consistent. Larger quantum numbers always means more nodes, shorter wavelengths, higher energy, and therefore higher speed of the particle in the box. So again, from n equals 1, 2, 3, 4, the energy goes up, the momentum goes up, the speed goes up, and also the wavelengths get shorter, and we have more and more nodes from 1 to 4. Over here, no nodes, 1 node, 2 nodes, 3 nodes. Again, the wave function of the particle in the one-dimensional box is this: the square root of 2 over a times the sine function of n pi x over a. The number of nodes of the wave function is n minus 1. So we can see when a is 1, we have 0 nodes. When a equals 2, we have 1 node. The first 4 wave functions again have 0, 1, 2, 3 nodes. When n is 1, 2, 3, 4. Alright, in general, energy increases as the number of nodes increases. A similar example is the atomic orbitals of the hydrogen atom. We learned this in general chemistry. When the principal quantum number A increases, the number of nodes increases, and also it's n minus 1. The atomic orbital energy also increases. The 1s orbital of hydrogen atom has 0 nodes, and the 2s2p orbitals, A equals 2, well, they have 1 node. 3s, 3p, 3d, they have 2 nodes. 4s, 4p, 4d, 4f, well, they have 3 nodes. Again, the number of nodes is just n minus 1. You can say this for the particle in the box. You can say this for the atomic orbitals. In general, the energy of the molecular orbitals also increases as the number of nodes increases. For example, the energy of the sigma star orbital with 1 node has higher energy than the sigma orbital with 0 node in the H2 molecule. You can say that for all other molecules. Chapter 15, Quantum Translation, Section 15.3, Heisenberg's Uncertainty Principle. The wave function of the particle in the one-dimensional box is the square root of 2 over a times sine n pi x over a. A is the box length, n is the quantum number. The uncertainty of the position of the particle is approximately 1/2 of the dimension of the box, just because the position is within a range of 1/2 of a plus minus 1/2 of a. So really, this is a range from 0 to a. The uncertainty of the momentum of the particle is n pi over a times h bar, because the momentum of the particle is plus minus n pi over a times h bar. N is the quantum number 1, 2, 3, 4, etc. And therefore, we can have the product of the uncertainty of the position and the uncertainty of the momentum. The product is 1/2 of a times n pi over a times kh bar. And we have n pi h bar over 2, or this, since this n is 1 or 2 or 3 or 4, the minimum value for n is 1. Therefore, the product of the uncertainties is greater than or equal to pi h bar over 2. And therefore, the Heisenberg's uncertainty principle holds, which states that the uncertainty of the position times the uncertainty of the momentum of the same particle must be greater than or equal to 1/2 of h bar, and certainly pi over 2 is greater than 1/2. The uncertainty of the position can also be determined more accurately using this equation for the standard deviation. The standard deviation of x can be computed this way: the square root of the average of x squared minus the squared average. Postulate 4 can be used to calculate the expectation values and also the standard deviation of the physical properties of the particle in the box, such as position. Now, given this wave function, we can compute the average value for x. It's pretty simple. It's the integral of psi star and then x operator applied to psi dx. X is from 0 to a because outside the box the probability is 0. We just need to integrate this. To integrate this, we need to solve this integral, which is non-trivial. So I used Wolfram alpha to integrate this whole thing. I got 1/2 of a as the expectation value for the position of the particle in the box. And also, we can avoid doing any mathematics. We just look at the shape of the wave function. Well, it's fairly symmetrical, and work as, this x would have the average at the midpoint of the box. Now let's look at the average of x squared. So again, we'll just integrate this. We integrate the this is the psi star, the complex conjugate of the wave function, and then the operator is x squared applied to psi. So integrate this. I used Wolfram alpha again. I got a squared over 3. This is really non-trivial calculation. Now, since we have the average of x and the average of x squared, we can calculate the standard deviation. Delta x is the square root of the average of x squared and the average of x and then squared. So we plug in the expressions, we get 0.29a. So this is the standard deviation of the position of the particle in the box. And this value does not depend on the quantum number n. So no matter n is 1 or 2 or 3 or 4, well, the standard deviation of the position is always 0.29a. Postulate 4 can also be used to calculate the expectation value and the standard deviation of the momentum of the particle in the box. So now let's look at the average momentum. We know it should be 0 because if we look at the wave function of the particle in the box, it's either sine n pi x over a or simply sine kx, where k is n pi over a. So either way, the sine function can be expressed as a linear combination of two exponential functions. One is e to the power of ikx with a momentum of kh bar. The other exponential function is e to the power of negative ikx with a negative momentum, which is negative kh bar. So this particle may have a momentum of kh bar or negative kh bar with 50-50 chance. Therefore, we know its average momentum should be 0. But still, let's look at this integral. Again, we integrate this psi star, and we apply the momentum operator to the wave function psi. And now we evaluate this. This is actually pretty easy, only because dx and dx cancel. So really, we have a constant here, and then integral of a sine function multiplied by the differential of the sine function. Well, you can just use some variable substitution. So you can say, well, this sine n pi x over a is z, and then you just integrate z dz, which is going to be just 1/2 z squared. What's the limit of z? Well, you can just plug in 0 here, you get sine 0. You plug in a here, you get sine n pi. So sine 0 is 0. Sine n pi is also 0. So the lower limit and upper limit for z are both 0 if z is defined to be sine n pi x over a. Or you can just do this integral directly. Anyways, sine n pi a over a is 0. Sine n pi 0 over a is also 0. So this average of momentum of the particle in the box must be 0. Again, over here, this is just the trick to express a sine function as a linear combination of two exponential functions here with an equal weight. Alright, because the coefficients squared is proportional to the probability. So you have 1 squared versus negative 1 squared, they are the same. And their eigenvalues are kh bar and negative kh bar. Well, k is n pi over a. The probabilities are equal, so you have 50% chance to get n pi h bar over a, 50% chance to get negative n pi h bar over a. So the average has to be 0. Positive 4 can also be used to compute the expectation value of the momentum squared of the particle in the box. Really, it's just the integral. This is psi star, the complex conjugate of the wave function. Here we have the operator, which is px squared, applied to the wave function. And we can simply do some mathematics. We evaluate this first. We apply px squared to the wave function, which is just the momentum operator applied to the wave function 2 times. And then we get this. Alright, and because this function is a normalized function, so we can simply just evaluate this integral to get the average of px squared. This is actually non-trivial, but I think we learned this. The momentum squared is actually 2 times the mass times the kinetic energy. Alright, and we know the kinetic energy is n squared h squared over 8ma squared. So this comes from the kinetic energy multiplied by 2m. Again, the kinetic energy is n squared h squared over 8m a squared, and then multiplied by 2m, you get this expression. Or you can do the math. You can use Wolfram alpha, but also if you do know sine theta squared, you see this sine squared. If you know sine theta squared is 1 minus cosine 2 theta, and then divided by 2, you can still solve this integral easily. But anyway, we got this result over here. The standard deviation of the momentum is the square root of the average of momentum squared minus the average of the momentum and then squared. So this is just 0. We just plug in this here, we get nh over 2a. The standard deviation of delta px is nh over 2a. Now let's verify the Heisenberg uncertainty principle. We calculated delta x to be 0.29a. It's independent of the quantum number n. Delta px depends on the quantum number n. So it's nh over 2a. We do the multiplication. We get 0.88 nh. And this is okay. There's a typo over here. This is actually supposed to be h bar. Okay, so what I did is h is h bar times 2 pi. 2 pi over 2 is pi. And then pi times 0.29 is 0.88. So over here, this is actually 0.88 n h bar. and because the minimum value of n is 1, so this is greater than or equal to 0.88 h bar, which is greater than 1/2 h bar, and this delta x times delta px is proven to be greater than 1/2 h bar in accordance to Heisenberg's uncertainty principle. In general, if the operators of two physical properties, let's say A and B, do not commute, then the exact values of A and B could not be determined simultaneously. So first, what does this mean, do not commute? Well, it simply means if we apply AB operator to a function and then apply BA operator to the same function, we get two different results. And that indicates AB is different from BA. Alright, if you are doing just multiplication of two numbers, AB equals BA always. However, if you are applying two operators to the same function, you might get a different result, which depends on the order, alright, of these two. For position and momentum, we can prove that their corresponding quantum mechanical operators do not commute, and therefore the exact values of position and momentum cannot be determined simultaneously. We can define the commutator of two operators to be this: A, B enclosed in a pair of square bracket, and this is defined to be AB minus BA. If the commutator of A and B is non-zero, that means AB is different from BA, then we cannot determine the exact values of A and B simultaneously. But what if the commutator of A and B is 0? Then that means, well, these two operators, A and B, they share one common set of eigenfunctions. And that means the exact values of A and B can be determined simultaneously. For example, the momentum operator over here and the kinetic energy operator over here, they do commute, so it's possible for us to determine the momentum and kinetic energy of the same system. So first, let's look at the commutator of the momentum operator and the kinetic energy operator. This is just notation. We have two operators inside, separated by a comma, enclosed by a pair of square bracket. We're about to apply this to an arbitrary function f. Really, it means, well, we're going to apply these two operators to f in a different order. Over here, kinetic energy operator first. Here, momentum operator first. And then kinetic energy operator. We'll take the difference. So over here, we just evaluate this. It's trivial. The result is I h bar cubed over 2m times the third derivative of f. What about this part? The same thing. Again, negative and negative cancel, and I goes here. H bar squared times h bar. We have h bar cubed. We have 2m on the bottom, 2m on the bottom, and really we're taking the second derivative of the first derivative, well, which is simply the third derivative of f. So we have this two exactly same, and then they cancel, we get 0. The kinetic energy operator and the momentum operator commute. Their commutator is 0. That means, well, they share a common set of eigenfunctions. For example, this function is an eigenfunction of the momentum operator and also the kinetic energy operator. E to the power of negative ikx is also an eigenfunction of the momentum operator and also the kinetic energy operator. Now, it is possible to determine the momentum and kinetic energy of the same system exactly at the same time. For example, when we have a particle with this wave function, Its momentum is exactly kh bar. Its kinetic energy is exactly k squared h bar squared over 2m. The position and momentum operators do not commute. So we can evaluate the commutator of the position operator and the momentum operator. So really, we're just apply these two operators to function f in a different order. Here we apply x to f first, and then we apply momentum operator. On this side, we apply the momentum operator first, and then the position operator. So we have a common factor, negative IH4. I take it here, and then we just need to evaluate d over dx of the product between x and fx. And here it's just minus x multiplied by f prime, the first derivative of f. So we need to use the product rule here. We get f plus x f prime, and then minus x f prime. In the end, we get negative IH bar times f. Again, when I say f prime, that's df over dx. F prime is simply a shorthand notation for the first derivative of f. Now, we can tell when we apply the commutator of the momentum operator and position operator to f, we didn't get 0. We get negative IH bar times fx. Alright, so that simply means the commutator of the momentum and position operators is equivalent to negative IH bar. When you apply this commutator to any function, it's equivalent to multiply this function by negative IH bar. So this commutator is equivalent to this operator. That means multiplied by negative IH bar. Now the physical meaning of the non-zero commutator of the position and momentum is that the position and momentum of a system can never be determined exactly and simultaneously, and that's the Heisenberg's uncertainty principle. We can never determine the position and momentum of the same system simultaneously. The uncertainty of position times the uncertainty of the momentum must be greater than or equal to 1/2 h bar. The Hamiltonian operator and the time operator do not commute either. So this is the commutator, it's non-zero. Now let's verify it. For an arbitrary function psi, we can write out the commutator applied to psi is equal to ht psi minus th psi. We just apply these two operators to psi in a different order. Postulate 5 can be expressed as a mathematical equation, h psi equals ih bar delta psi over delta t. So really this h, this Hamiltonian, is ih bar delta over delta t. And therefore we have this expression converted to this expression. I replaced h with ih bar delta over delta t. And then this t operator is just multiplied by t. So when we do this, we need to use the product rule. The first derivative of t psi is psi plus t times psi prime. Over here we minus t times psi prime. IH bar is a common factor, so it's right here. And then we get IH bar times psi. Obviously, the commutator of the Hamiltonian and the time operator is equivalent to IH bar or multiplied by IH bar, and this is not zero. The physical meaning of this commutator of h and t being non-zero is that the total energy of a system cannot be determined exactly if the measurement is carried out within a finite time period. If you determine the energy within a finite time period, this delta t is finite, and then this delta E is also finite. The shorter the time period of the measurement, the larger the uncertainty of the energy measurement. We have an inequality expression similar to Heisenberg's uncertainty principle. Over here, delta E times delta T is also greater than or equal to 1/2 h bar. Delta T is the time period of the energy measurement. Delta E is the uncertainty of the energy measurement. Chapter 15, Quantum Translation, Section 15.4, the particle in the two-dimensional box. The Schrödinger equation for the particle in a two-dimensional box is this. We have the kinetic energy operator applied to psi equals E psi. The kinetic energy operator includes two parts, the kinetic energy operator in the x direction and that in the y direction. What about the potential energy of the particle? Well, it's 0 inside the box. The potential energy, however, is infinity outside the box. Therefore, the wave function is 0 outside the box because the particle can never escape out of this two-dimensional box. Now let's look at this figure. It shows the shape of a two-dimensional wave function for a particle inside a two-dimensional box. We have x from 0 to 1, y from 0 to 1. And over here, if you just look at the x direction, it goes up and down and up and down. So it's just similar to the wave function in one dimension. If you look at the y direction from 0 to 1, also it goes up, goes down, and up and down. And over here, you can see in the x direction, there are two wavelengths. This is one wavelength, and then you have another wavelength. Same here, one wavelength, two wavelengths. Now let's count the number of nodes over here. There's 1, 2, 3, 3 nodes in this direction. 1, 2, 3, 3 nodes in the y direction. So really, the two-dimensional wave function can be decomposed into two one-dimensional wave functions. One in the x direction, the other in the y direction. And mostly in the x direction, you'll have just the square root of 2 over a times sine n pi x over a. In the y direction, you have the square root of 2 over b times sine n pi y over b, where b is the length in the y direction. The position and momentum of the particle in the x direction are independent of the position and momentum in the y direction. Therefore, the solution to the Schrödinger equation of the two-dimensional particle in the box is this. The wave function of x and y is equal to a function of x times a function of y. The function of x is simply the one-dimensional particle in the box problem. It's the square root of 2 over a sine n pi x over a. In the y direction, it's the square root of 2 over b times sine n pi y over b. But we cannot use n here and also here because it is possible for the quantum numbers in the x and y direction to be different. So I'm using n sub x as the quantum number here, n sub y here. Well, of course, they can be the same as shown in this figure, but they can also be different. For example, n sub x can be 1, and then n sub y is 2. It is entirely possible for the particle to move faster in the y direction than in the x direction. And over here, it's just one example. When n sub x is 4, n sub y is 4, we have this kind of shape. For the particle in the two-dimensional box, we have the wave function of x and y equal to a wave function of x only times a wave function of y only. The x function is the square root of 2 over a sine n pi x over a. the function of y is the square root of 2 over b sine n pi y over b. Again, these two quantum numbers may be different, so we need to use n sub x and n sub y to denote the quantum numbers in these two directions. We can easily compute the second derivative of x divided by x, because the second derivative of sine theta is just negative sine theta. The second derivative of sine k theta is simply negative k squared sine k theta. So we can easily do this derivation. The second derivative of this x over x is this nx pi over a squared, and then we need a negative sign. Same here, the second derivative of the y function over the y function is negative ny pi over b squared. The reason we derive this is because it's more convenient for us to use this kind of equations when we try to determine the kinetic energy of the particle in the two-dimensional box. We apply the kinetic energy operator to the wave function this way, and then we apply this second derivative operator to x times y. We'll apply this second derivative operator also to x and y. But remember, this y is independent of x, this x is independent of y, and therefore we get this expression. It's negative h bar squared over 2m, and then the second derivative of x times the function of y, and also we have x times the second derivative of the y function. So we have this expression, and now we will divide these two terms by xy and then multiply by xy, so we have something like this. Alright, the reason is we're about to use these two equations. Alright, and then from here to here we have negative h bar squared over 2m. Now we have x double prime over x plus y double prime over y. They're provided here and here, and then multiply by psi. Psi is simply the function of x times the function of y. Now we're going to just plug in the expression of x double prime over x here, y double prime over y here, and then we get this expression, and then we have the wave function of x and y here. We can clean this up a little. H bar is h over 2 pi. So h bar times pi is h over 2. So anyway, after we clean up, there are two terms inside this pair of parentheses. We have nx squared h squared over 8m a squared plus ny squared h squared over 8m b squared. So really, this is the kinetic energy of the particle in one dimension. This is also the kinetic energy of a particle in one dimension, but it's just in the y dimension with a box length of b. The energy of this two-dimensional particle is the sum of its energies in the x and y directions. The wave function of this two-dimensional particle is the product of these two wave functions, one of x, the other of y. They both take the form of the wave function of a particle in a one-dimensional box. Again, for the particle in the two-dimensional box, we have the wave function as the product of two 1D functions. This is a 1D function in the x direction. This is 1D function in the y direction. What about the energy? The energy is the sum of the energy in the x direction and the energy in the y direction. When this two-dimensional box is a square, that means A is equal to B. the energy of the particle in the square now becomes nx squared plus ny squared multiplied by h squared over 8ma squared. When we replace this b with a, when we have a square, now we observe energy degeneracy, because when nx and ny are equal to 1 and 2 or 2 and 1, we will get the same amount of energy. Now let's analyze more different cases. When nx is 1 and ny is 1, the energy is 1 squared plus 1 squared times h squared over 8ma squared. So really it's this is the so-called 0-point translation energy for the two-dimensional particle. 0 point means lowest possible in quantum mechanics. Later you will learn the 0-point vibrational energy as well in the future. Now we see when nx is equal to 2, ny is equal to 1, or when nx is 1 and y is 2, the energy is the same, 5h squared over 8ma squared. It's called energy degeneracy. You have two different sets of quantum numbers, 1 and 2 versus 2 and 1. You get the same amount of energy. We say the degeneracy is 2. And this gives you the second lowest possible energy. And again, the degeneracy of this energy level is 2. What if nx is 2 and y is 2? Well, then the total energy is 2 squared plus 2 squared and then h squared over 8ma squared. And this is the third lowest possible energy for the two-dimensional particle inside a square. The degeneracy of this energy level is 1. Now you can predict the next energy level. Alright, starting from 1, 1, and then you have 2, 1, or 1, 2, and then you have 2, 2, and then what's the next one? Well, the next energy level is gonna be 1, 3, or 3, 1. So you have 3 squared plus 1 squared, or 1 squared plus 3 squared. You get 10h squared over 8ma squared with a degeneracy of 2. Because you can have two different sets of quantum numbers, 1, 3 or 3, 1. Again, if you have a square, then the total energy is n sub x squared plus n sub y squared times h squared over 8ma squared. Now I'm gonna show you the first 9 energy levels from the lowest to the highest. 1, 1, 2, 1, 1, 2, 2, 2. We talked about this. And then the next level is 1, 3 or 3, 1. We have a degeneracy of 2 here. And then 2, 3, 3, 2. You square 3, you square 2. Sum it up, you get 9 plus 4, 13. Over here, 1, 4 or 4, 1. Square them, sum it up, you get 17. 3 squared, you get 18. 2 squared, 4 squared, you get 20. 3 squared, 4 squared, you get 25. So the corresponding energies in terms of h squared over 8ma squared are 2, 5, 8, 10, 13, 17, 18, 20, and 25. And also you have the degeneracy 1, 2, 1, 2, 2, 2, 1, 2, 2, respectively. Chapter 15, Quantum Translation. Section 15.5, the particle in the three-dimensional box. For the particle in the three-dimensional box, assuming the dimensions are a, b, and c, we have the wave function of the 3D particle. It's the product of a function of x, a function of y, and a function of z. The x function is the square root of 2 over a sine n pi x over a. The function of y is the square root of 2 over b sine n pi y over b. The function of z is the square root of 2 over c sine n pi z over c. Because the three quantum numbers in the three directions can be different, I'm using subscripts n sub x, n sub y, and n sub z as the quantum numbers in these three directions. The energy of this three-dimensional particle is the sum of its energies in the x, y, and z direction. They take the same form. It's n squared h squared over 8 ma squared in the x direction, n squared h squared over 8mb squared in the y direction, n squared h squared over 8mc squared in the z direction. I'm just assuming the box side length is a in the x direction, b in the y direction, and c in the z direction. Again, nx, ny, and nz are the quantum numbers in the x, y, and z directions. They can be different. Therefore, we add a subscript here, here, and here. N sub x, n sub y, and n sub z can be 1, 2, 3, 4, etc., and they can be and are often different. The wave function of the three-dimensional particle is summarized here. It's the function of x times the function of y times the function of z. So you can see this is mostly the one-dimensional particle in the box problem, and we have the square root of 2 over a sine n pi x over a. The other two wave functions of y and z are similar to that in the x direction. We just need to change the side length from a to b or c, the quantum number to n sub y or n sub z. And that's it. Over here we do have a typo. This should be z. For the particle in a cubic box, a equals b equals c. Now the three-dimensional energy is nx squared plus ny squared plus nz squared, and then multiplied by h squared over 8ma squared. A is the side length of the cube. Now, I'm listing the values of the three quantum numbers of the first 9 energy levels from the lowest to the highest. Over here, the three quantum numbers are all equal to 1. This is the lowest possible translational energy for a three-dimensional particle in a cube. So this is correspond to 1 squared plus 1 squared plus 1 squared. That's 3 multiplied by h squared over 8ma squared. Now what about the second energy level? It can be 211 or 121 or 112. Either way, we have 6 times h squared over 8ma squared. The third energy level, 1 squared plus 2 squared plus 2 squared. We get 9. 9h squared over 8ma squared. And also, we have a degeneracy of 3 here. Because when we have 1 to 2, this kind of combination, well, this one can be nx or ny or nz. The next level is 311 or 131 or 113 with a degeneracy of 3, because we have 3 sets of quantum numbers that correspond to the same energy. 3 squared plus 1 squared plus 1 squared, that's 11. Here we have a degeneracy of 1, 2 squared plus 2 squared plus 2 squared, that's 12. Now we have a degeneracy of 6. The 3 quantum numbers can be 1, 2, 3, but there are 6 different permutations. We can have 1, 2, 3 or 1, 3, 2. We can have 2, 1, 3 or 2, 3, 1. We can have 3, 1, 2 or 3, 2, 1. But either way, 3 squared plus 2 squared plus 1 squared, that's 14. So we can keep going and we can get more and more energy levels. Their energies in terms of h squared over 2a 2ma squared are 3, 6, this is 3, 6, 9, 11, 12, 14, 17, 18, 19, etc. The degeneracy of all these 9 energy levels are 1, 3, 3, 3, 1, 6, 3, 3, 3, respectively. Chapter 15, Quantum Translation, Section 15.6, The Tunneling Effects. When the energy barrier for the particle in the box is finite, the particle may appear outside the box, even if its energy is lower than the energy barrier, denoted by V0. V0 is a constant. This is called quantum tunneling. Outside the box, we have the Schrödinger equation. Over here, we have kinetic energy operator applied to psi. This is the potential energy applied to psi. The sum is h psi. H psi equals E psi. Now we can solve this differential equation. The second derivative of psi is equal to 2m V0 minus E over h bar squared times psi. The second derivative of a function is itself multiplied by a constant. So naturally, we think of exponential functions. The solution is indeed either e to the power of kappa x or e to the power of negative kappa x. A is just the normalization factor. This kappa is the square root of 2m times V0 minus E over h bar squared. Or you can write this kappa as the square root of 2m times V0 minus E, and then divided by h bar. This h bar is outside the square root. Because V0 is greater than E, kappa is real. It's a real number because mass is positive. If V0 is greater than E, this is positive. The square root of a positive number is a real number. So kappa is a positive real number as long as V0 is greater than E. Because the wave function must be finite, we'll choose this exponential function, e to the power of negative kappa x, where we define x as the tunneling distance between the particle outside and its nearest boundary. So x is always positive. It's the distance between the particle, for example outside here, the distance between the particle and the nearest boundary. We need this negative sign to make sure the wave function is finite. Now, since the total energy of the particle may be lower than its potential energy, we name this phenomenon quantum tunneling. Why? Because kinetic energy is equal to total energy minus potential energy. And if the total energy is less than potential energy, that means the kinetic energy of the particle outside the box is negative. It's a classically forbidden region. The tunneling wave function is e to the power of negative kappa x times the normalization factor a. X is the tunneling distance between the particle outside the box and the nearest boundary of the box. X is always positive. Kappa is also positive when V0 is greater than E. But again, when V0 is greater than E, that means the kinetic energy of the particle is negative, and it's so-called the classically forbidden region. Now, since psi is a times e to the power of negative kappa x, the tunneling probability density is psi squared. It's a squared times e to the power of negative 2 kappa x. Apparently, this function decays exponentially as x increases. When x increases, psi squared decreases. The rate of the decay of the tunneling probability depends on the magnitude of this kappa. And again, kappa is the square root of 2m times v0 minus e, and then divided by h bar. If kappa is large, this exponential function decreases rapidly. If kappa is small, this exponential function decays slowly. We observe more significant tunneling over a longer distance. Now, let's analyze this expression. When the mass of the particle is small, that means when the m is small, and also when v0 minus c is small, then kappa is small. When kappa is small, the tunneling probability e to the power of negative 2 kappa x decays slower as x increases. However, when the mass is large, and when the difference between v0 and e is large, then kappa is larger. The tunneling probability decays more rapidly. Again, when kappa is large, this exponential function decreases very rapidly. In summary, it's more likely to observe lighter particles, such as electrons, tunneling through a shorter distance, such as 1 angstrom. Meanwhile, it's highly unlikely to observe heavier particles, such as protons, tunneling through a longer distance. The mass of a proton is 1800 times the mass of an electron. So over here, they differ significantly. Now let's look at several examples in which a proton versus an electron tunnels through 1 angstrom distance versus 10 angstroms distance, with v0 minus e being 1 electron volt versus 10 electron volts. 1 angstrom is 10 to the power of negative 10 meters. 1 electron volt is 1.6 times 10 to the power of negative 19 joules. First, let's look at electrons. When x is just 1 angstrom, that means the tunneling distance is only 1 angstrom. And when v0 minus e is only 1 electron volt, that means the total energy is only 1 electron volt lower than the energy barrier. We can compute this kappa this way. We plug in all the numbers, 2 times the mass of the electron times v0 minus e, and then over h bar. It's about 5 billion per meter. Since the probability density is psi squared, the probability of finding the particle drops to this much after a tunneling distance of x. When x is 1 angstrom, we plug in the value of x and kappa. Kappa is 5 billion per meter. X, the distance of tunneling, is 1 angstrom. We plug in all the numbers, we get e to the power of negative 1. That's 0.36. So for an electron to tunnel through a barrier that's higher than the total energy by 1 electron volt, it's entirely possible. There's 36% chance to see this electron appearing just 1 angstrom outside the box, even if its kinetic energy on paper is negative. The kinetic energy of this particle outside the box with 1 angstrom tunneling distance is, over here you can see, it's negative 1 electron volt. So potential energy minus total energy is 1 electron volt. Therefore, kinetic energy is negative 1 electron volt. And there's this much chance of observing that electron with negative kinetic energy. However, when the tunneling distance is longer, well, the tunneling effect is smaller. It's just we plug in a longer distance here. Instead of e to the power of negative 1, we have e to the power of negative 10. Now this is so much smaller. It's about 10 to the power of negative 5. the tunneling probability drops rapidly as the tunneling distance increases. Now, what if the total energy is much lower than the potential energy? Let's say V0 minus E is now 10 electron volts. So actually, this means the kinetic energy is negative 10 electron volt. We again plug in all the numbers. We compute kappa again, the square root of 2 times the mass of the electron times 10 electron volt, and then over h bar. We have 16 billion per meter. We use 1 angstrom here, and we have e to the power of negative 3. Still, we have a decent probability, but this is much smaller than this one already. This is 0.36, this is 0.039. Now, what if the tunneling distance is 10 angstroms? Well, again, we plug in all the numbers. This minus 3 becomes minus 30. Minus 3.24 becomes minus 32.4. And over here, it's 10 to the power of negative 15. This is negligible. So the tunneling probability is smaller when V0 minus C becomes larger. So it's actually possible to have a negative kinetic energy for the particle appearing outside the box, but it cannot be too negative. It's difficult to be too negative. A little negative is fine, a short tunneling distance is fine, but a long distance and a very negative kinetic energy results in a very small tunneling probability. When do we observe significant tunneling? Well, when E is fairly close to V0. E can be less than V0, but not that much smaller. And also, when the tunneling distance is fairly small, we observe a larger tunneling probability. Now let's look at several examples for protons. For protons, we use the same parameters for the tunneling distance and the difference between V0 and E. We compute the kappa again. This time, well, this kappa is really large. And why is that? Because the mass is now 1800 times larger than the mass of an electron. So we're going to plug in all the numbers. Over here, it's actually about 219 billion per meter. Since the probability density is psi squared, then we can compute the tunneling probability using e to the power of negative 2 kappa x. We plug in all the numbers. We have e to the power of negative 44, and that's 9 times 10 to the power of negative 20. Very small number. Even though V0 minus C is only 1 electron volt, the tunneling distance is also only 1 angstrom, but because the mass of a proton is so much heavier than that of an electron, the tunneling probability of a proton is so much smaller than that of an electron. We can also plug in some other values for the tunneling distance. For example, 10 angstroms, and then we get 10 to the power of negative 191. Alright, so that means this is not going to be observed. We will not observe a proton tunnel through a barrier with this much distance and this much difference between energy and potential energy, because this number is just too small. We have a table of the tunneling probability here. Those are computed with this equation, e to the power of negative 2 kappa x. Kappa is the square root of 2m multiplied by V0 minus E. On the bottom, we have h bar. X is the tunneling distance. And again, we did 8 calculations, 4 for electrons, 4 for protons. The tunneling distance can be 1 angstrom versus 10 angstroms. This V0 minus C can be 1 electron volt or 10 electron volts. And again, V0 minus E is just negative kinetic energy of the particle. Alright, we plug in all the numbers. We got all those probabilities, and you can see Well, for the protons, all those numbers are really small. But for electrons, if you just tunnel through 1 angstrom distance, and if the energy barrier is only 1 electron volt, well, we have a decent chance seeing tunneling. What if the barrier goes up to 10 electron volt? Still 0.04, not too bad. What if the tunneling distance becomes 10 angstroms? Now it's fairly hard. It's about 10 to the power of negative 5. What if the distance is 10 angstroms, the barrier is also 10 electron volt? Well, the tunneling of the electron also becomes negligible. Well, you may ask, can we actually observe the tunneling of proton at all because this number is so small? Well, it's possible as long as we reduce this number or this number. So either way, if we have, for example, a much smaller number here than 1, or a much smaller number than 1 here, and then we will be able to observe a much more significant tunneling of a proton. The idea is to make kappa small. We want to make kappa small to observe more significant tunneling. And also, when x is small, the tunneling probability is significant. When x is large, the tunneling probability is small. Again, we'll analyze the tunneling effect. Its prevalence and more easily observed for light particles, such as electrons, with a short tunneling distance, such as a few angstroms. So it's really easy to see the tunneling of electrons over a few angstroms. Tunneling effects can be observed also for atoms or molecules, only if the tunneling distance is very small or this V0 minus E is extremely small. So ideally, we want both a small tunneling distance and a small V0 minus E to observe the tunneling of a heavy particle, such as a proton or an atom or a molecule. An interesting example of quantum tunneling is the tunneling of the electron in a simple hydrogen atom. The wave function of the 1s electron is e to the power of negative r. N is simply the normalization factor. R is the distance between the electron and the nucleus. We will study the solutions to the Schrödinger equation of the hydrogen atom later, but for now, let's look at this wave function. The total energy of this 1s electron is negative 1/2 atomic unit. 1 atomic unit is 4 times 10 to the power of negative 18 joules. So negative 1/2 atomic unit is the energy of that 1s electron. The potential energy of the electron is negative 1 over r atomic unit. And r is the distance between the electron and the nucleus in the atomic unit of length. 1 atomic unit length is 0.529 angstroms. Again, we'll learn this a bit later when we solve the Schrödinger equation for the hydrogen atom. Now, it is possible for the 1s electron to appear in a region that's more than 2 atomic units lengths away from the nucleus. And in that region, well, the kinetic energy is the total energy minus the potential energy, which means it's negative 1/2 minus negative 1 over r. And minus negative 1 over r is plus 1 over r. Now, this is the expression for the kinetic energy of the 1s electron of the hydrogen atom. What if this r is greater than 2 atomic units? Now we have a negative kinetic energy. So we can also observe the tunneling effect in a hydrogen atom. It's just prevalent and easily observed for light particles such as electrons. In general, the valence electrons are less attracted to the nucleus than the core electrons. So it's easier to observe the tunneling effects of the valence electrons. The energy it takes to remove A valence electron from an atom or a molecule is just much smaller than the amount of energy to remove a core electron. And this is why chemical bonds are always formed by the overlapping of valence electrons, never core electrons. The interference between the core electrons is almost always negligible, only because, again, it's extremely difficult to find a core electron far away from the nucleus, far enough to overlap with another core electron in another atom. So chemists care about valence electrons and the overlap of valence electrons. Chemists do not care about core electrons, and the overlap between core electrons is always negligible. Chapter 15, Quantum Translation. Section 15.7, the UV-Vis spectra of conjugated polyions. We can estimate the HOMO-LUMO gap for polyions, for example 135 hexatriene, assuming the conjugated pi electrons are free particles along the one-dimensional carbon chain. This is the structure of 135 hexatriene. Triene means we have 3 double bonds, and 135 specify the position of the double bonds, carbon 1, carbon 3, and carbon 5. And this is a simpler structure for 135 hexatriene. Now it does look like a one-dimensional box for the pi electrons. Alright, now let's look at the MO of this molecule. Let's focus on the pi-type MOs, molecular orbitals. There are 6 of them because we have 6 carbon atoms. Each carbon contributes 1 p electron in 1 p orbital. So we can use 6 p orbitals to make 6 MOs. Those are all pi-type MOs. The bottom 3 are occupied. The top 3 are unoccupied. The reason is we have 6 p electrons. The 6 p electrons only occupy 3 MOs, the bottom 3. Now, how do we know which MO has higher energy, which MO has lower energy by looking at this? Well, it's very simple. If you look at the bottom MO, you can see gray, 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 gray on top. They're all gray, bottom all white. So there's no node separating those p orbitals, 0 nodes. Now let's look at this side 2 MO. There's 1 node in the middle. Okay, we can cut it. Assuming gray is positive, white is negative. So between plus and minus, there's a 0 in the middle. Now this MO, plus, minus, plus. Between plus and minus, there's a 0. Between minus and plus, there's another 0. We have 2 nodes. Here we have 3 nodes. 1, 2, 3. 4 nodes. 1, 2, 3, 4. 5 nodes. 1, 2, 3, 4, 5. So from bottom to top, we have 0, 1, 2, 3, 4, 5 nodes. And the energy increases as the number of nodes increases. The bottom 3 are occupied by the 6 pi electrons. The top 3 MOs are occupied. The bottom 3 with fewer nodes are bonding orbitals. The top 3 are anti-bonding orbitals. And again, we analyze the number of nodes. We analyze the now quantum numbers for those MOs. If we assume this is just a one-dimensional particle, of course with a zigzag shape, but still it's considered as a one-dimensional box. And we can see, well, if we remember, in a one-dimensional box, the particle may have quantum numbers from 1, 2, 3, 4, 5, 6, etc. So for the particle in the box problem, the bottom MO corresponds to n equals 1. The quantum number is 1. Quantum number 2. Quantum number 3. For the HOMO, n equals 3. For the LUMO, n equals 4. So we have the quantum number of HOMO equals 3. the quantum number for the LUMO is 4, assuming this is a particle in the box problem. Now we'll just estimate the HOMO-LUMO gap for 135 hexatriene, assuming that 6 electrons are free particles along the carbon chain. We need to determine the length of the one-dimensional box. The 135 hexatriene carbon chain consists of 3 double bonds, 1, 2, 3, and 2 single bonds. The typical single bond distance is 1.5, and the typical double bond distance is 1.3. So we're going to just estimate the average 1.4. We have 5 carbon-carbon bonds, so the total length of this carbon chain is roughly 7 angstroms. Okay, this is a rough estimate. A is equal to 7 angstroms, and we know the energy levels should be n squared h squared over 8 ma squared. So for HOMO, we need to use 3 squared multiplied by this. For LUMO, it's 4 squared multiplied by h squared over 8 ma squared. Now, what's the HOMO-LUMO gap? It's the difference between 4 squared and 3 squared multiplied by h squared over 8 ma squared. So really, it's just 16 minus 9 times the Planck constant squared over 8 over the mass of an electron over the length of the one-dimensional box, which is approximately 7 angstroms. Plugging all these numbers on the Wolfram Alpha page, you get 8.6 times 10 to the power of negative 19 joules. That's the HOMO-LUMO gap. We can now calculate the wavelength of the photon that can promote an electron from HOMO to LUMO. The photon energy has to be this, the energy difference between HOMO and LUMO. So we set up the equation Hc over lambda equals the HOMO-LUMO gap. Solve this equation. Lambda is 230 nanometers. And this is how we predict the HOMO-LUMO gap for a polyene. And also, we can predict the UV vis spectra for a polyene molecule. Chapter 15, Quantum Translation. Section 15.8, Quantum Confinement. As the conjugated carbon chain of a polyene molecule increases, the HOMO-LUMO gap of the polyene becomes smaller. It's called redshift. This is because this value, n LUMO squared minus n HOMO squared, is roughly proportional to the number of carbon atoms. While on the bottom we have a squared. A squared is roughly proportional to the number of carbon atoms squared. Now let's look at this equation of HOMO-LUMO gap. It's n LUMO squared minus n HOMO squared multiplied by h squared over 8 ma squared. When the number of carbon atoms increases, this will increase, but also this a squared will increase. A squared increases faster than the difference between n LUMO squared and n HOMO squared. Assuming the average carbon-carbon bond distance is 1.4 angstroms, then the length of the 1D box is roughly n-1 times 1.4 angstroms. So if you have 6 carbon atoms, there are 5 bonds. If you have 8 carbon atoms, there are 7 bonds. So that's why n is the number of carbon atoms and also the number of pi electrons. Therefore, n HOMO is n over 2, and LUMO is n over 2 plus 1. This is because in each MO we have 2 electrons. Therefore, if we have n electrons, they occupy 1/2 of n MOs. Now let's look at the expression of the HOMO-LUMO gap. This is the quantum number for LUMO. This is the quantum number for HOMO. We take the squares of these two numbers and then take a difference. Here we have h squared over 8 ma squared. A is the box length. In this case, A is n minus 1 times 1.4 angstroms. Again, with n atoms, well, there are n minus 1 carbon-carbon bonds. Now, the HOMO-LUMO gap is proportional to n plus 1 over n minus 1 squared. We can see n minus 1 squared over here. Where does this come from, n plus 1? Actually, if you just evaluate this n over 2 plus 1 squared minus n over 2 squared, well, the difference is n plus 1. And therefore, the HOMO-LUMO gap is proportional to n plus 1 over n minus 1 squared. As n increases, well, both the numerator and denominator increase, but the denominator increases faster, and we have a smaller energy gap when we have more carbon atoms. It's called redshift. When n is much greater than 1, n plus 1 is close to n, n minus 1 is close to n. Now the HOMO-LUMO gap is proportional to the reciprocal of n, or the reciprocal of the number of carbon atoms. So now it's really clear that when we have a longer polyene molecule, we will observe a smaller HOMO-LUMO gap. The HOMO-LUMO gap is approximately inversely proportional to the chain length, or to the number of carbon atoms. In general, when a particle is confined, its energy is quantized. When the particle is confined in a smaller space, its energy spacing are larger. It's called blue shift. But when the particle is confined in a larger space, the energy spacings are smaller, and that's called red shift. When a particle is not confined at all, its energy spacings become infinitesimal or zero. For example, the energy of a free particle is continuous with a zero energy spacing, only because the free particle is not confined at all. And this figure depicts the redshift of the HOMO-LUMO gap as the size of some nanoparticles increases, and this phenomenon is called quantum confinement. It's often used to fine-tune the optical properties of nanoparticles. Mostly it's just the color of those nanoparticles. When we have a smaller particle, usually we have a larger energy spacing. When we have a larger particle, usually we have a smaller energy spacing. Also, we can see E sub g stands for the energy of the gap. Alright. Chapter 16, Quantum Rotation. Section 16.1, Classical Rigid Rotors. The simplest rigid rotor is a one-body, two-dimensional rotor, which is a particle rotating in a perfect circle with a constant radius. R0 denotes a constant radius. The kinetic energy of this particle is the rotational energy of the particle. Kinetic energy is half mv squared, and we have a circular motion, so the speed is d r0 theta over dt. R0 is the constant radius. Therefore, the kinetic energy is equal to half m r0 squared, and now d theta over dt squared. M r0 squared is the moment of inertia of this rotating particle, denoted by I. d theta over dt is the angular speed of the rotating particle, denoted by a Greek letter omega. The SI units of I and omega are kilogram meter squared and second to the power of -1, respectively. This data is in radian, not in degrees. So if a particle finishes the motion of this entire cycle within 1 second, then d theta over dt is 2 pi per second, assuming a constant speed. The angular momentum vector of the rotating particle is the cross product of the radius vector r and the momentum vector of the rotating particle. So L is r cross product p. L is the angular momentum, r is the radius vector, and p is the momentum vector. In a perfect circular motion, r and p are always perpendicular to each other. In this case, this L is simply r cross product p. Its magnitude is simply r times p. This r is the magnitude of the radius, and this p is the magnitude of the momentum. The kinetic energy can be written as 1 over m times mv squared, and this means the kinetic energy can be written as p squared over 2m, or in this case, with a perfect circular motion, it's 1 over 2m r squared, and then we have r cross product p squared. So we can also rewrite the expression of the kinetic energy of a rotating particle in a perfect circle. It's 1 over 2m r squared multiplied by the angular momentum squared, and therefore it's L squared over 2I. L is the magnitude of the angular momentum, and I is the moment of inertia. A rigid rotor has a constant radius and a constant moment of inertia. The simplest rigid rotor is a one-body, two-dimensional rotor, which is a particle rotating in a circle. The kinetic energy can be written as L squared over 2I. L is the magnitude of the angular momentum, and I is the moment of inertia. R0 here is a constant radius. Omega is the angular speed. Omega is d theta over dt, and L is I times omega. L is the magnitude of the angular momentum. More generally, the three-dimensional angular momentum can be written this way. The L vector is the r vector cross product the p vector. The p vector is m times the v vector. So L vector can be also written as the mass multiplied by the cross product of the r vector and v vector. We can also express the angular momentum vector as a determinant. Well, this is just because the cross product of two vectors can always be written in this form. Ij and k are the unit vectors in the x, y, and z directions. X, y, and z are the three components of the r vector. Px, py, and pz are the three components of the p vector. We can decompose a 3x3 determinant systematically into three 2x2 determinants like this. So we have these x component, y component, and z component. After the expansion of those 2x2 determinants, we have the expression of the vector of the angular momentum over here. So for example, the x component of the angular momentum is y times pz minus z times py. Over here, this is just a particle rotating in a perfect circle, and you can see the angular momentum L is the r vector, cross product the p vector. Tau is the torque. The torque is the r vector cross product the force vector. For a classical two-body, two-dimensional rigid rotation, the derivation of the rotational energy is similar. But there are two particles. Therefore, the total kinetic energy is 1/2 m1 v1 squared plus 1/2 of mv2 v2 squared. m1, m2 are the masses of the two particles. v1 and v2 are the speed of the two particles. Note that m1 r1 should be equal to m2 r2 for a two-body, two-dimensional rigid rotation, assuming there's no any other motion. R1 and R2 are the distances from M1 and M2 to the center of the mass. Alright, so over here this is R1, over here this is R2. This C denotes the center of the mass of the entire system. If M2 is heavier than M1, C should be closer to M2. The two masses have the same angular speed, so when they rotate, they travel at the same angular speed, but not necessarily the same speed, because R1 and R2 are often different. The speeds of the two particles are v1 equals r1 times d theta over dt. v2 is r2 times d theta over dt. Therefore, we can rewrite the expression of the kinetic energy as this: 1/2 multiplied by m1 r1 squared plus m2 r2 squared multiplied by this angular speed squared. This expression can also be simplified to 1/2 times I times omega squared. Omega is the angular speed, d theta over dt. I is the moment of inertia for the two-body rotor or two-particle rotor. I is simply m1 r1 squared plus m2 r2 squared. The two-body, two-dimensional rigid rotational energy can also be expressed as this. It's p1 squared over 2m1 plus p2 squared over 2m2. Since we have m1 times r1 equals m2 times r2, so m1 times r1 equals m2 times r2, and therefore m1 v1 is equal to m2 v2 for a rigid rotor. Well, because v1 is simply r1 times d theta over dt, v2 is r2 times d theta over dt. v1 and v2 are the speeds of m1 and m2. And now we set p is equal to m1 v1 and p equals m2 v2. Now we can further simplify the expression of the kinetic energy of the two particles. We'll just combine these two because they have a constant, this p squared in common. So the kinetic energy is 1/2 times the sum of 1 over m1 and 1 over m2 multiplied by p squared. Again, it's just because this p1 is equal to p2. Now we have this expression 1 over 2 mu times p squared. Here 1 over mu is defined to be 1 over m1 plus 1 over m2. Mu is called the reduced mass of the two-body system. If we take the reciprocal of both sides, mu is m1 times m2 over m1 plus m2. And now we have this expression of kinetic energy of this two-body, two-dimensional rigid rotor. It's p squared over 2 mu, or it can be written as this: 1 over 2 mu r squared, and then here we have the angular momentum squared. Therefore, again, the kinetic energy is L squared over 2I. L is the magnitude of the angular momentum, and I is mu r squared, and mu is the reduced mass. I is the moment of inertia of the two-body system. We can prove this mu times r1 plus r2 squared is equal to m1 r1 squared plus m2 r2 squared. Now let's prove this. Let's prove mu times r1 plus r2 squared is equal to m1 r1 squared plus m2 r2 squared. 1 over mu is equal to 1 over m1 plus 1 over m2. Again, these two expressions are both the moment of inertia of this two-body, two-dimensional rotating system. Again, m1 r1 equals m2 r2. Therefore, the ratio between r1 and r2 is the ratio between 1 over m1 and 1 over m2. And now we have a ratio among three terms: r1 plus r2 versus r1 versus r2 is 1 over mu versus 1 over m1 versus 1 over m2. Therefore, r1 is r1 plus r2 times mu over m1. r2 is r1 plus r2 times mu over m2. Now we're derive m1 r1 squared plus m2 r2 squared. Well, we'll just replace r1 with this: r1 plus r2 times mu over m1. We will replace r2 with this: r1 plus r2 times mu over m2. Now we expand both terms like this. There is definitely a common factor, which is r1 plus r2 squared. We can see that here, we can see that here. And also we see mu squared on top, mu squared on top. Therefore, the common factor is mu squared times r1 plus r2 squared. And on the left hand side, we have m1 over m1 squared. That's the reciprocal of m1. In the second term, we have the reciprocal of m2. Yeah, we look at this, the sum is 1 over mu, so we have this here. The result is mu times r1 plus r2 squared. So we just proved the moment of inertia can be written as m1 r1 squared plus m2 r2 squared. It can also be written as mu times r1 plus r2 squared. The moment of inertia of the two-body rigid rotor can be written in both ways. Its kinetic energy is just the angular momentum squared over 2I. Now let's imagine this is a diatomic molecule. So given the mass of the two atoms, we can compute mu. Given the bond distance, we have this r1 plus r2. Chapter 16, Quantum Rotation, Section 16.2, Two-dimensional quantum rotors. The time-independent Schrödinger equation for the one-particle two-dimensional rotor is this: the kinetic energy in the x direction plus the kinetic energy in the y direction plus the potential energy equals the total energy. And that's the physical meaning of this Schrodinger equation. We applied the kinetic energy operator to psi, potential energy operator to psi. On the left hand side, we have h psi. On the right hand side, e psi. H psi equals E psi. H is the Hamiltonian operator with a physical meaning of total energy E. A rigid rotor has a constant radius, denoted by R0. In a rigid two-dimensional rotor, the particle rotates freely in a circular motion with a constant radius R0. Here, rotates freely means its potential energy is 0. Now this particle never deviates from the circle. Therefore, we can write out these two equations. The potential energy of the particle is 0 on the circle, and the potential energy is infinity out of the circle. So when R is R0, V is 0. When R is different from R0, V is infinity. Therefore, we have a constraint regarding x and y of the particle. X squared plus y squared must be equal to R0 squared. The xy coordinate of the particle may be transformed into the polar coordinates. Well, if we define this angle to be theta, we have this R0 constant radius. The x is R0 times cosine theta. Y is R0 times sine theta. Tangent theta is y over x. We can now try to express delta squared over delta x squared and delta squared over delta y squared in terms of theta to reduce the number of variables from 2 to 1. In this Schrodinger equation, we see two variables, x and y. But we can express x and y as R0 cosine theta and R0 sine theta, and try to reduce the number of variables in this Schrodinger equation to only 1. Now let's do some calculus. Using the chain rule with theta and r being the intermediate variables, we have this. Delta psi over delta x is delta theta over delta x times delta psi over delta theta plus delta r over delta x times delta psi over delta r. We do need to pay attention to the subscripts. So what's the physical meaning of all this? Well, this is to hold y constant and determine how psi depends on x. Well, over here we hold theta constant, and then we determine how psi depends on r, and then how r depends on x. Here, this is how psi depends on theta, and then how theta depends on x. So overall, the physical meaning of the right hand side is also how psi depends on x. It's just we have a intermediate variable here, theta, and another intermediate variable, r here. Now for a rigid rotor, r is a constant anyway, so this term disappears in this case when r is constant. So how does psi depend on x? Well, we can just examine how psi depends on theta and then how theta depends on x. Now we're going to evaluate delta theta over delta x. This is non-trivial unless we again use an intermediate variable, and this time we use tangent theta as the intermediate variable. Alright, so delta theta over delta x can be written as this. Alright, you can see this is delta tangent theta, we have d tangent theta. Alright, so what does that mean? That means here, how does theta depend on x? Well, first we can determine how theta depends on tangent theta, and then how does tangent theta depend on x, right? So over here, it's just d theta over d tangent theta. The meaning is how theta depends on tangent theta. Alright, so it's possible to evaluate this. The first derivative of tangent theta is simply 1 over cosine theta squared. And tangent theta is y over x. So we can evaluate this derivative as well, holding y constant. This is just negative y over x squared. And this part is just cosine theta squared. Now y is r naught sine theta, x is r naught cosine theta. We clean it up, we get this. Delta theta over delta x is negative sine theta over r naught. Therefore, delta psi over delta x is equal to negative sine theta over r naught times delta psi over delta theta. And similarly, we can prove this. Delta psi over delta y is cosine theta over r naught times delta psi over delta theta. So in summary, we got this two equations. We can convert delta over delta x to negative sine theta over r naught, delta over delta theta. And this delta over delta y operator is cosine theta over r naught, delta over delta theta. Now for a rigid two-dimensional rotor, delta over delta x operator is negative sine theta over r naught, delta over delta theta. From here, we can derive the second derivative operator. The second derivative is simply the first derivative of the first derivative. So we just need to apply this operator 2 times. Now we can expand it because delta over delta x can be expressed in terms of theta here and then here. Now we're going to just apply this operator to everything inside. But before we do that, we see negative r naught as a constant. So we can take negative over r naught out. And then we have this expression, sine theta over r naught squared. And then delta over delta theta, sine theta, delta over delta theta. Now we're going to use the product rule. So really it's just applying this operator to this operator, and applying this operator to this sine theta. So we're going to do this. The second derivative with respect to x is going to be sine theta over r naught squared. Now we're applying delta over delta theta to sine theta. And then over here, multiply by this operator. And also we can just copy this sine theta here. We just apply this operator to this operator. Alright? And then we have 2 terms. It's sine theta over r naught squared. Over here, this is cosine theta. Delta over delta theta. And over here, it's sine theta. We have the second derivative with respect to theta. This is just the result. The second derivative with respect to x can be expressed in terms of theta. We can do that to y as well. We get this. You can prove it. So over here we can just prove it. We just do delta theta over delta y, and then similarly we introduce a intermediate variable tangent theta here, and then this is just 1 on the bottom over here. It's just 1 over cosine theta squared. Tangent theta is y over x. Now we hold x constant. We evaluate this derivative, which is just 1 over x, and this is just cosine theta squared. We clean it up. We get cosine theta over r naught as delta theta over delta y. Therefore, delta over delta y is this operator. The second derivative is to apply this operator 2 times. So we have this operator 2 times. And again, we use the product rule. We apply this operator, delta over delta theta operator, to cosine theta and to this delta over delta theta operator. So we have two terms over here. This part is negative sine theta, and this part is just the second derivative. So we get the expression here in terms of theta for the second derivative with respect to y. And also we got this before, the second derivative with respect to x. Now we sum it up. What's the sum of the second derivative operators with respect to x and y? We just sum up this and this. Fortunately, this term and this term cancel. They are the same except for the sign, so they cancel. These two may be combined because cosine theta squared plus sine theta squared is just 1. So in the end, the sum of these two second derivatives can be written in terms of theta. And it's pretty simple. It's just 1 over the constant radius squared multiplied by the second derivative operator with respect to theta. The sum of this can be denoted by this symbol. It's a triangle upside down squared. Well, it denotes the so-called Laplacian for the two-dimensional system. We simply define this Laplacian to be the sum of the second derivatives with respect to x and y for a two-dimensional system. And now the Schrödinger equation for the one particle two-dimensional rigid rotor is dramatically simplified. It's just this. And when you look at this, well, hopefully you remember this equation looks like the Schrödinger equation for a free particle in the one-dimensional universe. Again, the Schrödinger equation for the one particle two-dimensional rigid rotor is this: negative h bar squared over 2m over r naught squared. And then this is the second derivative of psi with respect to theta. That's the left-hand side. Right-hand side is E psi. We define the moment of inertia to be mr naught squared for this rigid rotor. And then mr naught squared is replaced with I. And then we move all the constants to the right-hand side. We see the second derivative of psi is negative 2ie over h bar squared times psi. How do we solve this differential equation? Well, we can do some simplification. If we set L to be the square root of 2ie over h bar squared, we'll see a simpler differential equation. The second derivative of psi is negative L squared times psi. Again, it looks really similar to the Schrödinger equation of a free particle in a one-dimensional universe. This is also considered a one-dimensional universe. It's just we have a circular universe. There are two possible normalized solutions, psi plus, psi minus. They are e to the power of plus il theta and e to the power of negative il theta. A plus, a minus are just the normalization constants. They can be arbitrary constants as well if you don't need to normalize those. L is a quantum number, and L tells us the magnitude of the angular momentum. We now prove that L must be an integer. Alright, so let's look at this solution first. E to the power of plus il theta. Because this function must be continuous and single valued according to postulate 1, then we have this equation. Alright, psi of theta should be equal to psi of theta plus 2 pi. because the position at theta and the position at theta plus 2 pi are exactly the same. Alright, you cannot have two different values for psi at position theta and at position theta plus 2 pi, because theta plus 2 pi is simply theta if you're talking about the position of the particle. Now we have this equation, both sides divided by a common factor, a plus e to the power of il theta. We have this equation. E to the power of il 2 pi has to be 1. Again, to satisfy postulate 1, the wave function of the two-dimensional rigid rotor must be continuous and single-valued. And from that, we get this equation. E to the power of plus il 2 pi is 1. We're going to use Euler's formula, which says that e to the power of I theta is equal to cosine theta plus I times sine theta. Now we get these two equations. Cosine L times 2 pi is 1. Sine L times 2 pi is 0. These two equations hold true only when L is an integer. Alright, you can try any other non-integer values. You're not going to be able to satisfy both equations at the same time. So L has to be an integer. L denotes the angular momentum quantum number for the two-dimensional rotors. Later you will see we use L to denote the angular momentum quantum number for three-dimensional rotors as well. In general chemistry, you have learned four quantum numbers NL, M sub L, and M sub S. And in general chemistry, you have learned L is the angular momentum quantum number for an electron in the atom. Alright, I did mention the four quantum numbers you have learned in general chemistry: N, L, M sub L, and M sub S. It's possible that you have not learned the quantum number S yet, but now I'm going to just talk about all those for a review, and also to introduce the quantum number S if you have not learned this. N is the principal quantum number. That's pretty easy. L is the angular momentum quantum number. It's about the three-dimensional rotation of an electron in the atom. M sub L is called the magnetic quantum number. M sub L H bar is the Z component of the three-dimensional angular momentum of the electron of interest. Now let's talk about S and M sub S. So we know electrons spin. So this S is the spin quantum number. S denotes S is used to describe the three-dimensional spin of the electron. Now M sub S H bar is the Z component of the three-dimensional angular momentum of electron spin. So when we are talking about electron spin, the electron can spin about its x, y, and z axis at the same time. So it's possible to get the x, y, and z components of its three-dimensional angular momentum. So this quantum number S describes the three-dimensional spin. M sub S is related to just the Z component. Now let's get back to the two-dimensional rotors. We may define M sub L to be plus minus L for a two-dimensional rotor. Well, later we'll learn this. M sub L can be negative L plus 1, negative L plus 2, etc. all the way to L for a three-dimensional rotor, or for the electrons in an atom. You learn this rule in general chemistry. M sub L has to be from negative L to positive L with an increment of 1. Alright, it's just because in an atom the rotation of the electrons about the nucleus are 3-dimensional rotations, so we use this. But for a 2-dimensional rotor, M sub L can only adopt 2 different values. It's either negative L or positive L. And now the wave function of the rotating particle is this: a to the power of a times e to the power of I times m sub L times theta. Again, this m sub L can be plus L or negative L. This m sub L is signed, and it denotes the z component of the angular momentum. Well, if you have only a 2-dimensional rotation, well, the angular momentum can be pointing up or pointing down. It's perpendicular to the plane of the rotation. M sub L h bar is the signed z component of the angular momentum of the 2-dimensional rotor. For example, if L is 2, M sub L can be negative 2 or 2. When L is 4, M sub L can be negative 4 or 4. What if L is 0? Then M sub L can only be 0. Again, this is the wave function for the 2-dimensional rotation. It's e to the power of I times quantum number m sub L and then times theta. M sub L can be plus minus L. Now we can derive the physical properties of this system. First, the kinetic energy. What's the kinetic energy operator? Well, it's negative h bar squared over 2m times the Laplacian. The Laplacian is simply delta squared over delta x squared plus delta squared over delta y squared. And then we learned that for this 2-dimensional rotation, the Laplacian can be derived in terms of theta. It's 1 over r naught squared delta squared over delta theta squared. So over here we have the kinetic energy operator applied to psi. We'll just evaluate this. We plug in the expression of psi. We take the second derivative of psi. It's easy because it's an exponential function. We just need to copy this I m sub L twice. Well, it's just I times m sub L squared, which is negative ml squared. And then we have this wave function here. We clean it up. We have a constant multiplied by psi. That constant is the rotational energy. The expression is m sub L squared h bar squared over 2I. Therefore, the kinetic energy of this rotating particle is ml squared h bar squared over 2I. M sub L can be plus minus L, and L can be 0, 1, 2, 3, 4, etc. We determined the kinetic energy. We can also determine the z component of the angular momentum. If we are looking at just the z component, its expression is negative IH bar times x delta over delta y minus y delta over delta x. So we can apply this operator to psi. It's like this. And remember, we expressed delta over delta x and delta over delta y in terms of theta. So we have all this negative sine theta over r naught delta over delta theta. Here, cosine theta over r naught delta over delta theta. So we can just replace x and the delta over delta y with here x should be R naught cosine theta. Delta over delta y should be cosine theta over R naught d over d theta. And here y is R naught sine theta. Delta over delta x should be negative sine theta over R naught delta over delta theta. So anyway, we can express the z component of the three-dimensional angular momentum operator in terms of theta. We're doing it here. So this is the z component of the three-dimensional angular momentum operator, and we can express it this way. Alright, and we have everything in terms of theta here. It seems R naught cancel, R naught cancel. We have cosine theta squared, we have sine theta squared. And really it's awfully simple. It's in the end delta over delta theta. So sometimes it's convenient to use polar coordinates. Alright, so if we apply the z components of the angular momentum to psi, that's equivalent to negative I h bar delta over delta theta applied to the wave function. The result is m sub l times h bar times psi. M sub l h bar is the eigenvalue. So we determined the eigenvalue for psi when the z component of the angular momentum is applied to psi. So again, m sub l h bar is the z component of the vector of the angular momentum, and since m sub l is plus minus l and l is 0, 1, 2, 3, 4, well, you can see, we have a quantized z component of the angular momentum. The value of the z component of the angular momentum can be 0, plus minus h bar, plus minus 2h bar, plus minus 3h bar, etc. The angular momentum of such a rotating particle is always an integer multiple of h bar, regardless of the mass of the particle or the radius of the ring. So if you have two massive astronomical bodies rotating about each other, well, their rotational energy must also be an integer multiple of h bar. Okay, now let's look at this case. It's a special case. M sub l can be 0. When m sub l is 0, the velocity, the speed, the angular momentum of the particle are exactly 0, with no uncertainty. So does this violate the Heisenberg's uncertainty principle? No, because the uncertainty of its angular position is considered infinity. Alright, so theta just can be any value. Alright, what's the physical meaning of this? Well, it's kind of strange. When m sub l equals 0, it simply tells you the kinetic energy is 0, the speed is 0, the angular momentum is 0, but now where is the particle? Well, we don't really know where the particle is at all. This particle is all over the circle. The angle of the particle is all over the entire range of the angle. Theta can be from negative infinity to positive infinity. So this is not a violation of the uncertainty principle. Although the uncertainty of the momentum is 0, the uncertainty of its angular position is infinity. Now, given this wave function here, we can determine the normalization factor A. Well, although this is fairly trivial, because you can see if we want to determine the physical property of this system, the value of A is not very important. But still, for some other problems, we might need the expression of A. So let's anyway derive A. The probability of finding the particle is 100% when theta is from 0 to 2 pi. And therefore, we have this equation. And then, well, the squared modulus of a function is equal to the product of this function and its complex conjugate. So we're going to use this statement, and we see the squared modulus of this wave function is equal to simply a squared. Now we have this equation. Sorry, I forgot to add d theta here, and we should have d theta here. We can integrate this, and then we determine that a should be 1 over the square root of 2 pi. And now we have a normalized wave function, e to the power of I times m sub l times theta over the square root of 2 pi. This is normalized. Again, m sub l can be plus l or negative l. Alright, you may view this as clockwise rotation and counterclockwise rotation. So one is positive, one is negative. L is the angular momentum quantum number. Alright, L has to be non-negative. L is 0, 1, 2, 3, 4. M sub L can be correspondingly 0, plus minus 1, plus minus 2, plus minus 3, plus minus 4. For a two-particle, two-dimensional rigid rotation, the Schrödinger equation and the solutions are the same as those for one-particle, two-dimensional rotation. We just need to make one small change. For the one-particle system, we use the mass of the particle. For the two-particle system, we replace the mass with the reduced mass of two particles. Alright, so the Schrödinger equation is this, negative h bar squared over 2 mu r naught squared, and then delta squared psi over delta theta squared is equal to E psi. Mu is the reduced mass of the two masses. 1 over mu is 1 over m1 plus 1 over m2. We can take the reciprocal of each side, and then we get mu equal to m1 m2 over m1 plus m2. The kinetic energy of the two rotating particles is still m sub l squared h bar squared over 2I, the same as the one particle system. M sub l is plus minus l. L is a non-negative integer. Well, the small difference is in I. I is the moment of inertia. But this time, since we have two particles, I is mu r squared. Alright, so I can be also expressed as mu times r1 plus r2 squared. Again, r is the distance between the two particles. R1 is the distance between mass 1 and the center of mass. R2 is the distance between mass 2 and the center of mass. The angular momentum of this two-body, two-dimensional rotor also must be either 0, plus minus h bar, plus minus 2h bar, plus minus 3h bar, plus minus 4h bar, etc. in the z direction. Again, we have a plus minus sign. They correspond to clockwise and counterclockwise rotations. Chapter 16, Quantum Rotation, Section 16.3, Three-dimensional quantum rotors. The three-dimensional one-particle rigid rotor has a constant radius denoted by r0. The time-independent Schrödinger equation for this one-particle system is this: kinetic energy operator applied to psi, potential energy operator applied to psi. The sum is equal to E psi. The left-hand side is also H psi, where H is the Hamiltonian. X squared plus Y squared plus Z squared is equal to R squared. V is 0 when R is equal to R0. V is infinity when R is different from R0. That ensures the particle stays on the sphere. So this problem sometimes is also called quantum particle on a sphere. Now let's look at the conversion between the x, y, z Cartesian coordinates and the spherical polar coordinates. Let's look at this position. We have x, y, and z, of course, but also we can use r, theta, and phi to specify the same position. R is the distance between this position and the center. Theta is the angle between the r vector that specifies the position and the z-axis. And also we can project this vector r to the xy plane. And now we have this dashed line on the xy plane. The angle between this dashed line and the x-axis is phi. Now we have x is r0 sine theta cosine phi, y is r0 sine theta sine phi, z is r0 cosine phi. This is just trigonometric functions, and if this r is r0, we can do a projection of this vector to the z-axis. Therefore, the z component is just r0 times cosine theta. And now this dashed line, the projection of vector r on the xy plane is r0 sine theta. So this is r0 sine theta. Its projection on the x-axis is r0 sine theta times cosine phi. Its projection on the y-axis is r0 sine theta times sine phi. Again, x squared plus y squared plus z squared is equal to r squared. For this rigid rotor, r is just r0, and then we have this equation. We can also look at tangent theta. Tangent theta is this dashed line divide. Tangent theta, yeah, it's this dashed line over the z component, here. And we have tangent phi. Tangent phi is pretty simple. It's just y over x. So we just do y over x. We have sine phi over cosine phi. That's tangent phi. The range for theta in quantum chemistry is defined to be from 0 all the way to pi. Alright, so when the vector is pointing up, theta is 0. When the vector is pointing down, theta is pi. We can also look at phi. Well, phi can be from 0 to 2 pi. So if this projection is on the x-axis, that's just 0. So we can rotate 90 degrees to the y-axis, 180 degrees to negative x, 270 degrees to negative y. And finally, after we rotate 360 degrees or 2 pi, we get back to this position. Again, in quantum chemistry, we use r, theta, and phi to specify the position. Theta corresponds to the latitude of Earth. Phi corresponds to the longitude of Earth. However, we have a slightly different lower limit and upper limit comparing quantum chemistry and geography. In geography, latitude is from north 90 degrees to south 90 degrees. The longitude is from west 180 to east 180. Over here, theta is 0 to pi, phi is 0 to 2 pi. However, they do share something in common. It's just between North Pole and South Pole, the latitude spans 180 degrees or pi. Over here, it's also 180 degrees or pi. The longitude, well, the longitude spans 360 degrees or 2 pi. Same here. phi spans a range of 2 pi or 360 degrees. Alright, we'll just imagine there's a axis pointing from the South Pole to the North Pole. That's the z-axis. Alright, that's the z-axis. We can now derive the Schrodinger equation in spherical polar coordinates. When r is r0, it's easier. If r is not a constant, it's more difficult. Now let's do the derivation, assuming r is r0. So this is the Schrodinger equation. You can see I dropped the potential energy term because for this problem, three-dimensional particle on a sphere, v is just 0 when the particle is on the sphere. V is infinity when the particle is not on the sphere. So since v is just 0 when the particle is on the sphere, we just drop the potential energy term. We're going to use the chain rule. How does psi depend on x? Well, we can express this in terms of r, theta, and phi. So we look at how psi depends on r and how r depends on x. How psi depends on theta and then how theta depends on x. How psi depends on phi and how phi depends on x. But since r is r0, it's a constant. So really psi only depends on theta and phi. The first term is just 0. So how does psi depend on x? Again, we can use theta and phi as the intermediate variables. It's just the chain rule. Similarly, we can write out delta psi over delta y. It's just how psi depends on theta, theta depends on y, how psi depends on phi, and how phi depends on y. What about z? Fortunately, when we are talking about z, there's no phi because if you look at this, delta psi over delta z is simply delta theta over delta z times delta psi over delta theta. We do not worry about this phi term because if you can just look at this, if I change the value of phi, how does the value of z change? Well, there's no change. Z simply does not depend on this phi, this longitude. So we can express delta psi over delta x, delta psi over delta y, delta psi over delta z in terms of theta and phi. The reason we don't have to worry about r is a constant. Now let's derive this one, delta psi over delta z. It's easier because z is a function of only theta, so we have this equation. Delta psi over delta z is delta theta over delta z times delta psi over delta theta. Over here, theta is the intermediate variable, and this is one of the applications of the chain rule. Now we're going to do derivation. We will insert another intermediate variable here, tangent theta. So this part, delta theta over delta z is delta tangent theta over delta z times d theta over d tangent theta. D theta over d tangent theta is the reciprocal of d tangent theta over d theta. So we have this. This part can be easily evaluated if you're familiar with single variable calculus. This part, tangent theta is the square root of x squared plus y squared over z, because the top is r0 sine theta, the bottom is r0 cosine theta. Finally, we have just this term, and then we're gonna just do a bit derivation. This part is just cosine theta squared. This part, we're gonna just hold the square root of x squared plus y squared constant because x and y are held constant, so it's here. We just need to get the first derivative of 1 over z. It's negative 1 over z squared, and we have all this. And now we need to convert x, y to r theta phi, z to r theta phi. And then on top we have r0 sine theta. On the bottom we have z squared, therefore it's r naught squared cosine theta squared. We clean up everything, we get negative sine theta over r naught, delta psi over delta theta. We just converted this derivative to the polar spherical coordinates right here. The simplified notation is this: delta over delta z is equivalent to negative sine theta over r naught, delta over delta theta. We're not done yet, because if you look at the kinetic energy operator, it involves the second derivatives. Alright, now the second derivative with respect to z is simply, well, the first derivative operators apply twice. So you have delta over delta z applied to delta over delta z. And then we have this delta over delta z here and here. And we first clean up a little. We take this negative over 1 naught out. We have this expression. And then we apply delta over delta theta operator to everything inside the parentheses. We need to use the product rule, so we get this sine theta, its derivative is this, and then we copy this here, we copy sine theta here, we apply delta over delta theta to delta over delta theta. That's the second derivative. So we have this expression, and I can take the sine theta into the parentheses, and we got this. Well, in principle, we can also convert the second derivatives of psi with respect to x and y into polar spherical coordinates as well, using the same strategy. It's a lot more tedious because we have to worry about two variables, both theta and phi, when we are deriving this. If you are interested in this conversion, you can take a look at Appendix P. In Appendix P, I converted the XYZ coordinates to the polar spherical coordinates r, theta, and phi for the kinetic energy operator, or you can say the Laplacian operator. In the polar spherical coordinates, after we finish all those conversions from XYZ to r, theta, phi, we'll get this shortening equation in r, theta, and phi. It looks more complicated. The reason we do this is because, well, if you use XYZ coordinates, it's actually more difficult to solve that shortening equation. Mathematically, it's easier to solve the shortening equation for the three-dimensional rigid rotor using polar spherical coordinates. Especially since r is constant, we have only theta and phi as the only two variables in this equation. And over here you see it's negative h bar squared over 2i. I is the moment of inertia. I is mr squared. Since it's a rigid rotor, r is r naught. R naught denotes a constant radius. If you have a two-particle system, I is mu r naught squared. We need to replace the mass with the reduced mass mu. Still remember the definition of mu? 1 over mu equals 1 over m1 plus 1 over m2. Theoretically, we can solve this equation. The solutions are fairly complicated. The solving process is extremely tedious. So I'm just providing you the first few solutions here. 1, 2, 3, 4, 5, 6. Actually more than 6, because over here there are two solutions. Let's look at the first solution here. It's just a constant, but why it's 1 over the square root of 4 pi? Well, it's just because we want to have a normalized solution. So this is actually normalized. So if you integrate this with respect to sine theta, d theta, d phi, you're going to get 1. Alright, what do these two numbers mean? We have a number in the subscript. That's quantum number L. and we have another number in the superscript. That's m sub l. So we have this kind of format over here, and y is the solution to the Schrodinger equation. Alright, so we have a bunch of solutions. This is the first one. The second one here, L equals 1, m sub L is 0, and you can see it's a constant times cosine theta. The constant is just the normalization factor. Cosine theta, remember, is proportional to z, because z is R0 times cosine theta. We have a couple complex functions here. It's a constant times sine theta times e to the power of plus minus I phi. These two are the solutions to the Schrodinger equation over here. But also remember, if we take the linear combinations of e to the power of plus minus I phi, we can get cosine phi, we can get sine phi. Cosine phi times sine theta is simply x over R0. Sine phi times sine theta over R0 is y. So this two combinations are proportional to x and y. And now over here we have more solutions. This one is proportional to 3z squared minus R0 squared. And the linear combination of these two-way functions are proportional to xz and yz. Also, we can just do a linear combination of these two complex functions. We can make cosine 2 phi, we can make sine 2 phi. Cosine 2 phi is cosine phi squared minus sine phi squared. Sine 2 phi is 2 times sine phi cosine phi. That's just mathematics. And you can see the linear combinations of these two functions are proportional to xy and to x squared minus y squared. Eventually you'll see this one is proportional to the wave function of the s orbital. This is proportional to the 2pz orbital, 2px, 2py orbitals. And now we have 3D z squared orbital, 3D xz, 3D yz. Over here it's proportional to 3D xy and 3D x squared minus y squared in the hydrogen atom. The reason I mentioned the hydrogen atom is because we can only solve the Schrodinger equation for the hydrogen atom exactly, not for any other atoms. Again, we can look at the linear combinations of some of the solutions. They resemble the SPD orbital. The first one is y 0, 0. L is 0, m sub L is 0. Well, that's just s orbital. Remember, if you have s orbital, L has to be 0, m sub L has to be 0. It's a constant. That means it does not depend on theta or phi, and that means it has to be spherical. Only a spherical shape does not depend on theta or phi. Over here, y 1, 0. L is 1, m sub L is 0. Isn't that a pz orbital? Also, we can see this cosine theta is proportional to z. Now we have two exponential functions over here, e to the power of plus minus I phi. The linear combination of this may result in cosine phi or sine phi, depending on whether you're doing addition or subtraction. Alright, so cosine phi is the sum of these two exponential functions over 2. The sine phi is the difference between these two divided by 2i. So anyway, we can get cosine phi and sine phi from the linear combinations of these two complex functions. Cosine phi times sine theta is x over R0. Sine phi times sine theta is y over R0. And they correspond to the px, py orbitals. And remember, in general chemistry, we have m sub L equals 1. Then when we have L equals 1, the m sub l can be plus minus 1 or 0 here. And therefore, we have 3 p orbitals. Over here, it's just mathematical proof. We can just express x over r naught and y over r naught as linear combinations of these two complex functions. We can sum up these two complex functions. I sine phi cancel. Alright, and then we get 2 times sine theta times cosine phi. It's proportional to x. We can take the difference between these two. Alright, so the difference over here, we expand them. It's just Euler's formula or Euler's equation. Cosine phi cancel, and then we get 2i sine phi in the parentheses, and the result is proportional to y. Well, we can also look at more complex d functions where L is 2. When L is 2, m sub L can be -2, -1, 0, 1, and 2. When m sub L is just 0, the solution is this. Well, it's actually just proportional to 3z squared minus r naught squared. Alright, so this part is equal to this part. You can verify this because z over r naught is cosine theta. We have these two complex functions. The linear combinations of these two are proportional to xz and yz. They correspond to the dxz orbital and dyz orbital in the hydrogen atom. Now, m sub L can be plus minus 2. So we have e to the power of plus minus 2i phi. The linear combinations of these two different solutions can make xy over r naught squared and x squared minus y squared over r naught squared. They correspond to the dxy orbital and dx squared minus y squared orbital in the hydrogen atom. The dxy orbital is proportional to xy. The dx squared minus y squared orbital is proportional to x squared minus y squared. I'm just showing you some mathematical derivation here. Xz and yz can be expressed as a linear combination of these two complex functions. So we can add up these two complex functions. We get sine theta, cosine theta, and then 2 cosine phi, and it corresponds to just xz orbital. It's proportional to x and z. We can take the difference between these two, and we get sine theta, cosine theta, and then 2i sine phi. And hopefully you remember cosine theta is proportional to z. Sine theta, sine phi is proportional to y. So this linear combination is proportional to yz. And these two are simply just the xz, dxz atomic orbital and dyz atomic orbital. Similarly, we can also express xy and x squared minus y squared as a linear combination of these two. I'll let you do the derivations yourself. Or we can just look at this page. We can prove xy is and x squared minus y squared can be expressed as linear combinations of these two complex functions. So we can sum up these two complex functions right here, and then we have 2 sine theta squared times cosine 2 phi. Cosine 2 phi is cosine phi squared minus sine phi squared. So we have these two terms. Sine theta times cosine phi is x over r naught. Sine theta times sine phi is y over r naught. So you can see the result is proportional to x squared minus y squared. And this is just the dx squared minus y squared atomic orbital. Now if we take the difference between these two complex functions, we'll get 2i times sine theta squared times sine 2 phi. Sine 2 phi is 2 sine phi cosine phi. Now sine theta times sine phi, that's y. Sine theta times cosine y, that's x. Therefore, this linear combination is proportional to xy, and this corresponds to the dxy orbital in the hydrogen atom. So again, in summary, dxy, dx squared minus y squared are linear combinations of these two complex functions. When L is 2, m sub L is plus minus 2. dxz, dyz are linear combinations of these two complex functions. L is 2, m sub L can be plus minus 1. Finally, dz squared is simply y to 0. L is 2, m sub L is 0. This is just to remind you the conversion between x and r theta phi, between y and r theta phi, between z and r theta. Z does not depend on phi, and phi does not depend on theta. And this is the picture over here. Theta corresponds to the latitude, phi corresponds to the longitude. In quantum chemistry, the range for theta is between 0 and pi. For phi, the range is from 0 to 2 pi. Well, now let's look at the shapes of those SPDF type linear combinations of this y function. We have the subscript L and superscript m sub L. L is the angular momentum quantum number. M sub L give you the z component of the angular momentum. So this is when L is 0. These three are when L is 1. And then m sub L can be 0 and plus minus 1. Over here, L is 2. M sub L can be 0. That's the middle one. This is the middle one. And to the left, to the right, you have dxz and dyz. And this one and this one, well, we have dxy and dx squared minus y squared. So this depiction of dxy and dx squared minus y squared is a little bit problematic, because these two orbitals should not look the same. So one should be about 45 degrees from the other. So you need to rotate this about the z-axis by 45 degrees. When you have dxy, the lobes are on the axis and y-axis, x-axis and y-axis. All right. But when you have dx squared minus y squared, well, the lobes are actually on the diagonal lines. We have f-type shapes as well. When you have f-type functions, L is 3. So m sub L can be from -3 to 3. That's why we have 7 f atomic orbitals. The middle one, we have m sub L equals 0, and correspondingly we have m sub L equals minus plus 1, minus plus 2, minus plus 3. The degeneracy is simply 2L plus 1. When L is 0, the degeneracy is 1. When L is 1, the degeneracy is 3. When L is 2, the degeneracy is 5. When L is 3, the degeneracy is 7. That's why in general chemistry we learn that, you have like one s orbital in a given shell, 3p orbitals, 5d orbitals, and 7 f orbitals. Chapter 16, Quantum Rotation, Section 16.4, Angular Momentum and its z-component of three-dimensional rotation. The three-dimensional rotational energy of this wave function of a two-particle system is L times L plus 1 times h bar squared over 2I. I is the moment of inertia. L is the angular momentum quantum number. L can be 1, 2, 3, 4, 5. L can also be 0. In that case, the rotational energy is 0. M sub L can be from negative L to positive L. So it's possible for us to observe a degeneracy of 2L plus 1. The total rotational energy can be expressed as this. What about the rotational energy in the z direction? The expression is a little simpler. It's m sub L squared h bar squared over 2I. Again, m sub L is from negative L to positive L. So you can see the rotational energy in the z direction is always smaller than the total rotational energy here. The maximum value for m sub L is just L. You plug it in, you get L squared h bar squared over 2I, and over here you have L times L plus 1 h bar squared over 2I. The angular momentum in the z direction is simply m sub L h bar. Now we look at one specific example. This function y with L equals 1, m sub L equals 0. Well, it corresponds to the pz atomic orbital. The function is cosine theta. We'll just prove this. We'll apply the rotational energy operator to the wave function and see if we can get h bar squared over I times the wave function. The rotational energy operator is fairly complex. It's this. We're going to just apply this whole thing to this cosine theta function. Don't worry about this normalization factor. It will just appear in every single step, including at the end. Cosine theta does not depend on phi. So when you apply this operator to cosine theta, you get 0. We apply this delta over delta theta to cosine theta, we get negative sine theta. Negative sine theta times sine theta, we get negative sine theta squared. Alright? We copy this constant over here. We copy negative h bar squared over I over here. We copy 1 over sine theta here and another operator here. Now we take the derivative of sine theta squared. That's just 2 sine theta cosine theta. This negative sign and this negative sign cancel, so we have a positive expression over here. Sine theta and this sine theta on the bottom cancel, so we got this expression. And note that this is simply the wave function over here. So when we apply the rotational energy operator to this wave function, we get a constant times this wave function. That constant is the eigenvalue of this function. The eigenvalue is h bar squared over I. There's a physical meaning of this eigenvalue. It's the rotational energy of a 2pz electron. It's h bar squared over I. I is the moment of inertia of this rotating particle. Given this wave function, we can compute the rotational energy in an easier way. We'll just use this formula here. This formula comes from solving the Schrödinger equation. If we use this formula, we can just plug in L equals 1. Immediately we get h bar squared over I. That's the rotational energy of this system. The magnitude of the angular momentum is the square root of L times L plus 1 and then times h bar. In this case, L is 1. So the magnitude of the angular momentum of this wave function is square root of 2 times h bar. So over here you can imagine that on top we have the angular momentum squared. The angular momentum squared over 2I is the rotational energy. So what about the z component? Well, the z component is simply m sub l h bar. In this case, m sub l is 0, so the z component is 0. And this square root of 2 times h bar comes from the x direction and y direction. Now let's look at two other solutions over here. L is 1. M sub L can be plus 1 or minus 1. What is its rotational energy? We can again use this equation, very simple. L is 1, so the rotational energy is h bar squared over I. The magnitude of the angular momentum is again the square root of 2 h bar. Because again the rotational energy over here is the angular momentum squared over 2I. What about the z component? Well, the z component is plus minus h bar, because the z component of the angular momentum is m sub l h bar. So now we have examined three different solutions. When L is 0, m sub L can be 0 or plus minus 1. We're going to look at this graph that shows us the angular momentum vectors, and they all have the same length, square root of 2 times h bar. So over here, we know that. But they have different z components. Their z components are 0, minus h bar, plus h bar. They correspond to m sub L being 0, minus 1, or plus 1. Now, what if L is 2 or 3 or 4? Then the degeneracy becomes 5, 7, and 9. The magnitude of the angular momentum when L is 2, we'll still use this equation, okay, and also this equation to calculate the rotational energy and the magnitude of the angular momentum. Alright, so we just plug in L equals 2. The angular momentum is square root of 6 h bar. When L is 3, the angular momentum is square root of 12 h bar. What about the rotation energy? Well, again, just plug in L equals 2 here. 2 times 3 times h bar squared over 2I. When L is 3, you plug in 3 here. 3 times 4 times h bar squared over 2I. And that's the rotational energy. Again, we have two equations. One for the three-dimensional rotation energy, L times L plus 1 times h bar squared over 2I. The other is an equation for the angular momentum. Its magnitude is the square root of L times L plus 1 h bar. So we can make a lot of predictions already given the value of L for a electron, for example, in the hydrogen atom. Again, if we have a solution like this, L is 2, we plug in the number, the rotation energy is 3 times h bar squared over I. M sub L can be minus 2, minus 1, 0, 1, 2. We have a degeneracy of 5. So we have this 5 different options. They share the same energy, or specifically, they have the same rotational energy. The magnitude of the angular momentum, again, we just use this equation. It's square root of 6 times h bar. The z component is m sub L times h bar. Therefore, the value can be 0, plus minus h bar, or plus minus 2h bar. When m sub L is 0, the particle does not rotate about the z-axis. Therefore, its rotational energy is distributed to x and y axis only. And in summary, the magnitude of the angular momentum is this: the square root of L times L plus 1 h bar. Its z component is m sub L times h bar. This two can be determined at the same time. It's just because the angular momentum operator and the z component operator commute. The commutator is 0. They do commute. It's possible to determine both values exactly at the same time. Again, the degeneracy for L equals 2 is 5. The equation for degeneracy is 2L plus 1. And that's why there's 1 s orbital, 3 degenerate p orbitals, 5 degenerate d orbitals, 7 degenerate f orbitals. We can have 9 g orbitals and 11 h orbitals. If we're talking about the rotation of the electrons in an atom. But if you're considering the rotation of molecules, although we solve the same equation, we get the same solution, we have same interpretation, but instead of L, we use J as the quantum number for the angular momentum. And the z component is m sub j instead of m sub L. It's just the notation. When you see L and m sub L, we're talking about the rotation of electrons about the nucleus. When you see quantum numbers j and m sub j, that usually are used for the quantum rotation of molecules about the center of mass of the molecule. For example, if we're looking at the rotation of HCl, its rotational energy is J times J plus 1 times h bar squared over 2I. Well, J can be 0, 1, 2, 3, 4, etc. This I is the moment of inertia of the HCl molecule. Over here, it's just a simple diagram that shows you when L is 2, we can have 5 different degeneracies. Sorry about the typo here. The subscript should be 2. So this should be 2, this should be 2, this should be 2, this should be 2, this should be 2. The superscript is the value of m sub L. M sub L can be from -2, -1, 0, 1, and 2. If you look at the length of each vector, alright, these 5 vectors, they share the same length. The length is the square root of 6 times h bar. The physical meaning of this is the magnitude of the 3-dimensional angular momentum. And now you look at the 5 factors here, they have different z components. You have 2h bar, 1h bar, 0, negative 1h bar, and negative 2h bar. They correspond to m sub L being -2, -1, 0, 1, 2. So 5 vectors, same angular momentum, same rotational energy, with a degeneracy of 5. But they do have different z components. That means this 5 vectors correspond to 5 different values of m sub L. Chapter 16, Quantum Rotation, Section 16.5, the uncertainty principle for the 2-dimensional rotation. For the 2-dimensional rotation of a 2-particle rigid rotor with a constant radius r0, the angle operator theta and the angular momentum operator L do not commute. We can prove this angular momentum operator is simply negative IH bar delta over delta theta. We start from the Cartesian coordinates. When we apply L to an arbitrary function psi, it's equivalent to negative IH bar and then x delta over delta y minus y over delta x applied to psi. And x is written here, y is written here. This delta over delta y is equivalent to cosine theta r0 times delta over delta theta. this delta over delta x operator is equivalent to negative sine theta over r naught times delta over delta theta. We derived this in a previous section. Now x is r naught cosine theta, y is r naught sine theta. That's just the conversion from Cartesian to polar coordinates. And now we have the sum of these two. Cosine theta squared plus sine theta squared is 1. And therefore, when we apply the angular momentum operator to a function, we get negative IH bar delta psi over delta theta for the two-dimensional rotation. Now let's look at the commutator of the two operators, theta and L. So when we evaluate this, we need to apply the commutator to an arbitrary function f. The expression is theta LF minus L theta F. Alright, we just switch the orders of the two operations and take the difference. And L is negative IH bar d over d theta. Alright, so that's why I replace L with this operator. And again, this is the L operator. Alright, so we just need to evaluate this. Over here, this is straightforward. This is just the first derivative of f, or f prime. This one, we need to use the product rule. The result of this one is f plus theta times f prime. We clean up everything, we get IH bar times f. So this commutator of theta and L is equivalent to this operator. This is a very simple operator. It's IH bar. When you apply this operator to any function, it's equivalent to multiplying this function by IH bar. This is non-zero. That means the commutator of theta and L is non-zero. Theta and L do not commute. We cannot determine the exact value of theta and L at the same time. And we have this uncertainty principle similar to Heisenberg's uncertainty principle. Delta theta times delta L must be greater than or equal to 1/2 of H bar. In this expression, L denotes the magnitude of the angular momentum of the rotation, but not the quantum number. So over here, this L is in terms of H bar. Note that in quantum mechanics and quantum chemistry, we use the same letter L to denote the quantum number of the angular momentum, which is an integer, and also the magnitude of the angular momentum itself, which has a unit of joule times second. And also we know the magnitude of the angular momentum for a 2D rotation is LH bar. For 3D, it's the square root of L times L plus 1 times H bar. So this can be a little confusing. We have two different uses for this lowercase l. But later in quantum chemistry, we often say this H bar is one atomic unit of angular momentum. And in that case, L times H bar is equal to L in the atomic units. So at least at that point, we know why L can be used to denote both the quantum number and also the magnitude of angular momentum. Chapter 17, Quantum Vibration, Section 17.1, Classical Harmonic Oscillator. The potential energy of a harmonic oscillator is half kx squared. K is the force constant, and x is the displacement of the spring. So x is the actual length of the spring minus its natural length or equilibrium length. When x is 0, the potential energy V is set to 0. Hooke's law states that the force exerted to a spring is proportional to its displacement. F equals negative kx. We have a negative sign here because the direction of the force is the opposite to the direction of the displacement. And because F is equal to negative dV over dx, where V is the potential energy, and then we have dV over dx equals negative force equals kx. We can solve this differential equation. We get V equals 1/2 kx squared. Again, when x is 0, we choose to set the potential energy of the spring to 0. We now derive the vibrational frequency of this spring. So F equals ma, that's Newton's law. A is the second derivative of the length of the spring with respect to time. The equilibrium distance is independent of time. Therefore, force is equal to m times the second derivative of the displacement x with respect to t. And F is also negative kx. So now we have another differential equation. Again, this x is the displacement of the spring, or it's the relative position of the mass relative to the equilibrium position. X is not the absolute length of the spring. The absolute length, or the actual length of the spring, is the equilibrium length plus the displacement. The equilibrium length is also called the natural length of the spring, or the free length of the spring, when there's no force exerted on the spring. The differential equation of the motion of a harmonic oscillator is this. Really, it's just ma equals negative kx. Because force is equal to ma, force is equal to negative kx. We can reorganize this equation. We have the second derivative of x equals x multiplied by a constant, a negative constant. Well, this is really similar to the Schrödinger equation of a free particle. We can solve this equation. Two possible solutions are e to the power of plus I times the square root of k over mt. Another is e to the power of negative I square root k over m multiplied by t. Also similar to the solutions to a free particle. The general solution is a linear combination of these two solutions. So we have two coefficients here, c1 times e to the power of plus I square root of k over mt, and then c2 e to the power of negative I square root of k over mt. The square root of k over m is the angular frequency, omega. c1 and c2 are just constants. And because e to the power of I theta can be expressed as cosine theta plus I times sine theta, x can be expressed as a sine or cosine function of time, or the combination of these two. So x is a combination of a cosine function and a sine function of the square root of k over m multiplied by t. We can combine these two to form another sine function or cosine function. Here I'm showing a sine function. We just need to add an initial phase over here, alpha over here. So when time is 0, x is a times sine alpha. If we assume at time 0, there's no displacement, and alpha is 0 in that case. Again, alpha is the phase shift of the sine function. The square root of k over m is the angular frequency of the sine function. B1, B2, they are arbitrary constant. Therefore, this A is an arbitrary constant. The angular frequency is equal to 2 pi times the ordinary frequency, denoted by nu. So omega is 2 pi times nu. The ordinary frequency of the harmonic oscillator is therefore omega over 2 pi, or 1 over 2 pi times the square root of k over m. By looking at this equation, if we have a larger force constant, a smaller mass, we have a higher frequency, and of course a higher angular frequency. Because the sine function is periodic with regular intervals of 2 pi, the period of the oscillation t of this sine function is defined by this following equation. So if we increment time t by uppercase T, well, the difference should be 2 pi if we're looking at the adjacent crests or troughs. Solving this equation, we get this uppercase T, the period of oscillation. It's 2 pi times the square root of m over k, and x can be written as a sine function of 2 pi multiplied by time divided by the period, and then plus some phase shift. The reciprocal of the period of oscillation is the ordinary frequency. So we get this equation again. This nu is the reciprocal of 2 pi times the square root of m over k. So nu, the ordinary frequency, is 1 over 2 pi times the square root of k over m, and the angular frequency is 2 pi times the ordinary frequency. For a two-body harmonic oscillator, we can separate the relative motion of the two masses, considered as the harmonic oscillation, from the concerted translational motion of these two masses. We can then solve the equation for pure vibration. So the idea is to separate the translational motion of the two masses from their vibrational motion. The derivation of the frequency of the two-body oscillator is the same as that for one-body harmonic oscillator, except all occurrence of m needs to be replaced by the reduced mass, and in the end we have the ordinary frequency nu to be 1 over 2 pi times the square root of k over mu. 1 over mu is 1 over m1 plus 1 over m2. Mu is smaller than m1, mu is smaller than m2. The two-body system may undergo translation as well, and if we define this uppercase as the total mass, this v as the translational speed of the center of mass, and then we have this equation: m1 v1 plus m2 v2 equals uppercase mv. And again, this v is the velocity of the mass center. The uppercase m is m1 plus m2. This uppercase v, the velocity of the mass center, is m1 v1 plus m2 v2 over m1 plus m2. This v is just, I think, the mass weighted velocity. Alright, so you need to take the mass into account. The top, you have the momentum of mass 1, you have the momentum of mass 2. So in total, you have the momentum of the entire system. On the bottom, you have the mass of the entire system. And this uppercase v is the velocity of the entire system. We can prove the sum of the translational energy of the two-body system and the vibration energy of the two-body system is equal to the sum of the kinetic energies of the two separate bodies. So really, we want to prove this 1/2 mv squared. This is the translational energy of the two-body system. 1/2 mu times v2 minus v1 squared. This is the vibration energy of the two-body system. We want to prove the sum of this is equal to 1/2 m1 v1 squared plus 1/2 times m2 v2 squared. So this is kinetic energy of mass 1, kinetic energy of mass 2. When we sum them up, we get the total kinetic energy. Over here we have kinetic energy of the translation, kinetic energy of the vibration. We sum it up, we get the total energy. The derivation is simply just some algebraic operations. First, we replace the uppercase M with M1 plus M2. V is M1 V1 plus M2 V2 over M1 plus M2. So we have this expression, and we have the vibrational energy. So what we're gonna do is we try to simplify the expressions. For example, we have M1 plus M2 squared on the bottom, so we clean up a little bit. We get this expression on the left. Mu is M1 M2 over M1 plus M2. We have that on the right, and we see 1/2 is a common factor. 1 over M1 plus M2 is a common factor, and then we sum up everything. The first three terms come from this, and the last three terms come from M1 times M2 times V2 minus V1 squared. So you see M1 M2 here, M1 M2 here, and M1 M2 here. And then we clean up a little bit. We look for things that we can cancel. This term, 2 M1 V1 M2 V2, negative 2 M1 V1 M2 V2, they cancel. So we have only 4 terms left. And we can further separate these 4 terms. We find V1 squared, we'll put them here. We find V2 squared, we put them here. Now this divided by M1 plus M2, we get M1 V1 squared over here. And this divided by M1 plus M2, we get M2 V2 squared. So we proved that, well, the total kinetic energy of this two-body system can be done in 2 different ways. One is we can have the kinetic energy of M1, the kinetic energy of M2. We sum up these 2 values, we get the total kinetic energy. Another way is to look at the translational motion of the entire system and the vibrational motion of the entire system, and then we sum up the translational energy and the vibration energy. We also get the total kinetic energy. Chapter 17, Quantum Vibration, Section 17.2, Quantum Vibration of Harmonic Oscillators. The time-independent Schrödinger equation for the 2-particle harmonic oscillator is this: H psi equals E psi, and H psi equals the kinetic energy operator applied to psi plus the potential energy operator applied to psi. The potential energy is half kx squared, as stated in Hooke's law. Now kinetic energy operator, it's negative h bar squared over 2 mu d squared over dx squared. Mu is the reduced mass. 1 over mu equals 1 over m1 plus 1 over m2. We can also take the reciprocals of both sides. The mu is equal to m1 times m2 divided by m1 plus m2. The solutions for this Schrödinger equation is this. It's fairly complicated. We have many solutions. This n can be 0, 1, 2, 3, 4, 5, etc. A sub n is the normalization factor, and h stands for a Hermite polynomial function. Over here we have a Hermite polynomial function of square root of alpha times x. Now what is alpha? Alpha is the square root of k mu over h bar. We also have a Gaussian function e to the power of negative alpha x squared over 2. So this Hermite polynomial function takes the form of negative 1 to the power of n e to the power of x squared, and then the derivatives of e to the power of negative x squared. This n can be 0, 1, 2, 3, 4, etc. And over here we just plug in the corresponding value of n here and here. So now let's look at one example. When n is 0, that's simple. We have negative 1 to the power of 0, and then e times e to the power of x squared. And over here it's d0 over dx0. So this is simply doing nothing. and then doing nothing to e to the power of negative x squared is itself. So this and this cancel, we have just 1. So this H0 Hermite polynomial function is simply 1. Now what if n equals 1? When n is 1, we have negative 1 to the power of 1, we have e to the power of x squared. We take the first derivative of e to the power of negative x squared. That's negative 2x times this Gaussian function. The final result is 2x. What if n equals 2? We have negative 1 to the power of 2, and then e to the power of x squared, and then the second derivative of the Gaussian function. The second derivative of the Gaussian function is simply the first derivative of the first derivative. Alright, we can just take the first derivative of negative 2x, which is negative 2 here. We can take the derivative of e to the power of negative x squared. Again, we get negative 2x times this Gaussian function, and negative 2x times negative 2x, we get 4x squared. Alright, so and then this and this cancel, so in the end we have 4x squared minus 2. So you can see h sub 0 is the 0th order polynomial function, h sub 1 first order, h sub 2 second order polynomial function, h sub 3, h sub 4 will be the 3rd and 4th order of polynomial function. It's just we need to kind of determine the derivatives of a Gaussian function and do some multiplication. That's it. The wave functions of the harmonic oscillators take this kind of form: a normalization factor, a Hermite polynomial function of not just x but the square root of alpha times x, and then a Gaussian function here. Alpha is the square root of k mu over h bar. Alpha is just defined that way to simplify the expression. And a is the normalization factor. A takes this kind of form. A is 1 over the square root of 2 to the power of n factorial, and alpha over pi to the power of 1 over 4. We can prove a sub n is equal to this, but it's extremely tedious. To prove this, we just make sure that the integral of the square modulus of psi is 100% over the entire space. H sub n is the nth order Hermite polynomial function, so we have the form of a Hermite function like this. And then if we have a Hermite function of not just x but the square root of alpha times x, well, h sub 0 is 1, h sub 1 is now 2 times the square root of alpha times x, h sub 2 is now 4 alpha x squared minus 2. The first 3 wave functions of the harmonic oscillators are thus here, here, and here. They are just a normalization factor multiplied by the Hermite polynomial functions multiplied by this same Gaussian function. Now we're going to look at some normalized wave functions for the harmonic oscillator. Again, the wave functions take this kind of form, and if we normalize those functions, we obtain the expression of a sub n. So over here, when n is 0, the ground vibrational energy, we have the normalization factor to be alpha over pi to the power 1 fourth, and the Hermite function is just 1, and then we copy the Gaussian function here. And now, what if a equals 1? Well, again, we're gonna get more and more complex expressions, because the Hermite polynomial function now takes an order of 1, an order of 2, an order of 3, etc. And also you can see the normalization factors are fairly complicated, but usually determining the values of normalization factors is tedious but not very important, because if you want to determine the physical property given a wave function, the normalization factor does not play a role. Alright, now let's just look at the shapes of those wave functions. First, psi of 0. Psi of 0 takes this kind of shape. It's just a Gaussian function. just typical Gaussian distribution. Now let's look at the shape of psi sub 1, the first excited vibrational energy. Alright, you see there's a node in the middle. Why? Because you see this x here. When x equals 0, we have a node. Psi of 2, we have two nodes, one here, one here. Why two nodes? Well, we can set this polynomial function to 0. Then we get two roots. Over here we can see when x squared is equal to 1 over 2 alpha, we have positive and negative square root of 1 over 2 alpha, two roots. Psi of 3, three nodes. Why is that? Look at this. The first node is when x is 0. Alright, and then two other roots, they correspond to plus minus the square root of 3 over 2 alpha. Alright, so I think they are here and here, three roots. And of course, when n increases, we get more and more nodes. When n is 4, we see 1, 2, 3, 4, and then n includes 5, 1, 2, 3, 4, 5 nodes. As the quantum number increases, the number of nodes increases as well. 0 nodes, 1 node, 2 nodes, 3 nodes, 4 nodes, 5 nodes, 6 nodes, 7 nodes. And also, if you just look at the shape closely, don't they look like the wave functions of a particle in the box? It's like a sine function, you know, the first sine function, the second sine function with a node, the third sine function with two nodes, and then 4. So this one looks like a sine function, right? So with two wavelengths, you have one wavelength here, another wavelength here, remember? So they do look similar to each other, because if you think about it, if you examine the Schrodinger equation of the harmonic oscillator, if you examine the shape of this potential energy, it's almost just like an energy barrier, right? Energy barrier. You have a particle confined by this barrier. Well, there are two differences. One, this barrier is not a infinite energy barrier, and also this barrier is curvy. When you have a particle in the box, it's like just a vertical line on the left, a vertical line on the right. So two differences, but both are like particles confined within barriers. So it's not a surprise they have similar shapes. Alright, let's get back to the vibrational energy. It turns out the vibrational energy is n plus 1/2 times h nu. So when n is 0, that's so-called 0 point vibration energy. The lowest possible vibration energy is 1/2 h nu. And when n equals 1, we have 3 halves. When n equals 2, 5 halves. When n equals 3, we have 7 halves h nu vibrational energy. So energy goes up, and we take this kind of form. The time-independent Schrodinger equation for the two-particle harmonic oscillator is h psi equals E psi. H is kinetic energy operator plus potential energy operator. In the ground vibrational state, we have a ground vibrational wave function, which is a Gaussian function here. A is the normalization factor, alpha is the square root of k mu over h bar. Now we'll just prove this. We'll apply this Hamiltonian to this wave function, and hopefully we'll get the corresponding vibrational energy multiplied by the wave function. So we'll do this. It's completely mathematics. I'm applying the kinetic energy operator to the wave function here, potential energy operator to the wave function. Alright, here we take the second derivative of a Gaussian function. It's the first derivative of the first derivative. So I'm taking this normalization factor out for simplicity, and I'm going to take the first derivative of this Gaussian function using chain rule. It's negative alpha x times the Gaussian function. So over here, this part is easy. I'll just copy that here. Now I'm gonna take negative alpha out, and we got a times alpha h bar squared over 2 mu. And then we'll take the first derivative of this. I copied the kinetic energy part here. Now what's the derivative of this one? Product rule in calculus. The derivative of x is just 1, so 1 times this Gaussian function here. What's the first derivative of this Gaussian function? We use chain rule. It's negative alpha x times this Gaussian function. There's another x, so it's negative alpha x squared. So we have this expression. We copy the kinetic potential energy term here. And now finally we need to plug in the expression of alpha. Alpha is the square root of k mu over h bar, so this is alpha. Alright, and we just replace this with square root of k mu over h bar. Alright, so we expand 1, 2, 3 terms here, here, and here. We do need to clean up a little. You see this mu here and mu here, they partially cancel, and we have h bar squared over h bar partially cancel. Over here we have k and mu on top and mu on the bottom, so we have a k left. We have h bar squared and h bar squared on the bottom, so we cancel. We do all those cancellation or other simplification. We get this expression of 3 terms. Apparently the second term and the third term cancel. Only the first term here, and I'll just copy that to here, and we can express this as 1/2 h bar times the square root of k over mu, and then multiply by the wave function. And again, 1/2 h bar times the square root of k over mu. Well, it's actually 1/2 h nu, or you can say it's 1/2 h bar times the angular frequency. Alright, the angular frequency is 2 pi times the ordinary frequency nu. So over here, chemists usually write 1/2 h nu. Physicists usually write 1/2 h bar times omega. So, but they are the same. 1/2 h nu equals 1/2 h bar omega. Nu is 1 over 2 pi times the square root of k over mu. The angular frequency is just the square root of k over mu. The time independent Schrodinger equation for the 2-particle harmonic oscillator is this. We verified that this is the eigenfunction, and A is the normalization factor, alpha is defined to be the square root of k mu over h bar for convenience, and we have derived the 0 point or lowest possible vibrational energy, which is 1/2 h nu. On the previous page, nu is 1/2 over 2 pi square root of k over mu. Again, this is also 1/2 h bar omega, where omega is 2 pi times h nu, and h bar is h over 2 pi. Given the wave function, we can always compute the expectation value of its physical properties. Now let's compute the expectation value of the potential energy and kinetic energy, or sometimes for simplicity we just say average potential energy and average kinetic energy. We resort to quantum mechanical postulate 4, which is this. This is the average property, and we have 2 integrals, one on the top, one on the bottom. They look similar, except this psi should be O psi on top. O psi is the O operator applied to psi. So we can do the calculation for the average potential energy. We have the wave functions on the bottom, the wave functions on top, and then this is potential energy applied to wave function. A and A cancel, A and A cancel. We do some simplification. We take 1/2 k out. Really, it's just the division between the two integrals. On top you have x squared here, multiplied by the Gaussian function. On the bottom, you just have this Gaussian function. So after you do this, you get something in terms of alpha, and then you combine half k with alpha. You will end up with a quarter h nu. And again, alpha is defined to be the square root of k mu over h bar. What about kinetic energy? You can just apply the kinetic energy operator over here to the wave function. So on top, it has to be the operator applied to the wave function here. Alright, and then on the bottom it's just the wave function. Here it's just wave function, wave function. This is non-trivial, so I'm gonna just neglect all those steps. You'll get 1/4 h nu as well. So the vibration energy is 1/2 h nu. It's evenly distributed to the potential energy and the kinetic energy. They all have 1/4 h nu on average. Again, this is just the average value. Can we determine the exact potential energy? No. Can we determine the exact kinetic energy? No. It's just this wave function is not an eigenfunction of the kinetic energy operator, not the eigenfunction of the potential energy operator either. So there's no way to determine the exact value of the potential energy or the kinetic energy. But we can determine the sum, which is 1/2 h nu. We can determine the average potential energy, which is 1/4 h nu. And actually, the average kinetic energy is simply the sum minus this average. We get 1/4 as well. Now let's look at one more solution. Let's look at the first excited state with such wave function. We have one additional polynomial function x here, first order, and then multiplied by the Gaussian function. Alpha is the square root of k mu over h bar. Again, we apply the kinetic energy operator to the Gaussian function, potential energy operator to the Gaussian function. The math is more tedious. You just take the second derivative of this whole thing. We need to use the product rule already over here, and this is a potential term. Second derivative, even more complicated, but we can do it. We combine, x squared and x over here, and now we have 1, 2, 3 terms. We can just kind of expand them and do some simplification. And over here we have another term over here. And in the end, if you just clean up everything carefully, I think you will just get something like this. In the end, it's going to be 1/2 h nu multiplied by the wave function. Sorry about this kind of mathematical derivation. It's really tedious. Honestly, I often use Wolfram Alpha to do those kind of derivation for myself. We get the eigenvalue, which is 1.5 h nu. Nu is 1/2 pi times the square root of k over mu. Again, you can rewrite this as 3/2 h bar times omega. H bar is h over 2 pi. Omega is nu times 2 pi. So it's just the different flavors. This is more like chemist's flavor, and if you use h bar times omega, more like physicists. Now we're going to talk about the tunneling effect, because you can see there is indeed a energy barrier. The potential energy is 1/2 kx squared. So if the total energy is smaller than the potential energy, supposedly we'll get a negative kinetic energy, and that's classically forbidden. However, we observe quantum tunneling effect as well. We observe the vibration may exceed the classical region. So when does that happen? Obviously when the total energy is less than the potential energy, and the total energy is n plus 1/2 h nu. So when this is less than 1/2 kx squared, you have the so-called classically forbidden region. theoretically the tunneling effect is just non-zero as long as this x is finite. Let's look at one example. The simplest example is the ground vibrational state. Alright, and then the total energy is simply 1/2 h nu, that's it. And then when the potential energy is greater than the total energy 1/2 h nu, we have a negative kinetic energy, and that's called quantum tunneling. It's in the classically forbidden region. We can even solve this. We can see x is greater than the square root of h nu over k, and also you can rewrite this as the square root of h bar over the square root of k mu. Why did I write this? Well, it happens that this is the reciprocal of alpha. Alpha is defined to be the square root of k mu over h bar. So when the value of x is greater than alpha to the power of negative 1/2, we see tunneling effect in the classically forbidden region. All right. So the spring is overly stretched. So again, over here you can see that these displacement can stretch actually over a very long range, and if you have a higher energy, the tunneling effect is even more significant. All right. So this is probably less significant than this. All right, we have more significant tunneling effect if you have a larger energy. All right, if you have a larger energy. Chapter 17, Quantum Vibration. Section 17.3, Quantum Vibration of Polyatomic Molecules. A polyatomic molecule contains 3 or more atoms. In general, if a molecule contains n atoms, it has 3n atomic coordinates because each atom has 3 coordinates x, y, and z. So this molecule has 3n atomic coordinates, and thereby 3n independent motions, because each atom has 3 independent motions in the x, y, and z directions. Now let's look at nonlinear molecules versus linear molecules. A nonlinear molecule has 3 translational modes in the x, y, z directions, and also 3 rotational modes about the x, y, and z axis. So for example, if you have a water molecule, let's say this is the z axis, and then we can draw another x axis and then another y axis perpendicular to the screen. So 3 rotational axes, 3 rotational motions. And we know in total there should be 3n motions. So 3n minus 3 translations minus 3 rotations. Well, a nonlinear molecule should have 3n minus 6 vibrational modes. For example, water. Water consists of 3 atoms. 3 times 3, we have 9 motions. 9 motions minus 3 translations minus 3 rotations, we have 3 vibrations. And you are looking at the 3 vibrations. This is the so-called anti-symmetric stretching, because over here, when this bond is stretched, this bond is compressed. They are opposite to each other. Over here, it's symmetric stretching. Both bonds are stretched or compressed at the same time. There's another scissoring bending. So you can call this bending as well. We're just changing the bond angle here. All 3 are vibrational modes of water. Now let's look at a linear molecule. If you have a linear molecule, still there are 3 translational motions, but only 2 rotational motions, because there are only 2 rotational axes. Let's look at CO2 as an example. Again, this CO2 may rotate about 2 of the 3 rotational axes. The last one, the molecular axis, does not count. This CO2 does not rotate about its own molecular axis. And therefore, if you have a linear molecule, again, the molecular axis does not count. So you have only 2 rotational axes or 2 rotational modes. And because of that, we use 3n minus 3 translation minus 2 rotation. We have 3n minus 5 vibrational modes, 1 more than the number of vibration modes of a nonlinear molecule. So now let's look at CO2. CO2 has 3 atoms, therefore 9 motions, minus 3 translations, 2 rotations. We have 4 vibrational modes. We have symmetric stretching, anti-symmetric stretching, and we have 2 bending motions. In these 2 vibrations, the bond angle, OCO bond angle, changes, but they are changing in different planes. So one is on this plane, the plane of the screen, and this motion is actually taking place in a plane perpendicular to the screen. Alright, I have to let you imagine this is actually a 3-dimensional animation, and the CO2 bending takes place on a plane that is perpendicular to the surface of the screen. This one is just in the screen. Again, this is the just the water molecule of 3 atoms and 9 motions, minus 3 translations, minus 3 rotations. We have 3 vibrations, anti-symmetric stretching, symmetric stretching, and bending. So bending is somewhere here. All these are bending, and then we have stretching here. I think anti-symmetric stretching has a slightly larger wave number than symmetric stretching over here. Yeah, the numbers are here. This is slightly larger than this, and we have scissoring bending over here. Those are the wave numbers from the NIST website. But if you really look at this infrared spectrum of water, you can see it's not as clean as we expected. We see a lot more than 3 peaks. So why so many peaks over here? Well, I just want to remind you, other than the vibrational motion, a water molecule may have rotational motions. So a water molecule may absorb a photon with energy to excite its vibration and also its rotation. And even more complicated, a water molecule might be in the rotational excited energy level in the first place. And when such a water molecule absorbs a photon, well, it can be vibrational excited and rotational de-excited at the same time. So that's why we have all different kind of situations regarding the rotational excitation or rotational de-excitation accompanying the vibrational transition. That's why the infrared spectrum of just water vapor can look so complicated with many peaks. But all this correspond to the vibrational excitation of the bending mode, and I think of this correspond to the symmetric stretching, and of this correspond to the anti-symmetric stretching. Why so many peaks? Well, the vibrational transition is accompanied by rotational excitation or rotational de-excitation. Chapter 17, Quantum Vibration, Section 17.4, Anharmonic Oscillators. Diatomic molecules are approximately harmonic oscillators when the oscillating bond distance is close to the equilibrium bond distance. So if you look at this graph, this is the potential energy versus the bond distance. So when the displacement is small, we have the bond distance very close to the equilibrium bond distance. And when that happens, we can use the harmonic potential to describe the bond. But what if the bond is overly stretched, for example, to here, somewhere here, and then you can see the blue curve is the actual potential energy. It's here, but then if you look at the green curve, it shoots all the way up, so there's a huge deviation when the bond distance is overly stretched. What if the bond is compressed? Well, same thing. You can see Well, now the green curve is far below the blue curve. So again, if we have a bond distance very close to the equilibrium bond distance, we can assume this chemical bond is a harmonic oscillator. Otherwise, you have to use a different equation to calculate its potential energy. And in this case, we usually use Moore's potential to describe the potential energy of such an anharmonic oscillator when the bond distance is quite different from the equilibrium bond distance. The equation is this. This is Moore's potential. The potential energy is a parameter d sub e times 1 minus e to the power of negative ax squared. What is d sub e? Now let's look at the blue curve. This is a realistic potential energy of a real chemical bond. You can see when R increases, the potential energy levels off to a certain level, the dashed line. So d sub e is the difference between this dashed line when the potential energy levels off and the bottom line over here. This is the distance between these two. That's the physical meaning of d sub e, and d sub e is the so-called depth of the potential energy well. So again, this blue curve is a potential energy well, and we determine this depth of the well, that's d sub e. A is another parameter. So again, you can see the blue curve and the green curve definitely are different, but they match each other when the displacement is small, when the bond distance is close to R sub e, the equilibrium bond distance. Alright, so let's prove this. When the displacement is small, the potential energy of the oscillator does exhibit the harmonic behavior. Why? We need to know the Taylor expansion of exponential function. Let's say you have exponential function e to the power of delta. Its Taylor expansion is 1 plus delta squared over 2 factorial plus delta to the power of 3 over 3 factorial plus delta to the power of 4 over 4 factorial, etc. Now, if delta is really small, we can neglect all those higher order terms. We can say e to the power of delta is approximately 1 plus delta. You can verify this yourself. E to the power of 0.1 is roughly 1.1. E to the power of 0.02 is roughly 1.02, etc. So we're going to use this Taylor expansion, assuming x is very, very small, then ax is also small, and then e to the power of negative ax is approximately 1 minus ax. Now let's look at this Moore's potential. I'm about to replace e to the power of negative ax with its truncation, 1 minus ax, of its Taylor expansion. 1 and 1 cancel, so we have a squared x squared times dE. So you can see this Moore's potential is proportional to the displacement squared when the displacement is small. Also, if you look at the harmonic potential, it's proportional to x squared as well. Compare this expression from Moore's potential, this expression from the harmonic potential. We see dE times a squared is 1/2 of k. K is 2 times d sub e a squared. The first constant k is approximately proportional to the depth of the energy well, d sub e. Now in this graph, you also see d sub 0. It looks like d sub e, but there's a small difference. This small difference is the so-called 0-point vibrational energy, or the lowest possible vibrational energy. And why is that? Well, actually, this d sub 0 has a physical meaning. D sub 0 is the bond energy of this diatomic molecule at 0K. And why is d sub 0 smaller than d sub e? Well, this is just because even at 0K, this molecule has a positive vibrational energy. That's the 0-point vibrational energy, or lowest possible vibrational energy. If you have a harmonic oscillator, it's half h nu. If you have a enharmonic oscillator, it's slightly smaller than 1/2 h nu. But nonetheless, we have some vibrational energy to start with. That's why when you break a chemical bond, you do not need a some external energy of dE. You just need the amount of d0 because this molecule has already have this much vibrational energy. When the Morse potential is used to describe the potential energy of the enharmonic oscillator, the vibration is less confined when the bond is stretched or overly stretched. Let's look at this potential energy surface again. So when this bond is severely stretched, for example over here, you can see the potential energy curve starts to level off. So this vibration is less confined, or the two particles are less confined compared to the harmonic oscillator. When you see this harmonic oscillator, the potential energy is half kx squared. Half kx squared approaches infinity when x approaches infinity. Now if you look at the real chemical bond, when x approaches infinity, well, the barrier actually levels off. That means the particle becomes less confined when its vibrational energy keeps increasing. However, when the barrier starts to level off, the particles are less confined. That means the energy spacing gets smaller. Remember in the chapter on quantum translation, we talked about quantum confinement. When a particle is more confined, the energy spacing is larger. When the particle is less confined, the energy spacing is smaller. When the particle is free, that means not confined at all, the energy spacings become zero. The particle is completely free, and then its energy can be continuous. Now let's look at the vibrational energy levels. When we use the Morse potential, we have a different expression for the vibrational energy. So it's going to be the harmonic vibrational energy minus a correction. The harmonic vibrational energy is n plus half times h nu. The correction is negative, it's minus n plus half squared times h nu times a parameter chi e. Chi e is usually small, it's usually between 0.01 and 0.05 for most diatomic molecules. And it's a negative correction. That means when A increases, well, we have more and more negative correction over here. And we will see that the energy spacing gets smaller when n increases. Again, chi sub e is just a parameter, it's a constant, it's the enharmonic constant, it's usually small. We can plug in the values of n can be 0, 1, 2, 3, 4, etc. When n is 0, the vibrational energy of the enharmonic oscillator is this, it's 0.5 h nu minus a quarter h nu chi e. When n is 1, n plus 1 half is 1.5. Now we square it over here for the correction. It's 2.25 h nu chi e. When n is 2, we have 2.5 h nu minus 6.25 h nu chi e. Now let's examine the energy spacing between two adjacent vibrational energy levels for a enharmonic oscillator. So it's going to be E of n plus 1 minus E of n. This is when n plus 1 is the quantum number, when n plus 1 is the quantum number, versus when n is the quantum number. We take the difference between this n plus 1 energy level and this n energy level. Alright, we just take the difference between the first term and the third term. They differ by 1 h nu. Alright, again, the first term, the third term differ by 1 h nu. Now we compare the second term and the fourth term. Well, they differ by this much. Obviously, we need to copy h nu chi e here, so really it's just n plus 1.5 squared minus n plus 0.5 squared. The difference is 2 times n plus 1. We have a negative sign here. Now you can see this is the energy spacing between E of n plus 1 and E of m. So when do we observe the bond breaking? Well, when the bond breaks, the particles are no longer confined, right? You have just two separate particles. When you have two separate particles, they are no longer confined. The energy spacing, the vibrational energy spacing should be 0. So we can simply set this to 0 and solve for n. and chi is usually much smaller than 1. Chi is usually between 0.01 and 0.05 for most diatomic molecules. So we can just simply compute the value of n given this chi. So if you do know the value of the enharmonic constant chi for a diatomic molecule, you know when this chemical bond will break. So you just set this to 0. H nu and H nu cancel. So the bond breaks when 2 times n plus 1 times chi is 1. So we can plug in two values. What if chi is 0.01? So we can plug it in here. When does this become 0? Well, when 2 times n plus 1 times 0.01 is 1. Alright, that means when 2 times n plus 1 is 100. That means when n is 49, the bond breaks. What if chi is 0.05? Also, we plug it in. So when 2 times n plus 1 times 0.05 is 1. That means when n equals 9, the bond breaks. So for typical diatomic molecules, the chemical bond breaks when n is usually a value between 9 and 49. I'm assuming this chi is between 0.01 and 0.05. You can use the NIST website to look up the value of chi for many diatomic molecules. Alright. And again, I just want to emphasize this is fairly important. When the two particles are more confined, you have a larger energy spacing. When the two oscillating particles are less confined, you have a smaller vibrational energy spacing. When the two particles are not confined at all, that means the bond breaks. You should have an energy spacing of 0. So you can use this equation, set it to just 0, to calculate the value of the vibrational quantum number n when the bond breaks. Chapter 18. Rotational and vibrational transitions of molecules. Section 18.1. Rotational transition. The three-dimensional rotational energy of a two-body system is L times L plus 1 times h bar squared over 2I. L is the rotational quantum number. L can be 0, 1, 2, 3, 4, etc. I equals mu r squared. I is the moment of inertia. Mu is the reduced mass. The magnitude of the angular momentum of the 3D rotation is the square root of L times L plus 1 times h bar. The z component of the angular momentum is m sub L times h bar. M sub L is negative L plus 1, negative L plus 2, etc. all the way to L. Therefore, we have a degeneracy of 2L plus 1. The selection rule for the rotational transition is that L must change by 1 in a photon-induced rotational transition. So L can increase by 1 or decrease by 1. This is to ensure the conservation of the angular momentum, because a photon carries a spin angular momentum of h bar or negative h bar in the direction of the light path. As the molecule absorbs a photon, it inherits not only the energy of the photon, but also the angular momentum of the photon. There are two types of rotational transitions. Rotational excitation, in which L increases by 1, and rotational de-excitation, in which L decreases by 1. In the rotational excitation, the energy change is positive. We can take the difference between the two energy levels, from level L to level L plus 1, the difference is L plus 1 times h bar squared over I. In a rotational de-excitation, the energy decreases. Again, we can compare the difference between the two energy levels between L and L plus 1. The rotational energy change is negative L plus 1 times h bar squared over I. The angular momentum quantum number for molecules is denoted by J instead of L by convention. So when we are talking about the rotational energy of a molecule, a diatomic molecule, it's J times J plus 1 times h bar squared over 2I. J can be 0, 1, 2, 3, 4, etc. For convenience, we often define a rotational constant B in meter to the power of negative 1 or centimeter to the power of 1 this way. We define HCB equals h bar squared over 2I. So B can be expressed as h bar squared over 2hci or h over 8 pi squared ci. So B is also called in wave numbers. B is the wave numbers of the rotation. The three-dimensional rotational energy of a diatomic molecule can be expressed as J times J plus 1 times HCB. Again, B has a unit of wave numbers. The rotational constant B again is defined to be HCB equals h bar squared over 2I. Therefore, the three-dimensional rotational energy of a diatomic molecule is J times J plus 1 times HCB. When we are looking at a rotational excitation from J to J plus 1, the energy increases by this much, 2 times J plus 1 times HCB. In a rotational de-excitation from J plus 1 to J, the energy change is negative 2 times J plus 1 times HCB. The value of B can be calculated for a diatomic molecule given its bond distance and reduced mass. Taking hydrogen chloride as an example, the equilibrium bond distance is 1.275 angstroms, and we have the mass of a hydrogen atom and the mass of a chlorine atom. First, we can compute mu in terms of AMU. Mu is M1 times M2 over M1 plus M2, and we convert AMU to kilogram. 1.63 times 10 to the power negative 27 kilogram. Now we can compute the moment of inertia mu r squared. We plug in the value of mu and the bond distance. We get the moment of inertia for HCl 35, which is 2.644 times 10 to the power negative 47 kilogram meter squared. Now B is h bar squared over 2hci. This comes from the definition of the rotational constant B. B is defined this way: HCB is h bar squared over 2I, and therefore B is h bar squared over 2hci. We have the expression of B over here because h bar is h over 2 pi. We plug in all the values, we get the value of B, which is 1059 waves per meter. Sometimes we use centimeter to the power of 1 as the unit. Then B is 10.6 waves per centimeter. The physical meaning is this: within 1 centimeter we can fit in 10.6 such waves. Of course, within 1 meter we can fit in 1059 such waves. By convention, L is used as the rotational quantum number of electrons. J is used as the rotational quantum number of molecules. Molecules occupy various rotational energy levels at room temperature. The occupation number assumes the Boltzmann distribution. The occupation numbers are simply the number of molecules in various energy levels. So N sub j is proportional to 2j plus 1 times e to the power of rotational energy over kBt. Why 2j plus 1? That's just the degeneracy of the jth rotational energy level. Again, it's just because m sub j can be from negative j to j. M sub j can have 2j plus 1 different values. So with this taken into account, the number of molecules occupying the jth rotational energy level should be proportional to this degeneracy and also to e to the power of negative kinetic energy, in this case rotational energy over kBt. The rotational energy is J times J plus 1 times hCb. K sub b is the Boltzmann constant. K sub b is R over Avogadro constant. K sub b is 1.38 times 10 to the power of negative 23 joule per Kelvin. Taking HCl35 as example, B is 1059 waves per meter. Now we compute hCb over kBt. Plugging on the numbers at room temperature, we get 0.051. And now N sub j is proportional to 2 times j plus 1 times e to the power of negative j times j plus 1 times hCb over kBt. When j is 0, 2j plus 1 is 1, and over here the rotational energy is 0, so this exponential function is 1. N sub 0 is proportional to 1. N sub 1 is proportional to 3 times e to the power of negative rotational energy over kBt. Here j equals 1, so on top we have 1 times 2 times hCb, and hCb over kBt is 0.051, so we can plug in that number here. We say N sub 1 is proportional to 2.7. What does that mean? That means N sub 1 over N sub 0 is equal to 2.7 over 1. Now let's look at N sub 2. The j value is 2, so the degeneracy is 5, multiplied by e to the power of negative rotational energy over kBt. The rotational energy is j times j plus 1 times hCb. So after we plug in on the numbers, we get 3.68. When j is 3, we get 3.79, and when j is 4, we get 3.24. So you can see from N0 all the way to N3, the occupation number keeps increasing. The relative occupation number goes up from 1 to 2.7, 3.7, 3.8, but then it drops to 3.2 when j equals 4. So if you look at HCl molecules at room temperature, I think more molecules occupy this third, this j equals 3 rotational energy level than any other rotational energy levels. Again, taking HCl 35 as example, B is 1059 waves per meter, or 10.59 per centimeter. So hCb over kBt equals 0.051 by numerical calculation. We can compute the relative occupation number, which is expressed as N sub j over N sub j equals 0. And this is equal to 2j plus 1 times e to the power of negative rotational energy over kBt. So we have this expression. Once we have this expression, it's very convenient to use Excel to use this equation and plug in the value of j from 0 to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now we plot this n sub j over n sub 0, the relative occupation numbers from j equals 0 to j equals 1, j equals 2, j equals 3. You can see at first the relative occupation numbers increase as j increases, but after n equals 3, after j equals 3, well, it starts to decrease. The reason is because we have this exponential term here. When j is really large, this exponential function becomes really small. Given n sub j over n sub 0 equals 2j plus 1 times e to the power of negative rotational energy over kBt, we can maximize this function. To maximize or minimize a function, we simply take the first derivative of the function and set the first derivative 0. That's what I'm doing right here. I'm taking the first derivative of this function of the relative occupation number, and we get this derivative. This has to be 0, and therefore 2 has to be equal to 2j plus 1 squared times hb over kBt. And we set this to be 0 again. 2j plus 1 is the square root of 2 times kBt over hcb, and j is simply the square root of 2 kBt over hcb minus 1, and then divided by 2. Remember, we calculated hcb over kBt for HCl 35 at room temperature. The value is 0.051. So we plug in that value, we got this equation. We calculate the value of j sub max, which corresponds to the maximum occupation number. We found it to be 2.63. So if we're looking at a continuous function of this, well, the maximum is 2.63, so somewhere here. And no wonder we see this nj over n naught reaches the maximum at n equals 3, and it's close to the maximum when the value of j is 2. So this is our calculation. We got 2.63, so it's not surprising over here on this graph we achieve the maximum occupation number when j is 3. If you round up 2.63, it's 3. Chapter 18, Rotational and Vibrational Transitions of Molecules. Section 18.2, Vibrational Transition. The vibrational energy of a harmonic oscillator is n plus half times h nu, where n is 0, 1, 2, 3, 4, etc. The selection rule for the vibrational transition of a harmonic oscillator is that n must change by 1 in a photon-induced vibrational transition. This is because a photon consists of an oscillating electric field and an oscillating magnetic field. Well, its oscillating electric field combined with the vibration of a molecule, a diatomic molecule with a dipole moment, will cause the coupling between the electric field generated by the oscillating dipole and the oscillating electric field of the photon. That's why this quantum number n has to change when the vibrating molecule absorbs a photon. There are two types of vibrational transitions: excitation or de-excitation. In excitation, it increases. In de-excitation, it decreases. In the n to n plus 1 vibrational excitation, the energy change is positive h nu. In the n plus 1 to n vibrational de-excitation, the energy change is negative h nu. For convenience, we often define a vibrational wave number omega. omega is nu over c. This omega is different from that omega for angular frequency. So very often we use the same letter for different meanings. Again, this omega here means vibrational wave number. It's nu over c. C is the speed of light. Now let's take the experimental data of hydrogen chlorine 35 as an example. We have omega equals 2,884 per centimeter. That means within 1 centimeter we can fit in 2,884 such waves. We can compute the frequency nu using the equation nu equals omega c. So we have the value of omega, we have the value of the speed of light. We get the frequency 8.6 times 10 to the power of 13 hertz. In the n to n plus 1 vibrational transition, delta E is h nu. We plug in all the numbers, we get 5.7 times 10 to the power of negative 20 joule. So from this level n to this level n plus 1, well, the molecule will need to absorb a photon with this much energy. In the n plus 1 to n vibrational de-excitation, which is extremely rare because nearly all HCl molecules are in the lowest vibrational energy level, but if that happens, delta E is negative h nu. For example, if we're looking at the vibrational de-excitation of HCl35 from n equals 1 to n equals 0, and then, well, delta E is negative 5.7 times 10 to the power of negative 20 joule. A photon can be emitted in such vibrational de-excitation. Again, this is rare because at room temperature, most HCl molecules occupy the lowest vibrational energy level. That means n equals 0. You cannot further reduce 0 for the vibrational quantum number. In the vibrational excitation, again, the change of energy is h nu. We can compute this, and also we can calculate this delta E over kBT. So this is the energy difference between level n and the level n plus 1. Divided by kBT, we plug in all the values, we get 13.92. Molecules may occupy various vibrational energy levels, but mostly the n equals 0 level at room temperature or at a temperature close to the room temperature. The occupation numbers assume the Boltzmann distribution. We have the equation here. So the occupation number of energy level n is proportional to e to the power of negative vibrational energy over kBT. So if we have this relative occupation number, the occupation number of level n versus the occupation number of level 0, we can just plug in the expression here and here. Well, the division results in e to the power of negative n h nu over kBT. This is usually much smaller than 1, and that means, well, most molecules occupy the lowest possible vibrational energy level with n equals 0. Taking the room temperature HCl as example, n sub 1 over n sub 0, the relative occupation number is e to the power of negative h nu over kBT. Again, this is just e to the power of negative vibrational energy over kBT. We pre-calculated this h nu over kBT. It's about 14. So we have e to the power of negative 14. That's less than 1 times 10 to the power of negative 6. That means less than 1 out of 1 million HCl molecules occupy the n equals 1 vibrational energy level at room temperature. We can also compute n sub 2 over n sub 0. This is even smaller. This is less than 1 out of a trillion. Alright, so by looking at those ratios, we know more than 99.9999% of HCl molecules occupy the n equals 0 level at room temperature. And that means we usually observe the vibrational excitation of HCl from level 0 to level 1, but it's extremely rare to observe the vibrational de-excitation from n equals 1 to n equals 0 because we don't have many HCl molecules in the n equals 1 energy level in the first place. Chapter 18. Rotational and vibrational transitions of molecules. Section 18.3. Infrared spectra of rigid rotors and harmonic oscillators. When a diatomic molecule such as HCl absorbs a photon, the molecule undergoes the rotational transition and the vibrational transition simultaneously. For the rotational transition, delta J must be plus minus 1. For the vibrational transition, delta N must be plus 1. J has to change due to the angular momentum of the photon. N has to change because of the oscillating electric field of the photon. At room temperature or similar temperatures, very few molecules occupy the excited vibrational energy levels. For example, about 99.9999% of HCl molecules occupy the lowest possible vibrational energy level. Therefore, only the 0 to 1 vibrational transition is observed for most molecules at typical temperatures in a typical rotational vibrational spectrum. The 0 to 1 vibrational transition is always coupled with the delta J equals plus minus 1 rotational transitions. Now let's assume hydrogen chloride is a rigid rotor and harmonic oscillator for simplicity. Its 0 to 1 vibrational transition wave number is 2884 wave numbers, or 2884 waves per centimeter. Its rotational constant B is 10.59 per centimeter, or 10.59 wave numbers. In the infrared spectrum of HCl, the observed wave numbers are omega plus minus 2 times J plus 1 times B, where J can be 0, 1, 2, 3, 4. Therefore, the infrared peaks of HCl are at omega plus minus 2B, omega plus minus 4B, plus minus 6B, plus minus AB, etc. Since 2B is roughly 21 wave numbers, the numerical values of this infrared wave numbers should be over here the pure vibrational transition 2884 plus minus 21 plus minus 42 plus minus 63, etc. The spacings between the neighboring infrared peaks are 2B, which is approximately 21 wave numbers, or 21 per centimeter, except between the central two peaks at omega plus 2B and omega minus 2B. So there's a gap between these two. The gap is 4B, 42 centimeters. This is because, well, no peak is observed right at this pure vibrational transition. Pure vibrational transition means delta J equals 0. And delta J equals 0 is forbidden, as we know the selection rule of rotational transition is delta J equals plus minus 1. Again, a photon has an angular momentum of plus h bar or negative h bar. when the molecule absorbs a photon, its angular momentum has to change. That's why the value of J must change as well. We cannot have delta J equals 0. The vibrational transition of a diatomic molecule is always accompanied by a rotational transition, with delta J being plus or minus 1. Now let's look at this diagram. So when we observe the vibrational transition from level 0 to level 1, this transition may be accompanied by rotational excitation, the R branch, or rotational de-excitation, the P branch. Now let's look at the R branch here. J can go from 0 to 1, 1 to 2, 2 to 3, 3 to 4, and 4 to 5. Delta J is plus 1. Now in the P branch, J can go from 1 to 0, 2 to 1, 3 to 2, 4 to 3, and then 5 to 4. So both R branch and P branch can be observed in a high-resolution infrared spectrum. Now let's look at the Q branch in the middle. The Q branch also has a vibrational transition from n equals 0 to n equals 1. But now let's look at the change of J. From 0 to 0, no change. 1 to 1, no change. 2 to 2, 3 to 3, 4 to 4, and 5 to 5. So Q branch is never observed in the experimental infrared spectrum of a diatomic molecule, only because delta J equals 0 is strictly forbidden in a photon-induced rotational transition. The R branch arrows are longer than the J branch arrows, only because in the R branch, not only we have vibrational excitation, we also have rotational excitation. So we need more energy. Here in the P branch, we do have vibrational excitation, but at the same time, we have rotational de-excitation. So less energy is required for the transitions in the P branch. The P branch arrows are simply shorter than the R branch arrows. Now let's look at the simulated high-resolution infrared of carbon monoxide. Let's use P branch to the left of the gap and R branch to the right of the gap. Again, because P branch involves the rotational de-excitation, we need less energy here. R branch involves the rotational excitation. That means we have more energy here. More energy, more wave numbers. Less energy, less wave numbers. In the middle, we have a wider gap of 4 times B. Between any two adjacent R branch peaks, the gap is 2B. Same between two adjacent P branches. And it's also 2B, 2B, 2B between these two. Just in the middle, we have a wider gap of 4B. By looking at this infrared spectrum of carbon monoxide, we can somehow measure the gap between two adjacent P branch peaks or two adjacent R branch peaks. And that's going to be 2B. After our measurement, you can actually measure, maybe 10 gaps together. It's roughly 38. And then therefore, each gap 2B is about 3.8. So you can go from here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So roughly 38 wave numbers. And then 2B is roughly 3.8 wave numbers. And then B is 1.9 wave numbers, or 1.9 waves per centimeter. Now, given the value of B, we can determine the bond distance in carbon monoxide, because B equals H bar squared over 2HCI. This is the definition of B. Remember, we define HCB to be H bar squared over 2I. So B is this. And this can be expressed as H over 8 pi squared Ci. Therefore, I is H over 8 pi squared Cb. And we plug in the value of B, we get the value of I, the moment of inertia. The moment of inertia is mu r squared, so we need to compute mu. Mu is 12 times 16 over 12 plus 16 AMU. It's about 7 AMU, or 1.1 times 10 to the power of negative 26 kilograms. And then given I, given mu, we have the equilibrium bond distance, the square root of moment of inertia on top, the reduced mass on the bottom, we get 1.14 angstroms. The experimental value is 1.13 angstroms. So the theory prediction is fairly accurate. The simulated infrared spectrum of carbon monoxide shows the P branch with lower wave numbers and the R branch with higher wave numbers. The pure vibrational wave number is right at the center between the P branch and the R branch. That's about 2,140 wave numbers, or 2,140 waves per centimeter. The rotational constant B is roughly 1.9 wave numbers. To estimate the J value at which the intensity of the rotational transitions reach the maximum, we need to find the maximum occupation number. So what I'm doing here is I'm taking the first derivative of the relative occupation number. We set it to 0 to maximize the relative occupation number. So solving this equation, we get 2J plus 1 squared equals 2 kBt over HCBE. At room temperature, we plug in the 298 K here. Kb is 1.38 times 10 to the power of negative 23 joule per Kelvin. We plug in the value of the Planck constant, the speed of light, and B sub E, the rotational constant, when this bond distance is at equilibrium bond distance. All this we get 218, and then J is 6.9, or approximately 7, because the rotational quantum number must be an integer. So we're going to say roughly 7. When J is 7, the occupation number reaches the maximum at room temperature. So if we're taking the spectrum at room temperature, we expect to see the occupation number reaches maximum when the rotational quantum number is 7. And we expect to see more transitions from 7 to 8 and from 7 to 6, because we have more molecules in this rotational quantum number 7, and those transitions are the most intense transitions. Now let's look at the spectrum, and indeed we have the maximum intensity that corresponds to the 7 to 6 rotational de-excitation, and also over here it's maxed at from 7 to 8. The starting point is J equals 7, only because we have more carbon monoxide molecules in this energy level, in this rotational energy level of J equals 7 than any other rotational energy levels. Chapter 18, Rotational and Vibrational Transitions of Molecules. Section 18.4, Non-rigid rotors and enharmonic oscillators. Real diatomic molecules are non-rigid rotors and enharmonic oscillators. The non-rigid rotational energy levels are J times J plus 1 times Hc B sub E minus J squared J plus 1 squared HCD when the centrifugal distortion is considered. B sub E is the rotational constant at equilibrium bond distance. J is the rotational quantum number, and D is the non-rigidity constant. The value of D is much smaller than B sub E. Therefore, this term J squared J plus 1 squared HCD is usually much smaller than J times J plus 1 times HCBE, unless J is very large. So usually when J is smaller than 10, the first term is much larger than the second term. The enharmonic vibrational energy levels are n plus 1 half Hc omega E minus n plus half squared Hc omega E chi E. Omega E is the harmonic oscillation wave number at equilibrium bond distance. K sub E is uniless. K sub E is the enharmonicity constant. This is chi. Chi sub E is usually between 0.01 and 0.05. It's much smaller than 1. Therefore, this second term is usually much smaller than the first term here, unless n is large. Now we have the rotational energy for a non-rigid rotor. We have the vibrational energy of an enharmonic oscillator. There's another term. The vibration and rotation of a real molecule are coupled. There's a so-called rotational vibrational coupling energy. So we have this term negative n plus 1 half times J plus 1 times Hc alpha E, and alpha E is the rotational vibrational coupling constant. Well, why do rotation and vibration couple? Here's one example. When a molecule vibrates rigorously, on average it has a slightly longer bond distance, and that will change the rotational energy spacing, and of course it's going to change the rotational constant. So that's why rotation and vibration are coupled for a real molecule. And over here, this correction is a negative correction, and we have all 5 terms written over here as the sum of the rotational and vibrational energies of a real molecule. Now let me explain all those 5 terms one more time. Here, n plus 1 half times Hc omega E, that's the harmonic vibrational energy. Now we have this correction, enharmonic correction, negative n plus half squared Hc omega E chi E. Chi E is a very small number, between 0.01 and 0.05 for most molecules. J times J plus 1 times Hc B sub E is the rotational energy of a rigid rotor. Now we have this centrifugal distortion term, negative J squared times J plus 1 squared times HCD, and D is much smaller than B sub E. So as long as J is not too large, this term is smaller than HCB term. Finally, the rotation and vibration are coupled for a real molecule, and we have the coupling here minus n plus 1 half, that's from the vibration, J times J plus 1 from rotation, times H times C times alpha E. Alpha E is the rotational vibrational coupling constant. So over here, omega E, B sub E, D, and alpha E, those are wave numbers. The SI unit is meter to the power of -1, but commonly we use centimeter to the power of -1 for omega E, B, D, and alpha E for historical reasons. Again, the sum of the rotational and vibrational energies of a real molecule, a real diatomic molecule, is this. We have the harmonic vibrational energy, we have the inharmonic correction, we have the rotational energy of a rigid rotor, we have the non-rigid correction, and finally we have the rotational vibrational coupling. Now, when a molecule undergoes a 0 to 1 vibrational transition and J to J plus 1 rotational excitation, we can predict the wave number of the absorbed infrared photon. It's very easy. The energy of the photon should be the energy difference between the initial and final state. In the initial state, the vibrational quantum number is 0, the rotational quantum number is J. In the final state, the vibrational quantum number is 1, the rotational quantum number is J plus 1. Now we have this equation. This is the energy difference between the initial and final states. Divided by Hc, we have this equation. We have over here, this is the final state, this is the initial state. So we have the final state minus the initial state over here. The final state, we have a n equals 1 vibrational quantum number. So over here, n equals 1, n equals 1. This is harmonic vibrational energy and harmonic correction. Also, let's look at the rotational energy when J plus 1 is the rotational quantum number. So over here, we have J plus 1 times J plus 2 BE minus the non-rigid correction. And right here we have the coupling between vibration and rotation. For vibration, the quantum number is 1, so we have 1 plus 1/2 here. And then for the rotation, the quantum number is J plus 1, so we have J plus 1 times J plus 2 over here. And again, omega E, BE, D, and alpha E, those are wave numbers. Chi E is unitless. Now let's look at the initial state. In the initial state, the vibrational quantum number is 0, so we have just 1/2 omega E minus 1/4 omega E chi E. And over here, this is the initial state J, so we plug in J here. And this is the non-rigid correction when the rotational quantum number is J. And over here we have the coupling. The vibrational quantum number is 0, so we have n plus 1/2 equals 1/2, and then J times J plus 1, and then times alpha E. This is really tedious. We see 1, 2, 3, 4, 5 terms for the final state, 5 terms for the initial state, and we need to take the difference. After we take the difference, we have omega E minus 2 omega E chi E plus 2 times J plus 1 times BE minus 4 times J plus 1 cubed times D minus J plus 1 times J plus 3 alpha E. So this is going to be the wave number of an IR photon absorbed by a real molecule when this molecule undergoes 0 to 1 vibrational transition and also J to J plus 1 rotational excitation. So by looking at this, we know it's going to be the R branch. Alright, the value of the rotational quantum number increases. So this is the R branch. We have 5 terms here. Again, this term comes from the harmonic vibration, inharmonic correction, rigid rotation, non-rigid correction. This comes from the vibrational rotational coupling. Well, molecule undergoes 0 to 1 vibrational transition and also J to J plus 1 rotational transition. We have this formula as the wave number of the photon absorbed by this molecule. Given a high resolution set of data of the infrared wave numbers versus J, we can simply plot this delta E over Hc versus j and determine the value of the parameter d for the centrifugal distortion by fitting the infrared data with a third order polynomial function of j. So you can see on the right hand side we have a third order polynomial function of this quantum number j. Delta E over hc is just the wave number of the photon that we can collect from the infrared spectrum. The coefficient in front of the j cubed term is negative 4d. You can see from here it's negative 4d times j to the power of 3. Of course, there are other terms like j squared and j to the power of 1, etc. But if we just focus on fitting the data to a third order polynomial function of j, the coefficient in front of the j cubed term is negative 4d, and we can compute d. The value of d is much smaller than b sub e. When j is not very large, we can neglect this non-rigid correction or centrifugal distortion. So over here, 2 times j plus 1 times b is much larger than 4 times j plus 1 cubed d. So when that's the case, well, we can simplify this equation, and on the right hand side you will see a second order polynomial function of j, or so-called quadratic function of j. So this is the simplified equation when we can neglect the centrifugal distortion or so-called non-rigid correction to the rotational energy. And again, this is a second order polynomial function, so it's a little simpler, and somehow we can plot the wave number here. This is the wave number of the infrared photon versus j. We can get a Excel graph, and we can fit the data with a quadratic equation and then determine some of those values, for example this value and b value, alpha e value, etc. Alright, when j is not very large, we can neglect the centrifugal distortion or so-called non-rigid correction to the rotational energy, and the R branch peak wave numbers are expressed as a second order polynomial function of j or a quadratic function of j. We can just expand everything over here. This is just j plus 1 times j plus 3. I think you'll get j squared plus 4j plus 3, and then you just expand everything and you group the j squared term, you group the j term, and you group all the terms that does not contain j at all. And also we realize that omega e minus 2 omega e chi e is simply the wave number for the pure 0 to 1 vibrational transition. So I'm using omega sub 0 to 1 to express this omega e minus 2 omega e chi e. And this way we have a fairly simple quadratic function of j. We have 3 coefficients. In front of j squared, it's negative alpha e. In front of j, it's 2be minus 4 alpha e. And then we have zeroth order term here. The first one is wave number for the pure vibrational transition, and pe is just rotational constant. Alpha e is the coupling between vibration and rotation. And now we can just determine, using a quadratic equation fitting to determine the coefficients in front of j squared, in front of j, and then this term as well. Now let's look at the p branch. In the p branch, the rotational quantum number decreases by 1, so it's going from j to j minus 1. And we're going to do the derivation as well over here. So over here we're going to look at the final state minus the initial state. In the final state, the vibrational quantum number is 1. In the initial state, the vibrational quantum number is 0. So there's a difference here and here. There's a difference here and here. Over here, this is 1.5 squared. This one is just 0.5 squared. Now let's look at rotation. This is rotational de-excitation. The value of j decreases. It goes from j to j minus 1. So over here we have j minus 1 as the quantum number. Therefore, it's j minus 1 times j times BE. And over here, it's just j times j plus 1 times BE. Now we have the coupling. When we have the coupling, we need the vibrational quantum number, which is 1 here, 1 plus half. And then the rotational number, which is j minus 1 times j. Here, over here, we have vibrational quantum number 0, so it's just minus half, and then times j plus 1. Again, it's the final state minus the initial state. We can clean up a little. We get omega e minus 2 omega e chi e minus 2j times be, and then minus j squared minus 2j times alpha e. So we again get a quadratic function of j. It's negative alpha e j squared plus 2 alpha e minus 2b times j plus this omega sub 0 to 1. This is the pure vibrational transition wave number. So the values of alpha e over here and be over here and omega 0 to 1 can be determined if you plot the p branch data, that means p branch wave numbers over here versus the value of j, and you need to do a quadratic equation regression analysis. Alright, and again, I mean, if when you do a quadratic regression analysis, you'll get something like, ax squared plus bx plus c, right? So ax squared, the value of a is the value of negative alpha e. Bx, the value of b is this whole thing, the value of c is this. So we can somehow determine the values of alpha e, be, and omega 0 to 1 given the wave numbers of the p branch waves. Now let's look at the R branch data analysis and p branch data analysis together. For the R branch, the photon wave numbers can be expressed as a quadratic function of j. Same for the p branch, it's a quadratic function of j. Well, these two equations look quite different, except the j squared term, that's the same. But then if you look at the j term, they look different. If you look at this term, they also look quite different. But we can use a mathematical trick to pull the R branch data and p branch data together in the same Excel graph and then do a quadratic analysis altogether for all the data. The mathematical trick is this: variable substitution. If we somehow set m to be j plus 1 for the R branch, we'll replace this j with m minus 1, this j with m minus 1, and we get this expression. Well, of course, it looks more complicated. We expand everything, but then, well, a lot of terms can cancel. And in the end, we get a quadratic function of m, negative alpha e m squared plus 2 times b minus alpha e times m, and then plus over here, this is the pure vibrational transition from 0 to 1 for a enharmonic oscillator. Now for the p branch, we set m to be negative j. Now it's simple, j is negative m, so we replace this j with negative m, this j with negative m, we just get this quadratic function. Now let's compare the two quadratic functions, one for the R branch, one for the p branch. They are exactly the same, and therefore we can simply plot the wave numbers of the photon, which is delta E over hc, versus m instead of versus j versus m. M, well, is defined to be j plus 1 for the R branch. M is defined to be negative j for the p branch. Now we have only one equation to use for all the data from the p branch and from the R branch. Again, I just want to emphasize that m has a different definition for the R branch and another definition for the p branch. M is j plus 1 for the R branch. M is negative j for the p branch. For the R branch, m can be positive 1, 2, 3, 4, 5. For the p branch, m can be negative 1, negative 2, negative 3, negative 4, negative 5. Can m be 0? No, m cannot be 0, because if m is 0, that means, well, when m is 0, that means there's no rotational excitation or de-excitation. That's forbidden. Alright, m has to be either 1, 2, 3, 4, 5, or -1, -2, -3, -4, -5, etc. We do not have the data when m equals 0. Or you can just look at this equation, this unified equation. When m is 0, well, we have the wave number equals the pure vibrational transition wave number, and again it's forbidden because you have to have a rotational excitation or de-excitation, and the rotational quantum number must change by 1. Again, we can use this equation, unified equation, for both the R branch and P branch. So we can collect the wave numbers in the R branch and P branch, and then we plot this. Just remember, M has a different definition for the R branch than for the P branch. For the R branch, M is J plus 1. For the P branch, M is -J. The values of alpha sub E, B sub E, and omega sub 0 to 1 can now be determined by plotting the infrared wave numbers versus the value of M, and we can just fit all this data with a quadratic function of M. The value of B can then be used to determine the equilibrium bond distance, R sub E, of this diatomic molecule using this definition of the rotational constant. HCB is defined to be h bar squared over 2I. This B sub E, it stands for the rotational constant when the bond distance is the equilibrium bond distance. And this B sub E, we just usually it's several wave numbers. You know, for HCl, I think it's about 10 wave numbers. For other diatomic molecules, B sub E can be smaller than 10 wave numbers or larger than 10 wave numbers. But anyway, once you have the value of B sub E, you can compute this R sub E given the reduced mass. And not only that, if we have the value of the 0 to 2 overtone vibrational transition wave numbers, that's for the transition from n equals 0 to n equals 2, and this is 2 omega E minus 6 omega chi E. If this value is also available, then we can somehow determine omega E and chi E simultaneously, because we'll be able to get this omega from 0 to 1 using this quadratic fitting. And also, if somehow you obtain a value from 0 to 2, and then we have this value, omega 0 to 1, omega 0 to 2. We simply have two linear equations that contain two variables. One variable is omega E. The other variable, you may consider the other variable to be omega E chi E. So we can determine the value of omega E and then omega E chi E, and then you can determine chi E later. The 0-point vibration energy of an anharmonic oscillator is this. You can do a simple calculation given the formula for the vibration energy of an anharmonic oscillator. It's h times c times 1/2 omega E minus 1/4 omega E chi E. So over here, this comes from n plus 1/2. This is n plus 1/2 squared. The bond energy of a diatomic molecule is the depth of the potential energy well minus the 0-point vibrational energy. So we can solve for a lot of things, but again, you know, the first thing we need to do is we need to have the infrared wave numbers from a high resolution infrared spectrum. Alright, all those wave numbers. We do need to identify R branch and P branch. We need to identify the value of J first for the R branch and for the P branch. For the R branch, it can be 0 to 1 transition, 1 to 2 transition, 2 to 3 transition. So the value of J is 0, 1, 2, etc. And we define M to be J plus 1. So the value of M is 1, 2, 3, etc. And now we look at a P branch. The transitions can be from 1 to 0, 2 to 1, 3 to 2, and then we define M to be -J, and then we can pull all the data together. Both the R branch and the P branch data can be pulled together in the same Excel graph. If we redefine, you know, this variable M to be J plus 1 for the R branch, M is -J for the P branch. Now let's look at one example. It's easier to see a real numerical example to understand the data analysis. Now let's say we collected the high resolution infrared spectrum of this hydrogen chloride, this chlorine 35. The reason I specify 35 is when you have chlorine 37, you have a different reduced mass, and the wave numbers shift a little bit. Now let's look at this. J has to change by 1, so when J becomes J plus 1, it's R branch. When J becomes J minus 1, it's P branch. We collect all those wave numbers. We have the values of J. J is 0, 1 over here. J is 1 and 2 over here. We redefine a new variable M. M is J plus 1 for the R branch. Alright, and M is negative J for the P branch. That's why over here this M is 1 plus 0, this 2 is 1 plus 1, and over here this is just negative 1, this is negative 2. We copy those wave numbers here, but I decided to use the SI unit over here just to remind students that traditionally we use centimeter to the power of negative 1. Sometimes we call that wave numbers, but it's not an SI unit. All those are SI units. So if you really want to do the calculations without worrying about the unit conversion, I would start with the SI units from the beginning, and then every single value you get is in the SI unit. Now we have 4 data points. We have this 4 wave numbers per meter, and we have the value of M. So we plot this graph, the infrared wave number in the unit of 1 over M, and horizontal axis is the value of M. M is negative J for the P branch, so we have P branch data here. M is J plus 1 for the R branch. M is 1 and 2 over here. You can see the R branch data have higher wave number than the P branch data, only because over here we have rotational excitation, here we have rotational de-excitation. So over here we need a higher frequency photon, here we need a lower frequency photon. The wave number is proportional to the frequency. And now let's look at the data fitting. You have to use a quadratic function over here. So I'm using a quadratic function. I get y equals negative 30x squared plus 2057 plus over here 288,565. R squared is 1. So really we just compare this coefficient in front of M squared with this coefficient in front of X squared. So we can immediately see alpha sub E is 30 per meter. 2BE minus 2 alpha E is 2057 per meter. And this omega from 0 to 1 is 288,000 per meter. Again, the wave number of the absorbed infrared photon for a real molecule can be expressed as a quadratic function of M. M is negative J for the P branch. M is J plus 1 for the R branch. We do a quadratic fitting over here, and then we can solve for alpha E, BE, and omega from 0 to 1. So again, we just compare this two. We see alpha E is 30, 2B minus 2 alpha E is 27, omega 0 to 1 is 280,565. The unit is meter to the power of negative 1. Sorry about using M for meter and M for the variable, but unfortunately in physical chemistry, every single English letter has 5+ different meanings, and so does every single Greek letter, I believe. Now this alpha E is determined, 2B minus 2 alpha E is determined, omega from 0 to 1 is determined. So by looking at these two equations, I think you can easily determine the value of B sub E, which is this. Why do we need this? Well, as long as we have B sub E, remember H times C times B is H bar squared over 2I. So if you have Planck constant times the speed of light times this value, well, the result is equal to H bar squared over 2I. H bar is a constant as well, so you can determine I, the moment of inertia. Given the moment of inertia, you can determine the equilibrium bond distance easily, as long as you know the reduced mass. And it's awfully easy to determine the reduced mass for a diatomic molecule. For example, HCl, you have mass 1 AMU, mass 2, 35 AMU, and then mu is very close to 1 mu. I think it's 1.62 times 10 to the power of negative 27 kilogram-ish. And then once you have the reduced mass in the SI unit, you have the moment of inertia determined from the value of the rotational constant B sub E. You can determine the equilibrium bond distance for each cell, and that's experimentally how chemists determine the bond distance for diatomic molecules. And over here we have the wave number for the pure vibrational transition. Given this number, we can determine the difference between the depth of the potential energy well and the bonding energy for a diatomic molecule, which is just 1/2 times H times C times this number.